Hello, hello, hello.
Hello, welcome to Rust Week, everybody.
Welcome to Rust Week 2025, the first ever Rust Week.
It's amazing,
Yes.
isn't it?
How did you like the video?
Terrence honestly spent all night rendering, sitting next to a progress bar.
We spent 3 days rendering.
Oh
All
man,
right.
no food, no water,
Alex,
just rendering.
will you introduce yourself, please?
Yes, my name is Alex Band. I work for Enelnet Labs. We make free open source software in Rust for a really, really long time already. And I'm here together with my colleague Terrence.
Yes, I also work at Enelnet Labs, and I'm also one of the organizers of this conference. If you see any other people who are helping organize, the volunteers with the yellow t-shirts, you can ask them questions if you have any. If you need help with anything, you can find them. And if you really can't find any of us, you can just go to the registration desk and there will always be somebody there.
So the Rust community and its inclusiveness and its openness is super, super important. So for this entire event, including all of the socials, there's a code of conduct, and we would kindly like you to read the code of conduct and adhere to it for the entire week to make everybody sort of warm and safe and welcome for the entire week.
Yes, and we also have a live stream that you can check into if you just want to sit downstairs and maybe watch it, or maybe you're watching the live stream right now. Hello to the people at home. There's also a Discord that we have. If you have any questions about the event, you can just chat there. And there's also lots of social activities. You can host your own. We're hosting some as the organization. You can sign up for them there, see what's going on. It's honestly a lot of fun and a lot of fun chatter happening there. So do join it.
Yeah, so all of the entire event will be here upstairs. The main event will be in Cinema 12 right here, and then there are 2 other tracks in Cinema 11 and Cinema 10. It's all next to each other, so you can't really miss it. All of the social events, lunch, and everything else, you can find that downstairs.
Yes, and you can be in the in-between areas, between things if you want to. It's a little bit quieter there. There's not much going on there, but if you want a little bit of space, you can go there. So the tracks are, here's the main track. Then today on Cinema 11, there's the ecosystem track, and then Cinema 9 is the industry track. If you have a special ticket for that, I assume you wouldn't be here, you would be at the industry track already. The ecosystem track features some special talks which come from the GoSim Spotlight. So there has been a round of nominations for cool Rust projects that should be highlighted, and people could nominate the projects that they liked. And then there was a panel of judges who selected a few to come here to give a talk, and also to just talk to people. So there is some talks by them today at the ecosystem track, and then also on the elevated area of the restaurant. That's where they will be if you want to talk to them. So you can talk to all the finalists there.
Okay, let's see what else. Oh yes, there's Wi-Fi in here. If you want to know the Wi-Fi code, there's a QR code probably. Have a look at the back of your badge.
Just password and SSID.
Exactly, yeah, okay. Sorry about that. I have a badge, I should check maybe. Anyway, also with regards to the code of conduct, Discord and everything, you can find all of that information on rustweek.org. Yeah, that's it. Anything else?
Let's
oh
do a
yes,
show of
of
hands.
course. We're celebrating 10 years of Rust. Yay, woo! So with this, we would like to do a show of hands. Who's been using Rust longer than 1 year? Can we show longer than 2
That's
years?
almost everybody.
Longer than 3 years. This is exciting. Longer than 4 years? Oh,
That's still a lot of people.
5
Wow.
years? 6 years? 7 years? 8 years?
Starting to get sparse now.
9 years? All of the 10 years? Really?
Longer than Rust 1.0. All right, let's go
Wow.
on. Before 1.0, 11.
Oh. not?
12? I still see a few hands. Anybody longer? How long? How long? 0.11.
I think you won. Congratulations. Round of applause for everybody. 10 years of Rust. Would you like to introduce the first speaker?
I would. And he's also been using Rust for a long time, and that's what he's going to talk about. Next up is Alex Creighton. He's worked on Rust for a long time. And a fun fact is that while he was working on Rust for the longest time, his net lines of code was negative on the Rust project, which, yes. Now he's working on Wasm Time, and who better to talk about how Rust has changed over the past years than Alex Creighton?
All right, thank you so much. It's a pleasure to be here. This is so many more people than I would have expected to see here after 10 entire years of Rust. And this is the question that I want to pose in this talk, is why have I been using this? Why have we all been using this? Why does Rust even exist after 10 years? What is this sort of secret sauce? Or just, I don't know, my own opinions about why are we all here? So if you ask someone kind of lying around, why are you using Rust? They'll probably say, oh, it's fun. It's an enjoyable experience. It's kind of relative to a lot of the languages, a lot of the tools. It's just kind of, it's nice to do. I hear there's this Stack Overflow survey, which often says that it's a very loved language. People who use it want to come back. So all right, thank you so much. That's all I have. No, I'm just kidding. So I'm actually going to try and dig in a little bit further here. Sort of why do we go behind this a little bit more than just it's fun, but why is it fun? A little bit more about the technical side, a little bit more about sort of the social side. Why I think that we're all here. So to kind of motivate this, I want to give you a bit of a backstory myself. So through these past 10 years, and a little bit beyond that, I've made a lot of contributions to the Rust compiler. This is sort of numerically. I'm also just kidding here. No one can possibly beat the juggernaut that is Bors. But nevertheless, I have done a lot of contributions to the compiler, the ecosystem. This is just commits themselves. But I've also seen the project through many, many lenses. I have been around for quite some time. I've been on many, many teams. I've been pre 1.0, post 1.0. But the other interesting aspect about myself is my contributions are very backloaded. I discovered Rust around kind of late 2012, the kind of 0.5, 0.6 timeframe. I was hired by Mozilla to work full-time on Rust, and this peak is when we didn't really use Bors at the time, so I could get a lot of commits in. It was great. But that was the Rust 1.0 peak, and so I did a lot of Rust afterwards, a lot of maintaining things, adding new features, kind of just developing the language. But the other major thing happening here was this is where WebAssembly came out. A little less relevant for Rust, but much more relevant for me. And so you probably haven't heard much of me or seen a whole lot of me in the past few years. I've been off doing a lot of WASM stuff here and there. But despite all of this has sort of given me at least a bit of a broad perspective. So I kind of want to offer my thoughts of this question of why are we all here? Why is Rust here after 10 years? And how has it been so successful? So beyond this sort of fun aspect, I think you can focus on the technical aspects of Rust. The concept that Rust is a superpower, this concept that Rust is sort of energizing you or making you more productive, making you more reliable in all of the software you work with. So I kind of want to go through this from a personal example that I have. So I'm going to be talking about Wasm Time, the project that I work on, and WebAssembly. If you're not familiar with those, that's totally fine. This is more of just kind of a high-level overview of how we're using Rust and kind of what we're using internally. So when you write a WebAssembly runtime in Rust, one of the first things that we need is we need it to be reliable. This is sort of one of the chief requirements that we have. And so the reasons for this is that in the WebAssembly world, we're running completely untrusted code. We're running this in a very high-stakes environment where two completely different modules are running right next to each other, and they're not allowed to actually talk to each other, and we have to enforce that at runtime, compile time, all that good business. And then finally, we also have to run this practically everywhere. Everyone expects WASM to run pretty much on every machine, and so we have to do the same thing, but also reliably all at the same time. So reliability is a key thing that we want in Wasm Time, and what we ended up using in Rust. Another aspect, though, is this high performance aspect. Wasm is typically expected to run very, very quickly. This is kind of the very small performance gap with native. And additionally, this often requires manipulation of very low-level primitives, so kind of various syscalls, various memory layouts, kind of all that fun stuff that Rust gives you access to. But finally, there's this other aspect, which is we need Rust to be productive. We don't have a team of dozens and dozens of maintainers. We have a small handful of folks that are working on this. And then we also can't have all of these principles of reliability, performance, and productivity. We don't want to compromise on those. We don't want to sacrifice performance for reliability, and we don't want to sacrifice productivity for performance or things like that. But it turns out this is kind of where Rust comes in. If you take these three features of reliability, performance, and productivity, it turns out if you go to the Rustling Rust homepage, those are front and center. They are the major features of Rust, which makes this basically an absolutely perfect fit for what we are working on. And this is sort of some of the technical strength pillars, in my opinion, of Rust. And so I want to give you a bit of an overview of sort of the internals of not only kind of high level how we're using this, but some of the details as well. So one of the nice parts about Rust is we can segment all of our code into our nice little box of unsafe code and a nice little box of unsafe code, or safe and unsafe. But the really nice part here is that we have massive portions of WASM time written in completely safe code. This is chiefly things handling completely untrusted data, so parsing and validation and compilation and translation, and also the runtime APIs of when you make a syscall. How actually processing all those arguments and kind of shepherding all that along. This is all 100% safe and is a massive boon to reliability and productivity to make sure that we just, frankly, don't have to worry about these nearly as much as we would otherwise. Now, of course, we do have some unsafe code. We have a runtime, we have a just-in-time compiler, we're manipulating virtual machine APIs, virtual memory APIs, but all of that is Rust is giving us the ability to sort of nicely contain this. So Rust is giving us these tools to kind of build this abstraction for ourselves, where we can kind of segment all of our unsafe stuff over here, all of our safe stuff over here, and we can have it kind of keep a nice clean separation between that. But what I think is sort of one of the true superpowers of Rust is not just the fact that it's giving us the ability to do this, but this is a multiplicative effect which affects all of our users as well. So depending on whatever you're doing, you're building whatever embedding you want with WASM, or whatever embedding you want with WASM time. It could range from giant servers that have many threads and lots of async threads and lots of all these tasks, to tiny, tiny devices that have none of that even as a capability. And all of this at the same time is built on top of these abstractions that we've built and have all been able to do with Rust. So all of this is completely safe. All of this is isolated from all these little unsafe boxes and all these little unsafe pieces. And so effectively what this is enabling is you as the users of WASM time or of Rust libraries are benefiting from this speed, this reliability, this productivity just by using these well-designed libraries or by using Rust under the hood as well. So I can kind of summarize a lot of the sort of technical aspects of Rust with this concept of a fire flower. This is where little Mario eats the fire flower, becomes giant Mario, and hurls fireballs. So we're not really going to hurl fireballs in Rust. That's very unsafe. But this was a series of blog posts which kind of capped the kind of about 10 years ago, or around some number of years ago at this point, which was summarizing these pillars of Rust: the speed, reliability, and productivity. And this is something where what I think about all this is kind of what I was saying is that this is compounding for not just you, but all of the users of Rust. So you yourself are not selfishly benefiting from these results, but everything is compounded, every layer down the stack, that speed, the reliability, and productivity every single time. And so kind of around the 1.0 timeframe was these other concepts of we can have our cake and eat it too in Rust. We have all these fantastic technical achievements because of these foundational pillars we have: this fearless concurrency, abstraction without overhead, and stability without stagnation. Kind of this is the very, very early 1.0 timeframe. So these are fantastic blogs. I would highly recommend reading them, and also the whole entire series that was summarized on the Fireflower pages as well. But okay, I've been talking a lot about the technical aspects of Rust. It's kind of easy to focus on the technical aspects once you get past the fun part. But I do think there's more to this. It's not just that Rust is technically good. There's a lot more behind this project. There is so much more happening. And I would phrase it that Rust is changing much of the time, and almost always for the better. And so I want to kind of go through a lot of these things. I want to take you back to Rust 0.5, and I want to show you some of the primordial Rust that we actually came from. As a small disclaimer, this is about 13 years ago. I have a horrible memory, so if I get anything wrong, that's not intentional, just letting you know. But all right, first thing I'm going to talk about from Rust 0.6 is In-Hadawama. If you have not heard of this, fantastic, it worked. The whole point was imagine never hearing the phrase or words aliasable, mutable again. This was sort of the original idea of ownerships in Rust, or kind of the original concept of ownership and borrowing kind of making its way through Rust kind of as it was developed. And what this ended up being was that Rust 0.5 was not quite sound as a language, and Rust 0.6 made it a lot further forward. Not quite there all the way yet, but it was sort of the ideas were starting to form. An example, I pulled this from the Rust 0.5 test suite. It's a little funky. I was thinking this morning, this is kind of like I'm showing you a picture of a velociraptor. I'm like, one day that'll be a chicken. So we can see here, we've got like some mutable fields, we've got some sigils here, we've got pure functions. This was even early enough for me, I'm not entirely certain what a lot of this was doing, but as we now know, almost all of this is gone. We don't have mutable fields, we don't have these sigils, we don't have this pure, and we can sort of see that Rust's ownership system was starting to form around this time, and this is sort of trying to build up all those technical foundations pretty early on in Rust's lifetime. So these sigils that we've been taking a look at, or I was seeing, this was historical Rust. This is sort of a historical take on ownership and various ways that we can actually use ownership. So this was, again, from the Rust test suite, which is a little contrived, but not entirely contrived. And what this would look like nowadays looks like a lot of soup, but there's actually a lot going on here. So we can sort of see these twiddle brackets are actually more like vex. We've got these @mutes, which are GC-like. We never had a necessarily full GC, but also with interior mutability. These twiddle stirs are strings. This @ is GC. So there's some clear correlations. We can start seeing that Rust is still existing here with slightly different syntax. But I think that one of the major pivotal changes this was trying to take these features out of the language and putting them into the libraries. So this was us sort of kind of realizing that we want to be shooting for a pretty low-level language. We want to shoot for a pretty low-level, powerful ability to not require these built in, but we can actually build these abstractions in the standard library. So this is where today we have string, vec, box, RC, refcell, all sorts of abstractions. And so all of this was removed from the language in 0.11, but we still use it today. All of these same concepts are still around. We just call them slightly differently. The next thing I want to talk about, which is a little less so on the technical and syntactic side of things, but is a little bit more so on the runtime side of things. So this small program, it's a little weird syntax with this do function, but that was actually just syntax sugar back then for invoking a function with a closure as the last argument. We can clean this up a little bit more. We no longer have a println function, but we've got a macro. We don't need pub. And this actually looks a lot like Rust. So you could write this today, and there's nothing necessarily wrong with that. However, one of the weird things about this is that this actually spawned a green thread. This was different semantically today from Rust, even though it's syntactically valid. And this was representative of a time where Rust in its early trajectory was thinking about green threading, end-to-end scheduling, kind of all that fun stuff. We originally used libuv in the standard library, and this was how we built. This was the plan. We were going to have an entire runtime, and everything was going to be having green threads. You can spawn them. They're super cheap. That was the dream. But down the road, we realized this probably isn't quite right for Rust. We're going to try and shift this development a little bit more towards native focus as well. So we actually took libuv out of the standard library. We made it into libgreen, and then we also added libnative, which is more like native threading that we have today. But even this didn't feel quite right. It was not the best abstraction to have, and so we actually ended up removing libgreen and merging libnative into the standard library that we have today, and that's sort of the standard library that we all have right now and has persisted through to today as well. But the major thing here is this is, again, a absolutely pivotal change to Rust prior to 1.0, which was saying that, no, we want to focus Rust as this very low-level, very portable tool. You practically wouldn't see all of the embedded talks or all the embedded folks downstairs today if we still had a green threading runtime, most likely. And so this is sort of acknowledging that that's not the direction we want to go in, but again, a very, very big change early on in the history of Rust. Sorry, the final change that I want to talk about is one that I think was really interesting in terms of, I've been talking about technical changes or runtime changes, but this was very much more a social change. Now, on the surface, super simple. There was RFC 544, which said that we had int and uint types way back when. Let's just rename them. There wasn't even a proposal of what to rename them to. It was just saying they're bad, we should rename them. Now, today we call these isize, usize, and it's kind of a given today, but at the time, this was contentious. The community effectively had reached a consensus saying, yeah, this is a bad idea, we gotta rename these. Whereas the core team at the time effectively had a talk one day, we discussed it, and we just handed down a decision and said, nah, we think it's fine. We're gonna leave it exactly as is. But this ended up being, definitely for me personally, but I also think for the project, a very pivotal moment to learn about open source governance. It turns out if you just hand someone a decision, there's nothing open about that. There's nothing collaborative about that. That's not actually building consensus. And so this is very obvious in retrospect, but it took time to learn. It took time for us to grow into what does it actually mean to be an open source project that is openly governed, where anyone can walk in with any change and actually be seriously considered. And so this decision, or sort of this initial act that we kind of closed the thread, spawned hundreds or thousands of discussions across dozens of forums at the time. This was a very, very widely debated topic. Not the int and uint necessarily, I mean, that was certainly part of it, but also just how these decisions were made and what the failings of the core team and how things should be adjusted and how things actually come out today. So if you've ever looked at the standardization process in Rust, one of the features right now is what's called a FCP, or a final comment period, and this is where that came from, or this is sort of one of the original motivations for final comment period. And to me, this is one of the more formative moments, at least for myself, in the governance of Rust in the early stages of learning what it actually means to govern this language and to actually have a successfully managed and governed language that's not just the interest of a few. So all right, coming back to this, again, this question of why are we all here? Why is Rust successful after 10 years? I've given you some ideas of Rust is technically very strong. Rust has been changing. I don't know about you, but if Rust still looked like 0.6, I probably wouldn't be here at this point. But as we all know, when Rust 1.0 was released, it was absolutely perfect and nothing has ever changed since then. Of course not, no. Ever since 1.0, I've been describing all these ancient changes. I'm showing my age, but even then, there are still many, many changes happening today for the better and that are actually very much improving the language. So I want to go through some examples of these and show you how some code has changed throughout the ages. So I want to start with async. It's kind of one of the nicer things that has been evolving throughout Rust over time. In Rust 1.0, this is how I wrote async, which is, no, we just didn't. We just gave up. We just said, we're not even going to try this. We'll just try and figure that out later. So what actually ended up happening was around 1.15 was where we had procedure macros added to the Rust compiler. So this enabled us to build this futures crate in the ecosystem. We could have an async and an await macro. This was built on generators, which were still requiring nightly at the time, but we could start seeing what it might look like to have async and await in the language. Now, obviously, this is far from what we have today, but it's sort of similar-ish. And the other fun fact here is this is actually when Serde became stable. I don't know if you can imagine a Serde without Rust, but I have Serde and so many projects at this point. And so this was a major, major feature, not just for async development, but also just for Rust in general, having procedural macros there. But so the next development of async happened around the 1.26 timeframe. This is when we could return impl_trait. So all of a sudden now, we could actually have something much closer to sort of the runtime semantics, and this actually worked on stable Rust. This was the first time that async kind of started coming into the vision of stable Rust. And so we now had a trait, the futures trait in the futures crate, and we could return it as the actual no overhead kind of structure as we have here. We didn't actually have the async keyword yet, though, and we also didn't have a wait. And so this is where if you wrote another map and then an and then a map, this actually gets really nasty really quickly. And so while this was close, this still was not necessarily production ready. Like you could run it, but you probably couldn't scale it to hundreds of thousands of lines of code and have anyone understand it other than yourself. So the final thing here, or rather the next stage of things happening here, was 1.39, where we actually got the async and await keywords that we have today. And this was very, very much a labor of love on so many people's aspects, and also not necessarily love, but just it was a huge amount of effort to get this stable, to get this actually released in the ecosystem that we all now have today. And this is sort of a key change, which I really want to emphasize here, that you'll notice that these version numbers are increasing quite a lot over time. I started on 0.5, and this is 0.39 with async. There's not one person pushing these changes through. There is not one entity which tried to do async for the past 6 years and finally succeeded at this point. This is an innumerable number of contributors over spanning years of time, coming in and going, pushing this change forward, relentlessly pushing the project a little bit further, where no one person is going to push literally everything across the finish line, but everyone can kind of collectively push a little bit more. So I'll talk a little bit more about those aspects there, but async is still improving. Just around last year on 1.75, we can have async and traits now. And so this is, again, so many things. There are so many features that's actually happening here under the hood that took there's a reason it took 39 to 75 to actually release this feature. It is very much a community effort to push this forward, and very much a concerted effort on behalf of the entire project to ensure that these all actually end up succeeding in the end. So again, though, I'm focusing on the technical aspects. This is sort of the language has changed, we've added features, that's great. But there's non-technical things, or sort of more of the developer side of things as well. So in Rust 1.0, when you had a lifetime error message, this is kind of what it looked like. Now, at the time, we thought this was fantastic. This was fantastic at the time compared to other compilers at the time. But as we can all see nowadays, we're looking at this and, whoa, there's way too many file names. It's way too dense. It's kind of hard to see what's going on now. And so this was around the 1.12 timeframe, which we really took a focus on the error messages in the Rust compiler. We always knew that learnability was going to be one of Rust's weak points, and so error messages coming out of the compiler were absolutely critical for guiding people in Rust and guiding people to learning this. And so this was a massive change internally, and we can still see this today. I don't think this error message looks exactly the same today, but it is very, very similar and is much, much easier to digest, but furthermore set up the entire framework for all of the errors we have today and all of these fantastic diagnostics. Which again, this is an effort that maybe kind of started around here where the actual original change was made, but I've seen these error diagnostics change for dozens and dozens of versions. They continually improve over and over and over again. This is, again, a labor of love on so many contributors constantly pushing this forward. And it almost always starts with someone coming in and saying, that's nice, but let's try and make this better. We can actually improve this a little bit more. And so I want to also focus a little bit on cargo. This is not just the Rust compiler or the Rust tooling, but the developer experience in that as well. So around the 1.0 timeframe, we could write our manifests, we could write our package, we could write our dependencies, but we couldn't really do a whole lot else. It was actually a pretty limited system at the time. So it was actually 1.13 where we were able to write workspaces. Now, I don't know about you, but practically every project I work on today has workspaces in it. So I was very, very happy when we were able to actually land this to have only one target directory and one lock file and one project and one repository. But Cargo has continued to iterate as well in terms of we have patches now, so we can, for example, take in small crates with small edits. We can now also have profiles configured where you can configure flags at your workspace level. And then finally, we can also do lints. We can actually configure Rust lints or Clippy lints, and this is sort of the iterations of the Cargo manifest over time. Now, all of these aspects are kind of, I didn't focus too much on Clippy here, but Clippy didn't even exist at 1.0 or not on stable at 1.0. And so even, I forget exactly what version that I actually landed in, but Clippy was another major developer tool improvement that happened over Rust's lifetime and is one of the more critical ways that people learn Rust today. And it's a fantastic tool for new developers and a fantastic tool for everyone new coming to the language. So I would be remiss to talk about change if I didn't also talk about compiler speed. This is a graph from perf.rustlang.org from 1.28 over to the present of the average compiler speed over time. And you'll notice here kind of this idea of slowly pushing something forward is actually pretty easy to see in this graph. There really aren't that many giant drops. No one just walked in one day and said, I'll make the compiler 2 times faster. If they could, they already would have done that years and years ago. And so we can see here this continuous trend of over the years, little bit by little bit, 1%, 2%, 3% at a time, we can pull this down to where about twice as fast as we were back then. No one change adds up. No one change was the end-all be-all, but it's this continual effort of people over and over and over again saying, I think we can do a little bit better. I think we can push this a little bit further forward. And I think the other fantastic part about here is this is, again, not just one person. There is an innumerable number of contributors who are constantly looking at this, constantly trying to make this better, and constantly taking a look at all these graphs, and it changes year by year. The same person has not been doing this for 15 years. It's kind of rotating in and out, and people come and people go, kind of as happens in an open source project. So all right, I wanted to kind of do a little bit of brain dump. I'm talking about a lot of changes here, but I kind of wanted to write down everything that I could think of that has changed since Rust 0.5 when I started, and kind of all for the better. These are all features or fantastic things in Rust that I haven't even talked about in this presentation. So I wrote a little bit of a list. I wrote a little bit more of a list, and I started running out of room. And I really want to emphasize here, this is the tip of the iceberg. This is everything that I could think of sitting down for an hour. I got the font really small. You can actually read a lot more of that than I thought. This is a very large screen. But nevertheless, this is only me. I am one person. I am a small aspect of Rust. The actual community and the actual efforts are far, far beyond this. There are so many things that are not mentioned here. There are so many things that I am not even aware of, which very much deserve to be up here as well. And so this is, again, to me, it's this juggernaut of a community that's behind Rust, this unrelenting community, which there is incredibly diverse, it is incredibly large, and everyone thinks that it's great, it's nice, but I want to try and push this a little bit further forward. I want to try and make this a little bit better. So we have everything here from additions to features to, I don't know, there's so many aspects here. So all right, I've been talking about why are we all here? Why is Rust successful after these 10 years? And we've got this superpower aspect, and now we've got this change aspect, how we've seen Rust evolve over time. Rust is not Rust of 1.0, Rust is not Rust of 0.5. And I think that's why a lot of us are here. I would not still be here if Rust had simply frozen in time at any one point in time. It's this idea that Rust is continually improving, that Rust is, if it doesn't quite solve your problem today, it has a very high chance of solving it tomorrow. But I think, thinking more about this, kind of, why are we all here? Why is Rust successful? I think we can actually shrink these quite a lot and say that it's actually excellent folks on this project that are pushing this forward. I think that is one of the fundamental foundations of Rust. So in essence, I am here because of all of you. And I think all of you are here because of either the person next to you or people otherwise here. It is this, again, unrelenting community which has constantly pushed this language forward and has constantly done such a good job over the last 10 years of pushing this language forward. So I can kind of summarize at least my own answer of why am I here after 10 years. I would say Rust is a fantastic tool in any toolbox. It is technically excellent. It has done very, very well on its speed, productivity, and reliability. It's not the best tool for any job, but it is a fantastic tool to have, and it is extremely useful when you do need it. Rust is not perfect. Rust never has been perfect, and currently is not. But it has a decade-long track record of continuously improving for better. This is 10 years and more before that of continually getting better, continually improving on what it's currently doing. And if Rust does not currently solve your problem, we couldn't do async at 1.0, we can definitely do async today. And then I think, finally, again, Rust has, for 10 years, had fantastic folks working both on it, in it, and around it. This is everywhere I've seen in terms of this community has been extremely successful, and the language is successful because of the community. So that's all I have. I think I will definitely leave you with this. I would say a lot of us are here because it was good, and I think a lot of us are going to stay here because it's going to get better. Thank you so much.
And then we have time for some questions. And Tert has a catchbox, which he's going to throw around. And of course, I can't see anything. Anyway, so somebody raising their hand, I have no idea. I can't see a thing.
I can see a little bit more if I step out of the light.
So you're right. You're just looking to.
Oh yeah, no, I've been blinded the whole time. It's okay.
Who's got a question? Raise your hand up high. I hear a yeah, but I can't see any. Nobody has any questions.
Nobody has any questions.
We need more coffee.
Oh, sorry. Slipped up my hand. I'm sorry.
Somebody is now wearing their coffee.
Okay. Oh, bloody hell. Yeah, great talk. Thank you. With the original sort of prehistoric Rust code that you showed, how much of was it influenced by Cyclone, which was sort of a first attempt of making like a safer version of C? It looked quite similar.
That's fair, and I have heard of Cyclone as well, and I'm the wrong person to talk to, unfortunately. I was never aware of Cyclone, and I was very green behind the ears when I was working on all that at that point, so I was not responsible for a lot of that. So the answer is, I have no idea. I would recommend, I suspect Nico could probably give you a bit of a better answer, but also, I'm actually just not sure, sorry. That was old even for me.
Thank you.
I see a hand over here in the front.
Okay.
I'll just give you a mic.
We're going to hand it, yeah, no, to Zine.
Hello. Rust, I really enjoyed your talk. Why are the Rust stations so good? Like, it's been 10 years. There's plenty of time for weird stuff to happen. Like, how do y'all keep it going, you know?
If you figure it out, let me know. Honestly, this is a mystery to me as well. Rust has not Rust has had its share of drama. Rust has had its ups and downs. Rust has not been a perfect language or a perfect community at all times. It has been a labor of love that it's gotten worse, it's gotten better. I've had my own peaks in Rust, I've had my own troughs in Rust. Somehow it always bounces back. My thoughts are, I think a lot of the stuff about Rust is rooted in sort of the technical aspects of it is so technically good, but also the foundational roots of Rust are, okay, things are great, but let's make them better. And it's this idea of, okay, but can I not have my cake and also eat it too? And so I think a lot of that's the very technical side. That doesn't explain the community, but I feel like a lot of folks come to the community kind of like that, where it's like, I don't really want to settle for a bad community. I want a productive. I want an effective. I want to be welcome here. I want to be thriving here. And I think a lot of folks bring that to the community. And I think that I don't know. That's my personal take on where it comes from. But this was not shepherded along. This was not created. This was more of a sort of organically grown thing. And if anyone figures out how to replicate it, I think that'd be fantastic because there's a lot of other places we could put this as well.
All right, got a question over here.
So you've been around longer than almost anybody in the community, including most of the people still working on Rust at this point. And the usual question most people ask is like, what from that really early era, like what would you have changed before 1.0, that kind of thing. It's this perennial question. I want to ask the opposite question. What that did get changed do you wish hadn't been? Or what from the pre-1.0 days do you wish was still around but it isn't anymore? What should we bring back?
Oh, wait, no, I have the perfect answer for this. Okay, so one of my first projects working at Mozilla was to rewrite the channels in the standard library. I wish I'd never done that. So in terms of, that was more of a runtime-y side of thing where this was sort of, it was really leaning into the green threading runtime. It was really leaning into like, we want these performing, we want these fast. And then we also ended up realizing, well, we also want to working on native and across green threads. And so I built this monstrosity that I think took like years to remove from the compiler and the standard library at that point. But I'm glad it's all gone now.
Fair enough. Thanks.
Yeah, okay, in the front here. Well, there were two. I'll give you the mic next.
One thing is like, what do you think Rust can't do because of the 1.0 stability that might be like a future language that could replace Rust? Like what can't Rust do that a new language might be able to?
That is a fantastic question. And one aspect of that is that if Rust is still as successful as it is today in 100 years, I'd actually be really surprised. In the sense of, I'd be surprised if Rust was the end-all, be-all of languages, or this was nothing to come after Rust. As for a specific answer, I'm probably not the best person to answer that. In the sense of, I mean, it's one of those where I got what I feel like a lot of folks dream about. I got to make a language, and now I work in it on a daily basis, and it solves all my problems because I got to work on it. And I got to solve all my own problems. So in terms of what else I would add, I actually wouldn't add anything. I was happy a long time ago. I joke that the Rust I write is actually a 1.0 style Rust. It's not true. I actually use tons of new features nowadays as well. But I think that I don't know. I am personally happy, and as for, I think everyone will have a slightly different answer to that question as well, though, in terms of what they think is the next feature of Rust. And I think, I mean, in some sense, this was it's something we always worried about, kind of designing the original release processes, designing the original. But this was additions. That was the intention, is that we did make mistakes, and we knew we were going to do that. We didn't know how we were going to fix it, but we figured it out a couple years later in terms of additions. And so that's sort of the current of that should be enough of an escape valve. But I guarantee you, there's something that's going to come up. That already has come up in terms of we just can't fix it at this point. It's a little bit too hard.
All right, there's a question over here, right?
So do you think that iteration speed has played a role in bringing us here? Because Rust comes out every 6 weeks, a new version, and that's faster than most programming languages iterate.
That's an interesting question. I feel like it was definitely something that we talked, oh my God. I remember sitting in a room before 1.0 with a lot of folks at Mozilla, and we talked for like 6 hours about the release process and what to do. And it took us forever to actually settle on what we have currently. And I would say while I do think the iteration speed is a crucial aspect in terms of people can rely on, there's not the rushing. It's people aren't rushing features in because there's another train coming. You can always wait a little bit more. But I think it's in my mind, it has very much increased the quality of the compiler because we're not rushing features. It has very much increased the quality of users as well, but not so much from the release cadence necessarily, but more of the release process. So we have official binaries. We have official releases that everyone is at least by default, you can use. And there are many other options as well now. So I do think that actually is a key aspect. But this is one where sort of the competition at the time was like C and C++ and installing various tool chains there. It's not too hard to compete with that sometimes in terms of pulling those from various sources and having only one source. And so, but anyway, I do agree. I think that actually is a key thing that has helped, especially in terms of Rust's stability in itself, but also the quality of the compiler.
Right, you were quite quick with your talk, so we have even more time for questions. If you're up for it,
I love answering questions.
awesome.
We're
Okay,
just going to keep going.
Please do.
we have a question over here.
Cool. Yeah, I noticed that the compile time graphs, I mean, everything was pretty split and everyone followed their own track, and then there was this lovely little blip in the middle. I think it was 153 or 52, something like that.
I thought this
Is there a
was okay.
story there?
I wish I knew. I'm not actually sure. I don't know if that's just kind of a measurement blip or what. I feel like people who actually maintain these graphs would definitely know that. But I unfortunately don't have a. Oh, wait. Are you answering the question? Yeah. Oh.
Incremental compilation broke.
Right.
Incremental compilation was unsound, so it was disabled.
I remember that.
Yeah.
Yes. Okay.
It was dark times.
There's your answer.
Oh, thank you.
All right. We'll now have a little bit of a break. Let's hear it for hear for Alex.
Yeah, thank you, Alex.
Thank you, Alex.
So if there are people who want to change tracks, people want to come in, get out, and this is the opportunity to do so.
Exactly, and the new people can come in.
See, this is exactly what I expected. Because in about 5 minutes, we'll continue with the next talk.
Yeah.
As I was showing like 1 minute left, according to the clock.
Yeah, exactly.
Oh,
and we were all like,
So the clock said, so the thing said 35 minutes talk, and I implied 10 minutes break between talks. So I was showing the true, like to leave the break time.
this is good because Yeah? We want to start at about 25. So I want to give everybody about 2 minutes to take their seat so we can continue with the next talk. Thank you. excited.
We switched laptops. We did all sorts of
yeah.
things. Are the chairs at least comfy?
Yeah? Yeah, I'm secretly hoping that I can tell everybody to reach under their seat for their 3D glasses and then we're going to do like a presentation in 3D. But first I want to introduce a Grandmaster Tetris player. Yeah.
Hello.
She's working on CAD software in Bevy, and she founded Leafwing Studios together with one of her other speakers, Alex Cecile. And I want to introduce to you Rose Peck.
Thank you. The Tetris thing is real. I do want to warn everybody before we start, this talk includes audience participation. So there they go. So the extroverted among us can prepare themselves to participate when the time comes and yell answers to my questions when we get there. But today, we're talking about floating point hashing. We're talking about why you should never do it and why I decided to do it anyway. By the end of today's talk, we will hopefully all have learned some new, mildly cursed information about everybody's least favorite number format. But first, I want to talk a little bit about some problem context. I originally gave this talk internally at my day job at the Foresight Spatial Labs because this came up in a real-world problem that we had to solve: rasterizing non-uniform points. We had a geospatial point cloud, which you can see in the top left there. And this point cloud was tagged with a bunch of different attributes, which you can see I've shown in different colors. The point cloud came from a set of real-world engineering data, but due to an NDA, I can't say exactly what the data was, but like, for example, this may have been particles generated from erosion data on a riverbank. So sediment erodes away from a riverbank, and then we make a point cloud of all of the particles that eroded away, labeled with what kind of sediment it was, when it eroded, that kind of thing. It wasn't that exactly, but that gets us the right idea for the type of problem we're trying to solve. The spatial distribution for our point cloud was relatively uniform, but it wasn't entirely uniform, and we wanted to uniformize it. Essentially, we wanted to rasterize this point cloud to a set of uniform voxels that had the right material tagged on it. And you can kind of see what that looks like here on the right. If you're in the back, it might be a little hard, but this is a bunch of uniform voxels, and they each are colored based on what material composes them. And I want to note that this is non-trivial to do. Since the particles aren't distributed uniformly, a single voxel might contain multiple points, it might contain no points, it might contain only one, we just don't know. So to solve this, we use a Voronoi tiling to determine how much of each particle should be in each voxel. And this is like a relatively standard approach for doing this sort of thing. Here you can see I have a kind of graphic that I made for this. Please appreciate it. I spent way too much time on it. Thank you. It means so much. And here we can see the points from our original point cloud here. So we have one in green, one in yellow, one in red. And then the shaded region around each point corresponds to the Voronoi tiling for each point. So it's the region of space that is closest to that point. And then superimposed on that, I've shown this white grid, which represents the uniform voxels that we're trying to rasterize to. This diagram is in 2 dimensions, but the actual thing was in 3 dimensions. I'm showing it in 2 dimensions because it's easier to understand. Just know that in the real thing, we were doing it, you just do it a third time for the 3rd dimension. The way that the algorithm works is that we check each corner of every voxel to find the nearest point in the point cloud. So for example, if we look at this second voxel here, we take these 4 corners, again in 3D it would be 8, but here it's only 4 corners, we see that each corner is closest to this green point and we mark them as green. If all of the corners of a voxel are the same, then we can map the point and terminate. We can say, okay, all of these are closest to green, this whole voxel can be green, we are good. For another example, we can look at the next block, in the case where they're not all the same. So here we have the same thing, we have our block, we look at our 4 corners, and after we've looked at all 4 of them, we see that 3 of them are green and 1 of them is yellow. The entire thing is not all the same, so in this case, we recursively split into subvoxels and then we check the corners again. Again, normally it would be 8, but here we're recursively splitting into 4 subvoxels. And then each subvoxel has its corners checked. This keeps going until either we reach a subvoxel where all of the corners are the same, like we saw in the first case, or we reach a recursion limit. There is a limit to this, both so that we can keep some reasonable boundaries on the performance and also to avoid infinite recursion with degenerate cases. But you can see here, these 3 voxels all have green corners, so all of these 3 subvoxels become green. This one is still mixed, so it might keep splitting, or it might stop if we reach the recursion limit. And as you keep doing this, the points that you have checked at each of these corners will slowly approach the true ratio of the contents of the voxel. So that's great and all. But there's something here that I want to point out. These original corners get checked twice in the algorithm. We check them one when we do the first step, and then when we recurse down, we check them all again because they share the exact same geometry because they're covering the same space. And because of how it was written, this ran all of these checks again. And these checks are expensive. You have to find a nearest neighbor point, so that's a BVH traversal, that's a big O of log n. And in the actual problem, there were several other things we had to check as well. There were a couple boundary conditions that we had to look for that also took a very long time to calculate. And the performance of this mattered for the case that we were doing this. So I saw this, I saw that these were being done, and what an easy opportunity for optimization, I thought, at the time. We'll just make a cache of all of the points that we've checked so far, and you can see kind of a rusty example of this. We make a hash map, we're starting with our points. These are F64 triples representing the point in space, and then we can map that into the fill that we've computed for that voxel. We can say this one's green, this one's red, what have you. And then I kind of lied over some details here, but when we get there, you take the point and then you try to insert it into your cache once you've computed the value, and then later we can look it up in the cache, and if it's available in the cache, we can skip recomputing it, and we can just get the value from the cache instead of computing it all over again. So this is great. So you code this up and you try to do this, and then the Rust compiler yells at you. It says that you're not allowed to do this. It says that you can't insert the point because F64 doesn't satisfy eq or hash. The trait bounds are unsatisfied. So if you're me, you go to Google the problem, fully expecting that you're going to copy-paste the first solution you find on Stack Overflow. That's certainly what I do whenever I encounter a programming problem that I don't know how to solve. I look it up and I try to copy-paste the first thing that I find. So you do this, you go to Google, and then Stack Overflow yells at you. Stack Overflow also tells you that you shouldn't do this and that this is a terrible idea and this is horribly unstable and you probably don't want to do this. But why? Why can't you hash floats? Why won't it let you? Before we get too deep into this, I want to note that as engineers, I think it's good for us to ask these kinds of questions. Who knows? You could be the genius that proves everybody wrong. More likely, you will learn that everybody else was right and that you were the one that was wrong, but that's still a valuable experience. It helps us learn. It makes us better engineers. So why? To answer this question, we should first learn a little bit more about floating point itself. So what is a floating point anyway? I assume there's probably some people in the audience that are already familiar with this, but for those of us that aren't, when I was in college, I learned that floating point is a primitive type that's used for fractional numbers and also very large numbers, which the integer types can't handle. So you can do like 0.5, which is obviously not an integer, but you could also do like 15 billion, which is beyond the range of most integers. This is true, but it's also a simplification, i.e. a lie. So today we're going to go a little bit deeper. For our purposes today, a floating point is this. If you look into an F32, if you break it open and you look inside and look at all of the bits that are inside of it, this is what you get. And you see that it's split into 3 parts. There's a sign component, an exponent, and then a fractional component. You may have heard that floating point works a lot like scientific notation, which is true, except it's in binary. So the way that these 3 sections are interpreted is like scientific notation, but for binary. The sign bit here is just indicating whether it's positive or negative. In this case, a sign of 0 indicates a positive number. Then we take the fractional portion and we say 1 point that fractional portion in binary. And then we multiply it by 10, but this is 10 base 2, so it's actually 2 in base 10. And we raise that to the power of the exponent, interpreted as a signed integer. In a format that we're more familiar with, it looks like this. So if you look at it in base 10, 1.01000 is 1.25 base 10, times 2 base 10, 10 base 2 is 2 base 10, raised to the power of -3, and if you do the math, that results in this. Congratulations, we've made a floating point. With this understanding, we can start to see some problems with hashing. Problem the first, inherent precision loss. There's only 32 bits that we have available here, but we're trying to represent every real number. That means that many numbers, uncountably infinitely many numbers as a matter of fact, can only be represented approximately. You can't get them perfect. And this is unintuitive. Can anybody tell me what this code outputs? I warned you there would be audience participation. We're taking the number 16,777,214 as an F32, and we're just going up by ones each time and printing each one out as we go. So, and I'll give you a hint, this is a trick question. Who thinks they have an answer? Who wants to try? Yeah, you. Go.
So the first 3 lines will output what we would expect. The last line will output what we would expect. But the second to last line, the 17, will be truncated towards down. So it will output 16 instead of 17.
That's amazing. Huge congratulations. That's truly incredible, because this is insane. Absolutely. This is ridiculous. Most people would not know this. I did not know this before I made these slides. Why is this one wrong, but all of the other ones are right? There is a reason for this. I can explain to you the reason for this, but I'm not going to. We're moving on. So that's a problem. This is our list of problems, and we're going to build up this list as we go. But that's one problem. We found one so far. Not every number can be represented exactly, and it's not intuitive as to which ones can and which ones can't. Unless you know exactly what you're looking for, all of those integers look the same to most people. And this can cause issues for hashing. When you're trying to hash a floating point value, it's very easy to hash one number, but actually hash something else. You might think that you're hashing that 217, but the internal representation is actually slightly different. And I know what you're thinking, but don't worry. It gets worse because of drift and error. You see, this limitation on precision is baked into the format itself. This means that every single intermediate value in every mathematical expression is susceptible to this kind of problem anytime you do math with floats. And here's an example of that, and I won't make you guess it because you have no chance. Here we're taking pi, an approximation of pi, and then we add Euler's constant, and then we subtract it again. Mathematically, this operation is the identity. We're taking a number, we're adding another number, and then we're subtracting it again. We should end up exactly where we started, but we don't. You can see that our value ended in 2.5 and now it ends in 2.7. It's actually drifted very slightly from where it began, even though we should have ended up right where we were at the beginning. And to make matters worse, this error can accumulate arbitrarily. Given a long enough mathematical expression, there is no bound on how far your values can drift from where they started. And this has even been used on purpose for some computational clownery. You can see Gradient Half Decent by Tom Seven for an example of that. Very good stuff. Here's another example. Here we're taking 0.1 and we're adding 0.2. Does anybody want to try to tell me what this code outputs? And I'll give you a hint. This is a trick question. That's a really great answer. It's still wrong, though. I'm very sorry. This should actually come as extremely surprising to people who are familiar with floating point, because 0.1 plus 0.2 is a classic example of floating point being wrong. This post on Stack Overflow has 4,000 upvotes. It's a classic problem. You take 0.1 and 0.2, and many people would expect you get 0.3000004. There is even a website dedicated to this problem because of how famous it is. But here we look and it gets 0.3. What gives? What's the deal with this? Did I lie to you? No, the answer is that we're using F32. The classic 0.3000004 error only shows up on F64. It only shows up on double precision floating point. On single precision floating point, it at least appears to be much more correct. Remember when I told you this stuff was unintuitive? I wasn't kidding. So that's another problem. Doing math with our values can pollute them permanently, as we saw in the first example. And as we saw in the second example, the behavior behind how this pollution works is extremely unintuitive, even to people who are familiar with floating point. And, to make matters worse, this error can accumulate arbitrarily. Thinking back to our original problem, this causes a lot of issues for hashing. You can have two mathematical expressions that should provide the exact same output, but they end up being slightly different because of floating point drift. This makes it extremely easy to end up hashing two different values that you think are the same, that should be the same. That's very bad. But I know what you're thinking. Don't worry, it gets worse because of NaN. remember those edge cases from earlier? When I was going over how floating point works, there was actually several edge cases that I glossed over, and it's time to talk about them now. One of those edge cases is NaN. NaN stands for not a number, and it's a special value which is built into the floating point format itself to handle errors. Invalid operations will result in a NaN value instead of throwing an exception, though that also happens too sometimes. So, for example, here we can see some NaN error handling. We can take 0 divided by 0, which is a mathematically invalid operation. You can't divide 0 by 0, and so we get a NaN output as the first one. And then also basically any operation that involves NaN itself is also going to result in a NaN. So if you take NaN and you multiply it by 100, you also get NaN. Great. As another example, we could take 100 and divide it by 0. Division by 0 is mathematically invalid, and so that should result in a NaN, which as you can see, it does. Not just kidding. I guess floating point knows better than me. My bad. I can also explain this, but I'm not going to. So when you look inside and look at what a NaN is, this is what they actually look like. Any floating point value whose bits follow this pattern is interpreted as NaN. If you remember from a handful of slides ago, this is having the exponent portion be entirely ones, and then everything else is stars, wildcards. And you see, note the wildcards, because there are so many of them, NaN is not a single value. There are billions of different NaN values because there are billions of different combinations for all of those different wildcards. The reason this was done was so that the NaN can encode information about what produced the error. So the 0 divided by 0 NaN that we saw might have one particular set of bits, whereas the NaN times 100 NaN that we saw might have a different set of bits. How would you even hash that? A simple solution maybe is to try to work out what the error was, a simple solution maybe is to try to hash all NaNs the same. We say, okay, they're all errors, so we'll just say that every NaN is hashed identically. Except, you can't do that, because NaN is not equal to itself by the original floating point standard. This snippet of text is from IEEE 754, which is the RFC that defines how floating point works, and it says that NaN is always unequal to itself, and it's always non-ordered with respect to itself and every other floating point value. Even if you have two NaN values, which are bit for bit identical, they are still considered non-equal. And you can see that borne out in the Rust here. NaN equals NaN, false. As a bonus fun fact, if you actually try to do this in Rust, the compiler yells at you because this is not a valid way to compare NaNs. As a doubly bonus fun fact, I'm pretty sure this is the actual reason why eq, ord, and hash aren't implemented for floats in the standard library. Because NaN is not equal to itself, because NaN is not equal to itself, you cannot create a mathematically consistent definition for any of these traits. So, that didn't work, but maybe there's still a way? NaNs are encoding error information, so perhaps we could try to figure out which error the NaN is indicating, and then we hash based on that, similar to what we might be familiar with a result, where different error variants could all get different hashes. That should work, right? Wrong. You can't do that either. Again, in the original definition, we can see here that the exact bits that are encoded is left to the implementer's discretion. Which bit strings correspond to which errors, and even which errors are encoded at all, is left undefined by the IEEE standard. Different chip manufacturers are left to do this however they wish. So if you try to hash exact bit values, you will get different behavior on different platforms. That's really bad. NaN really throws a wrench in things because of all of the edge cases in its definition. And that's not even including all of the other stuff that I cut for time. Things like transcendental functions, the fact that absolute accuracy goes down as you get further away from 0, the fact that LLVM can optimize out certain operations, further obfuscating which operations are occurring to your numbers, value casting, the special case infinity values, the fact that floating point has both positive and negative 0, and these are definitionally equal to each other despite having different bit strings, subnormal values, all of these things cause problems for hashing. There is no sensible hash implementation for floating point. You cannot do it. But what are they gonna do, huh? Take me to floating point jail? What's the worst that could happen? As my coworker pointed out when I originally gave this talk at work, the standard library provides this 2-bits function. We can just use it. And we do have some advantages here. Let's think back to our original problem. We're only trying to implement a cache here. We're not trying to make a general purpose hashing system. This is kind of a big deal. We only want to look up values that we've already computed. In a cache, false negatives are inefficient, but they don't result in any incorrect values. Suppose, for example, that we have some point in space, point A, and we hash it twice. But for some reason, we get 2 different values. For all of the myriad reasons that we've discussed, when we hash at point A the first time, we get 1 hash, but when we hash point A the second time, we get a different hash. The second hash will miss the cache, but that's fine. We'll end up recomputing the value unnecessarily, but the only thing we've lost is wasted time. This means that overly conservative hashing, while it leaves money on the table, it is safe to do in general. This is a huge win. It doesn't solve all of our numerical stability problems, but it does give us a lot of slack that we can work with. Okay, great, but what about all that NaN nonsense? As it turns out, we have a handful of advantages here as well. Because of our problem domain, NaN doesn't really matter. We're working with real engineering data here, mostly measurements that are from an actual site that were measured by an actual human. NaN should never occur. Even if it did, our system would already be hosed. We're doing a bunch of other math, and all of that other math that we're doing can't properly handle a NaN value either, so any weird NaN behavior that's introduced from the hashing system is no worse than anything that we're already doing. Garbage in, garbage out. So maybe there's a way. We don't need to worry about the false negatives, where the same value gets 2 different hashes, and we don't really need to worry about the weird values either. So what about false positives, where 2 different values end up getting the same hash? This could occur if you have 2 values that drifted into each other, converging on the same incorrect value. Well, there may be a way to handle this. We know the devil. We know our problem domain very well. We're specifically trying to rasterize these non-uniform points, and that means we can make some assumptions about our data. Based on the scan area, we can put an upper bound on the total size of our point cloud. Again, thinking about scanning river banks, we're dealing with a data set that's not going to be kilometers wide, we're dealing with something that's meters wide. Very unlikely it would ever be more than, say, a few hundred meters. We can assume, for example, that all of the voxels that are coming into our function are a uniform 1 by 1 by 1 cube, which was true in the original problem and is true in the toy example here as well. We know that the recursion depth of our function is bounded, which means that we know that our subvoxels can only get so small before we give up and terminate, and so on, and so on. All of this means we can get some pretty accurate bounds on the scale and distribution of our data. Additionally, we know what math is happening to those numbers. And all of that means we can get some reasonable bounds on the error of our numbers. If we can bound the accuracy of our values, we can be pretty confident that we're not going to get any false positives on our cache, which means we did it. And that means we can look at the actual implementation that I wrote. This isn't the literal implementation, this is a slightly simplified version, but it's essentially the same idea. It's a little bit complicated here because we're doing a bit of bit magic to perform a ULPS comparison. I can talk about that if people are interested, but if not, I'm going to kind of just gloss over that for time. The important takeaway, though, is that we're treating a small neighborhood of consecutive floating point values as being identical for the purposes of hashing. In this case, it's every 4 consecutive values. This is done on purpose. The idea is that we want to be a little bit fuzzy in order to handle errors and to reduce the number of false negatives, but we don't want to be so fuzzy that we then start getting false positives. And I did a bit of math to try to come up with a reasonable boundary here. And given the boundary on the accuracy of our data, we can do this with some reasonable safety. And that's about it. Dear Princess Celestia, today I learned that floating point hashing is bad and you should not do it, that even if you think you know what you're doing, you probably don't, but sometimes, if you can put enough constraints on your problems, you can justify it and you can do it safely. What a nice talk. Do you buy it? Because I'm not sure that I buy it. Looking at this code again after the lapse of almost a year, over a year, there's actually a couple of things that I missed. Can you spot the errors at home? I won't make you shout it out because we're starting to run up on time. The main thing that I noticed was that I didn't really account for arbitrary error accumulation properly when I wrote it back then, and I also didn't really account for subnormals. I can get into this if people are curious, but I'm going to keep moving. Knowing what I know now, I could probably justify that all of these issues are actually fine. I still stand by the hash implementation that I wrote. I don't think that there is a problem with the code. I think the problem was in my proof. And that's not great. I probably could justify some of these things, but when I wrote it, I didn't properly justify them, and I really should have. So let's try that conclusion again. Dear Princess Celestia, today I learned that we don't know the devil, and you should be afraid of floating point, because even if you think you know what you're doing, you probably don't. Thank you very much for your time.
Thank you so much, Rose. That was lovely. Do we have any questions in the audience? Do you want to run around over there?
Perfect.
So you only showed the hash implementation, but what about the equals implementation?
That's a great question. The EEC implementation, I can actually go, the slides are gone, that's fine. The EEC implementation was done very similarly. It also used the same ULPS trick, but essentially it was done the same way where a small neighborhood of floating point values would all get truncated into the same one, and then you would compare exact bit equality on those. So essentially, if they were hashed the same, then they are equals each other, and if they're not hashed the same, they're not equals each other. And I think that might actually be a requirement in the hash trait that it needs to be consistent with EEC. But yes, that is how I did it.
Thank you.
Any other questions?
Okay.
I see something over there. Can we throw?
I'm not particularly excited about throwing.
So, great
but
talk.
It's made for throwing. Nobody will get hurt.
So, great talk, thanks. I noticed in the hash implementation that after converting to the bits, you hashed an array instead of a tuple. Was there some specific reason for that, or was it just random?
No, it was just random.
Okay, thanks.
There is no particular reason behind the array.
You only need to check, you're only checking the points on the corners of the raster.
Yes.
And then maybe a smaller raster and a smaller raster, but up to a limit. So why don't you just convert or treat the raster as an integer grid and hash
That's
those?
such a good point. You're extremely correct, as a matter of fact. So when I gave this talk originally at my company, somebody at work asked me essentially that exact same question, and they were very polite about it, as you have been. And I, with some embarrassment, admitted that, well, I didn't really think of it at the time, so I didn't do it. But that is the way that it should be handled. I put a link to my blog on there for shilling purposes. On there, I actually have an addendum post. I post a blog post with a bunch of extra bonus stuff that I couldn't fit into this talk, and that is one of them that I talk about, but I'll briefly go over it here. The point that's being made, because you know the exact spacing of all of the subvoxeling that you're doing, you could actually create a uniform integer grid and then use that. And this is exactly how this should be done. If I were to rewrite it today, I would not write a hash implementation, and I wouldn't use floating point at all. I would use a regular integer grid, and I would evaluate it on that grid. And then you can maintain a cache, and because integer math is entirely deterministic, including across platforms, you're totally fine. So very good point. Yes, you should do that. Don't do what I did.
All right, let's have a final question.
I think it's a very similar question, but the question is also, can we convince people in industry not to use floating point when capturing data?
I've tried. I have tried, but I don't think so. That being said, I don't think it's terrible. I talk about this in the blog post a little bit as well, but for real-world engineering data, I don't think it's a bad format. There's a ton of trade-offs that were made, and if you read through the whole RFC, you can really feel the trade-offs being made. Things about relative accuracy preservation, things about being able to handle different orders of magnitude. I think that for real engineering data, it's not a bad format. And as we kind of saw in the talk, a lot of its quirks sort of just come out in the wash when you're using it for its original intended purpose. That being said, I don't think we can convince industry, even if maybe we should. And as somebody who does build industry software, they mentioned I do write CAD software for a living. I'm generally of the opinion that fixed precision systems are usually better if you can, because if you know what domain you're working in, you can usually make a pretty reasonable guess at what precision you need to be working in. Going back to the riverbanks example, if you're looking about spatial data that's on the scale of a riverbank, you can be pretty confident that anything you're working with doesn't need anything more than, say, micrometer precision. That if you're precise down to a micrometer, any user would be happy with that, even if you, sorry, even if you don't have perfect relative precision all the way down to the subnormals.
All right. There were a few more questions. I think you can find Rose around.
I'll be around. Maybe out in the hallway. I don't know.
Thank you so much. Let's give it up for Rose.
Thank you.
All right, we're now going into a break. It will be a 40 minutes break until 11:40, after which we'll have Rafe Levine here. You can get Ferris glitter tattoos downstairs if you want.
So I'm
Isn't
gonna
that
slowly
amazing?
work my way up towards getting a real one.
Exactly. Also, there was just a question asked on Discord about the Wi-Fi. There is Wi-Fi. It's on the back of your badge. That's the SSID and the password.
Right there.
Have a nice break, everybody.
Yeah, we're back at 11:40. Check, check. Ha. Hey, welcome back, everybody. I hope you enjoyed your break. Let's see. This event wouldn't be possible without sponsors. We got some great sponsors, and I particularly want to thank the diamond sponsors, JetBrains and AWS, for making this possible. For JetBrains, they have a booth downstairs. Go visit it. It's super interesting. With regards to GoSim, in the middle of the restaurant area, there's actually a little elevated bit where you can walk up the stairs. And that's where you can find all of the GoSim people. So go and have a look if you haven't noticed that. The elevated area in the middle of the restaurant bit. And lastly, GoSim, they also sponsored a specialty coffee in the back, which I haven't found myself yet.
There was a long line for it. I
Yeah,
saw,
exactly. Yeah, and the same with the glitter tattoo. So I didn't get a tattoo yet because the queue was too long. But maybe I'll sneak out now. You know, after
but you should all get it in the break because an exciting talk is coming up, of course.
Exactly.
We all need to stay here and then get glitter tattoos after. Next
No,
up,
I'm talking about me personally.
Yeah, okay. Well, you can get your glitter tattoo.
Audience,
yeah, of
no, not
course,
the
yeah.
audience, no.
Right. So next up is Rafe Levine. He is on the Google Fonts team and specifically working on GPU font rendering. He's launched the Pull Down CMark project, which has now been given to the community, and a large community is actually building on that. And you've been working on many things, Velo, Xylem. Last year you talked about Xylem at Rustenel, and now you're going to talk about Velo. You've just been recompiling your slides to make page down work, I think.
Yeah, we have page down, so, named key, page down.
And I also think that you have a very interesting T-shirt. What does it say?
Yes, with undefined behavior, anything is possible.
We live for that. All right, take it away, Rafe.
Thank you, Terts. All right, so today I'm going to talk about the evolution of Velo to be faster and I think most importantly, easier. I'm glad Terts mentioned Pull Down CMark because this is I do a lot of researchy things, and Pull Down CMark is like one of the few Rust things that I've done that's actually like really in production, and I kind of want to recapitulate that. That I want to make 2D rendering easy and something that people can just reach for and have. So I want to talk a little bit about the current state of the Velo GPU renderer. I think it has a lot of it's research that really advances the state of the art of rendering. But there are definitely challenges. Like if you want to put it into production, then you're going to run into at least one of these challenges. So one of them is that it is based on compute shaders, and compute shaders are a relatively recent feature. It's hard to know for sure whether your GPU is going to support that. And certainly if you want to deploy your app on WebGL, you do not have compute shaders. Another challenge that people have run into is the memory usage, that the default configuration is quite a bit of memory, and a bigger problem is that it's unpredictable. So if you specify such and such buffer size, and then you have a bigger CAD drawing that you need to bring in that overflows that buffer, then it will fail. And this is one of the things that's really challenging about kind of compute GPU programming. The architecture is based on compute shaders, and most existing renderers, like if you look at Bevy or some other game engine, it's going to not be based on compute shaders, but based on the rasterization pipeline. And so if you want to take the output from Velo and blend that into your renderer, it's not that easy to do. There's some performance cliffs, like if you zoom way in or zoom way out, then the performance falls down. And just generally, like it's a difficult code base to get into. So those are the challenges that we want to address with this new work, this evolution. The key advance, the kind of technological advance, is this idea called sparse strips. And sparse strips is both a representation of the rendered path that you get, and it's also the algorithm for rendering that path. And so the idea, a sparse strip is geometry that has fixed height. We're experimenting with both 4 or 8 pixels for the height, and then the width is variable. And so it's an efficient representation of the rendered path. The idea is that it takes fairly minimal memory usage, and also a fairly small number of primitives to render, because when you bring this to the GPU, then there's a cost per primitive, and it's efficient to calculate. So there's a wall of text here. I'm not going to walk through that. I will show you with an animation that I've been working on. So let's say we want to render this shape. We want to render this R, and it has a mixture of line segments and curve segments, Bezier curves. So the first step in the pipeline is that we will take the curve segments and flatten them to lines with some tolerance, adjustable tolerance, obviously. So you tune it so that it's, you don't see it visually. So now we have the shape entirely made out of line segments. The next step in the pipeline is that we are going to divide it into tiles. And here a tile is going to be, we're going to use 4x4 for the tiles here. And so we put a grid over the line segments. And then the next step is to generate tiles from that, for each line segment in the shape. We're going to identify which tiles are covered by that line. And for each tile that it covers, we're going to generate an element in this tile array that has the x and y coordinate of which tile it came from, and also the clipped geometry of that line. So now that we have all of the tiles to render this shape, the next thing that we're going to do is sort. And this is actually just regular call to sort unstable is good enough for the ordering guarantees. And so now these are sorted by in scanline order. So there's an XY coordinate, and those just increase for the tiles in the shape. And that sorting, that's really one of the critical things. That solves a lot of problems for us. And in particular, all of the tile segments that are in the same geometry, in the same tile location in the original, are now a contiguous slice. So we're going to take those contiguous slices, identify them, and merge them. So for each merged tile, we now have a slice of the tiles. Now that we have the merged tiles, that contains all of the information that we need to render the pixels. So we're going to take that merged tile and just compute a 4x4 grid of alpha values. And that's a fairly simple calculation. We're just computing the percent area of each pixel within that tile that is covered by the line segments in that merged tile. It's about 90 lines of code. It's not an incredibly complicated calculation. So now we have the rendered pixels for each of the merged tiles, and the next step in the process is to organize those into strips. So this is the sparse strip idea. Now we're seeing the strips from the sparse strip idea. And so each one of these strips is going to become a quad that is sent to the GPU. And again, the reason for combining these into strips is to reduce the number of quads that need to be rendered. We could send each tile individually, but that would be a lot more tiles. And we want to make the GPU computation as efficient as possible. So we organize into strips, and then we send them to the GPU to get rendered in the XY location. And there we have it. There's also, I didn't animate this, there's also this question of filling in the sparse fills, the areas that don't have alpha values, but that's just filling a solid rectangle, which is like the simplest and most efficient thing that you could possibly do on a GPU. So that's the central engine behind this algorithm. And I was doing experiments late last year of doing a CPU implementation of this kind of as an intermediate step towards, okay, we want to get this running on the GPU, get it faster. But what I found is that running this on the CPU is really fast. Like it is, I think the experiments that I was doing showed it about 2.5 times faster than TinySkia, which is very efficient. TinySkia is very good code. We drew a lot of inspiration from it. And it's also faster than Skia software. It's faster than renderers that are in production. So there's a spectrum. There's like many different modes that will be shipping this sparse strip idea. And one of them is a purely CPU implementation. And so that's very portable. It'll run essentially everywhere. It's no STID. And it's a small, simple code base. So if you are on a server and you don't want to deal with getting your GPU configured, then you can just call into Velo CPU and have a pretty good performance renderer without any of the difficulty of the GPU infrastructure. And one of the reasons why we're getting good performance, I'll talk a little bit more about this later, is SIMD optimization, the ability to use that parallelism at the CPU level. Now, of course, CPU-only rendering, there's a speed limit. Like, you do not want to do the pixels on the CPU if you have a possibility of computing the pixels on the GPU. It's order of magnitude more throughput. So the mode that I'm really focusing on today is the Velo hybrid mode, which basically says that you do your geometry and your scheduling, you do that sort on the CPU on tiles, so you're not doing the per pixel work on the CPU, you do all of the per pixel work on the GPU. So you do this tiling, you upload that work, it gets evaluated on the GPU. Right now, we're doing the alpha values also on CPU, but the next step soon is to move that work to a compute shader as well. And then the fully GPU-driven mode, we want to get there, but that's an open research topic. There are many, many difficult problems that you have to solve to really get this, memory efficient and so on and so forth. And so this is going to be work going forward. So for today, we're focusing on the Velo hybrid mode, where you have this mix of CPU and GPU. So the performance philosophy is that as opposed to the Velo that you might have seen a year or two ago, that we are moving some of the allocation and scheduling work to the CPU just because of how difficult it is to get that fully GPU driven, and then do all of the per pixel calculation on the GPU, really focus on SIMD and eventually multi-threading for the CPU work, so we can take advantage of as much parallelism as possible on the CPU. A really important direction for performance is caching. So this depends on your application. If you have a fully dynamic scene, then caching is not very important. But if you want to render a UI, then all of those glyphs are cacheable, and so you don't want to keep re-rendering them. And then, given that we have the CPU to do the scheduling and allocation work, once we decide what work needs to be done, we want to move that to the GPU so that that work is as efficient as possible. So it's sparse. We want to avoid any unneeded work. Like if there's a region that doesn't have any coverage, then you don't want to do any work at all. And then this is a more technical thing that we want to minimize the barriers, because a lot of times if you have a lot of draw calls and you have pipeline dependencies, then that can be a slowdown. And so this is a real goal, is to pack as much as possible into a draw call so that the number of barriers is minimized. And a really important part in terms of putting this into production is that we are using bounded memory on the GPU, no matter how complex the scene gets. If you overflow a buffer, then you issue the draw call, and you do as much as possible within a draw call, issue that draw call, and then go to the next draw call to do the rest of the scene. So you don't have unbounded memory usage. So as I say, path caching is a really important part. This is not actually implemented yet. This is part of the plan. But to avoid the dynamic rendering of all paths, when you have that path already rendered, you use that sparse strip representation, which is very memory efficient, especially as you're, like if you have glyphs, like the classic glyph atlas really only works for small glyphs, because if you have a large glyph, you have so much area, it's n squared, but the sparse strip representation is linear. We also can avoid a little bit of complexity because the layout of the alpha values is linear, so you don't have to do this 2D allocation in a glyph atlas. Yeah, so this really is showing you that efficient scaling, that if you have a small glyph, then it's really dense. You don't get any value out of the sparseness. But on the other hand, it's very efficient on the GPU because rendering these strips is essentially as fast as if you were rendering a single quad out of a glyph atlas. You've got a little bit more vertex work, but on the other hand, you're saving in fragment work because any coverage that is not that's not actually covered by the glyph, then you don't even schedule those fragment shaders. Then as your glyph gets larger, then you really get a tremendous amount of advantage from the sparseness, because you're really only storing the alpha values on the edge of the glyph, and those large regions that are empty, or those large regions that are completely filled don't take any memory. So another optimization that this is actually landed in, well, it's fully landed in the CPU, and there's a PR in flight for it to land in hybrid, is clip optimization. So let's say that we have some simple shape that we're using to clip some contents, in this case text. And so this is one of the things you have to do in a 2D renderer. It's not like, this is different than 3D rendering, where you pretty much just painter's algorithm and draw the things. Sometimes you have these trees, you can have nested clips, and so it can get quite complicated. And this is challenging. Like Tiny Skia will composite all of the, it'll draw the inner contents, and it'll draw the mask, and then it'll composite everything. And that is a real performance problem. So we want to optimize this. Again, the philosophy of making the GPU work as efficient as possible. So we classify every tile in the clip path into basically 3 possibilities. So if you're in the interior of the clip, then you just draw. You just do the same drawing of the interior contents without doing any special processing for the clip at all. If you have nothing to draw, or if you have no clip path, then you don't schedule any work to the GPU. You don't need to draw any pixels, so don't draw anything. And then for the third classification, for the things that actually have some alpha values in the mask, then you do compositing. You render the mask, you render the interior content, and you do a compositing operation on those tiles, right? So I think that clip optimization, I think this is one of the reasons why we will expect really world-class performance from this renderer. And so there's those tiles to composite. There's an intermediate buffer that needs to store those rendered, the rendered content that you'll be clipping. And this is a challenging thing. So the idea here is what I call spatiotemporal allocation. So this is rendered kind of abstractly, where each of those nodes in the tree is representing some kind of compositing operation, maybe a clip compositing where you take the mask and composite it with the content, or maybe a blend, maybe something like hard light. Like all of that uses the same infrastructure, where you need to have some intermediate texture representation and then do some work based on that. So if you have abundant memory, then you do all of the individual elements that needed to be composited in parallel. But of course, you've got data dependencies, so you need to schedule multiple draw calls to get those dependencies resolved. If you have tight memory, on the other hand, if you're working in a bounded buffer space, then maybe you don't have space for all of those tiles, and so you are going to spatiotemporally allocate those. You're going to move those out in time so that each individual draw call is going to be only needing a bounded number of tiles. Great. All right, so again, parallelism is the name of the game. This comes from GPU land, where you have massive parallelism, where like if you are not able to express your problem in at least 10,000 threads, you're not using the hardware. On a CPU, you don't have tens of thousands of threads, but you may have a dozen. So all of the early pipeline stages up to coarse rasterization are fully parallel by draw object. So you render all of the paths. They're all completely independent of each other. There's no need to serialize that. So you can effectively just put those out to Rayon and have them all rendered in parallel. Then there's this coarse rasterization step. Currently, this is taking, like for some of our tests, it's taking like 2% of the total time. So this is potentially your serial bottleneck, but it's fast. And it's a relatively simple calculation per tile, per one of those wide tiles. That's not a 4x4 tile, that's about 1,000 pixels. And then lastly, on the CPU, you have this fine rasterization step, and again, that's fully parallel. That once you've done the coarse rasterization, there's no dependencies from one tile to another, so you can just farm those out to all the cores on your computer. And of course, if it's a GPU, then you're using those tens of thousands of threads that are available. And one of the things that we've been exploring more and more is that for the stages of the computation that are on the CPU, you really want to use SIMD. So again, coming from GPU land, there's this massive amount of parallelism that's available. Why not exploit that parallelism by using the SIMD lanes on your chip? SIMD is single instruction multiple data, and it basically it's on all modern computers these days. And the idea is that instead of just saying, multiply two numbers together, you can say, here's a vector of 16 numbers, multiply all of them together, and that happens in one clock cycle just as fast as the scalar. So it's a really significant increase in throughput compared with being able to do just scalar computations. And we've been finding, again, coming from GPU land, that we can use the SIMD for all of the stages of the pipeline that are performance critical. The flattening, the tiling, the rendering of those alpha values, as long as those are going to be on the CPU, and then the fine rasterization, the per pixel. Also, you can really exploit that SIMD parallelism. One of the things that I have been particularly excited about is Neon FP16. So this is, one of the nice things about AI is that people start to care a little bit more about these smaller data types. And FP16, you can get twice the bandwidth, twice the throughput as if you're using 32-bit floats. And so that's particularly important on things like Apple Silicon and also Android phones. Those generally have this 16-bit capability. One of the challenges is that my experiments, I am writing that in assembly code because Rust doesn't really have support for FP16 SIMD yet. So one of the things that I am hoping to do this week is to talk to people on the compiler team, Rust project, who are working on SIMD, because I have a lot of ideas about how we should do this. So if you're working on SIMD, let's talk. Okay, so this project, the community aspect of this project is, to me, it's really been incredibly gratifying. The team has come together. We have 3 people. Taj and Alex are here from Canva today. Actually, let's see. Taj, Alex, Laura, Tom, Daniel, and Nico are here. So you'll be able to meet most of the team. And in addition, Lorenz Stampfel from ETH Zurich, he is doing his master's degree on the CPU version and basically exploring how far can we get on the speed up of the CPU version. And then also Tom Churchman has been working independently. Daniel is funded by Google Fonts, part of Linebinder organization. And Nico Burns, who's also here, is on the Blitz project, which is part of Dioxys and driving a lot of the Blitz use cases. We have renderer office hours every Wednesday. There's also transcripts of those available if you want to read that. And I really want to recommend, come to the Linebinder community for learning and building some of this infrastructure. I think I'll show a demo of Blitz here. This is using, all these demos came together just in the last week, in fact. And so Blitz is essentially a small fragment of a web browser that's really designed to render applications, but it can render web pages. So here we are rendering rustlang.org. And it is, it's not complete. It doesn't have complete rendering fidelity, but it gets a lot of stuff on the screen. And this is using CPU, by the way. This is perfectly good, perfectly usable, dynamically rendering all of the glyphs. Like by the time we're done with the performance optimizations, even on CPU, it's going to be quite usable. And of course, when we move the pixel rendering to the GPU, it'll be really fast. Another demo that I found is Josh Camo's page on CSS shadows. We do implement these blurred rounded rectangles. That's one of the rendering primitives. And so that's part of the imaging model. Let's see. So I have a little demo on the, let's see, this is RunWasm WebGL. All right, here we go. Okay, this is Velo Hybrid. This is a relatively simple demo. It's just a SVG renderer. rendering the standard Tiger image, which is sort of hello world of vector. So this is running in the hybrid mode. So the pixel rendering is all being done on the GPU. And then I have, let's see if this works. I have a demo of this running in WebGL. So this is running without compute shaders in WASM. Let's see here. That's my Chrome window. Do I have to exit? Make this work. There we go. And so there's your GoScript Tiger running with WebGL. So we run on down-level GPUs. All right. Great. So current status. So we just did a release late last week of Velo CPU 0.0.1. It's still, I would consider, alpha quality, but you can absolutely get started on this. It has Lawrence has been doing incredible work on this. And so the imaging model includes now gradients. The gradients, you can specify the color space using the color crate. It supports images, different interpolation modes, clips, blends, blurred rounded rectangles. The text supports variable fonts, hinting, and also both color v1 and bitmap emoji. And so I actually think that rendering emoji, this is one of the use cases of why you would want to do Velo CPU. If you're rendering these small things, spinning up a GPU infrastructure doesn't make a lot of sense. But if you say, I just want this emoji rendered, then it's a great solution to that problem. Velo CPU is also no-std. When I showed you that Blitz demo, that was going through an any render abstraction so that you can choose like which renderer you want to do. And Velo CPU is one of the supported backends of that abstraction. Velo Hybrid is not quite as far along, but it's in very active development. We're making, the rate of progress is amazing. If we count PRs that are in flight, then we have images and clips. And we have that WebGL2 backend that does not depend on WGPU. So it is a very lightweight dependency. Roadmap, we have, of course, a lot of ambitious stuff we want to do. There's a full roadmap doc that you can go to. We want to really complete the imaging model. It's really almost done for CPU, but really complete it on hybrid. Build a set of image filters for both the CPU and the GPU modes, things like blur and stuff like that. Obviously, we want to do a lot of performance work, including the glyph caching, and then some really advanced things like HDR color and conflation-free compositing for the future. All right, that's my talk. I'll take questions.
Thank you. Thank you so much. Great talk. Are there any questions? In the meantime, I'll apologize for the flickering that was on screen. We'll try to get it fixed. There was a little bit of...
I didn't see it.
We're looking into it. Don't worry. We'll get it fixed. Where is the catch box gone?
Hi.
There we go.
Great talk. Thanks. My question is, why 4x4 tiles, and what are the trade-offs involved in choosing that size?
There's a bunch of Zulip threads on this exact question. So the trade-off, the essential trade-off is the amount of work that you have to do to create those tiles and sort those. So a larger tile will reduce the amount of sorting work. But the other side of that trade-off is that if you have a larger tile, then some of those pixels in those tiles are going to be either all 0 or all 1. So you're doing more work per pixel. There's a much more complicated trade-off. I think we will probably go to an 8x8 tile for most of this, just to reduce, if you've got the GPU doing the alpha rendering, then you probably want the 8x8 tile because the cost of those wasted pixels is much lower, and then you're really focused on the CPU side of getting those tiles sorted, so getting fewer tiles is better. But yeah, ultimately it's an engineering trade-off that you look at the relative costs and then pick the tile size that gives you the highest performance.
All right, next question.
Thanks, I appreciated the talk. You focused a lot on the rendering backend, and the performance seems very impressive, but I was curious what work there is to integrate this with existing Rust UI libraries, and how similar the API actually is to some other library like TinySkia or the things you were listing.
Yeah. So these are both ongoing, ongoing projects. So we are building this for Xylem. I was not able today to show a demo of Xylem rendering with this render, but that's obviously coming soon. In terms of the API, we're actually not completely settled on the API. That one of the things that we're wrestling with is, do we do an abstraction? And Nico's work on any renderer is kind of a snapshot of what that abstraction might look like. Or do we want to expose kind of lower level primitives? And I think ultimately that's going to depend on the application. The API is pretty easy. It's not that different than TinySkia. There are important differences. Like TinySkia, those are immediate mode rendering primitives on a PixMap, and that won't fly if you're on a GPU. And that's actually, like, for example, the thing about compositing and with the clip optimization, that you really need to have more intelligence where you have both the contents and the clip path before you can decide what work is needed. So there's a little bit more batching and stuff like that in the API. It's not exactly the same, but it's pretty easy to use. It's not like really painful. Hope that answers the question.
All right.
So you mentioned that there's currently like hybrid is the most developed, but you're working on doing like a full GPU implementation.
Yeah.
Is the limitation like GPU APIs or hardware features, or is there some aspect to those problems that is like inherently non-GPU friendly? Curious.
Yeah, no, it's a great question, and I have this other blog post called I think I Want a Good Parallel Computer that goes into those. It goes a little deeper into that exact set of questions. So it's not a limitation of parallelism. I can exploit as much parallelism as is available, but there are important limitations in the GPU execution model, right? Where the GPU, the way GPUs generally work today, that you want to submit all of the work up front, and then when you have intermediate buffers, you can't dynamically resize them in the middle of the computation. Though that's just not part of the standard GPU model. So it's really those limitations. But in terms of being able to exploit, tens of thousands, hundreds of thousands of threads, that's not the limitation at all. So I'm hoping to, explore like advanced GPU features like work graphs and stuff like that, which are more dynamic in their ability to schedule work. That's kind of why it's research.
Okay, cool. Thank you.
All right, there's another question over here. You've got the clocks.
Yeah. Where can I buy one of those shirts?
There is if you go to the blog post, I think the blog post is called exactly this, with undefined behavior. There is a T-shirt purchase link, and I think the proceeds go to Amnesty International.
All right, question
Hello.
answered, I think. There's another one over here.
Yeah. So thank you so much for your talk. So my question is, I saw in the GitHub repo that there is like it has a predecessor, right, called Piet, if I'm not mistaken.
Yes.
What would be the main changes between Piet and Velo? Thank you.
Absolutely. So Piet really was designed as an abstraction over the platform rendering capability. So Piet would delegate to Direct 2D or Core Graphics or something like that. So here the focus is really implementing the renderer logic ourselves. Another very important difference is, this is a huge evolution, is that Piet was also delegating to the platform to do text layout. But now we're building, also part of the larger Linebender project, that we're building a really robust production quality text stack. A lot of that infrastructure is being shared with Chrome. So you may have seen some blog post about memory safe font loading in Chrome. That is all the same infrastructure. A lot of that is developed by the Google Fonts team, and obviously we're using that in Linebender. We're dividing the responsibility that text layout is not the responsibility of Velo. You call into Parley to do, or Cosmic Text, we actually give you both choices, to do the text layout, and then Velo renders the glyphs, the emojis, the variable fonts, And so that's a very important distinction, because in Piet it was like, the text layout was actually part of the scope.
There's another question here. Yeah.
Yeah.
Go ahead.
Me first? Okay, hi. Yeah, thank you so much for a great talk. It's amazing. Like you, I am very excited about dynamic work graphs and the shiny feature of dynamic allocations on the GPU and all of that happening. At the same time, it feels far away on something like WebGPU.
Yes.
So is your opinion work graphs are bust, or is there something that one might imagine that ever happens with WebGPU here?
Okay, so that's a deep question. I think work graphs right now are not fully baked. I think a little bit more evolution needs to happen. So how long is that going to take, and how long is that going to take before it's like standardized and available in WebGPU? I can't even start to say. So that really is why we're focusing on these hybrid modes, so that we can get you a renderer. We want to get you a production quality renderer in your hands that you can integrate in your application and use today, and not wait on this kind of advanced research.
Okay, and then let's do the last question here in the front. Sure.
Yeah, so you mentioned sort of comparing to the the text rendering, or sorry, the system rendering for text. I've noticed that there's like pretty widely varying results from different font renderers, depending on what application I'm using. And I'm wondering, is there like a standard way to actually evaluate your rendering and how it looks on a given screen, or is that just kind of...
It's a good question. I don't think there's a standard way of rendering. Obviously, being on the Google Fonts team, text is one of our top priorities, and our goal is to get text rendering quality that is top notch. And which is hard, by the way. So the Skrifa level, the font loading level, now does have hinting and auto hinting. That is actually, the auto hinting is exact match for free type, which is very high quality. That's all work by Chad Brokaw. The other challenge that we don't do yet is the subpixel RGB rendering. This is also planned, but I'm not going to promise when that's available. So, our goal is to have the absolute top tier of text rendering quality, and we will get there.
Nice. That's a very good last question and a very nice answer. Thank you very much, Ralph Levine. Okay, now we're going to have a couple minutes break, so to do like the transition from one laptop to another. And the next presentation will be in 5 minutes. They'll also give people an opportunity to sort of leave the room, other people to get in time for the next presentation to start. Doen? I do the intro? I'm all set. You want to start? Sure. Let's go for it. Let's go for it.
Right. Hello. Welcome back, everyone.
Yeah, welcome back. So we
Please
want to
take your seat.
introduce Shane Carr, right?
Well, first, so the flickering might continue for a little bit. We're sorry. Maybe it's gone. Who knows? We might get lucky. Software is magic, right? And hardware
Yeah,
too.
but this could be hardware. It could be
It
like
could
a
be
broken
hardware,
cable,
that is-
something like that. You know, it's yeah. So actually, troubleshooting did involve wiggling of connectors to see whether that would solve the problem. Yeah, unplugging it and plugging it back in could be the next step. Let's try that over lunch. Anyway, so we got a board game designer, right?
Yeah.
And you're on Google's internationalization team. Excellent. And a guru on Unicode and TC39. And all of the rest I will leave to you. Thank you. And looking forward to your presentation. Thanks, Shane.
Give it up for Shane.
All right. You can all hear me? Great. My name's Shane. Thank you for the introduction. I work on Google's internationalization team. I also sit on TC39, which is the JavaScript standards body, as well as the Unicode ICFX TC, which I'll show you about a little bit later. So I'm going to be talking to you a lot today about this big long word here. It's internationalization. It's I followed by 18 letters followed by N. As programmers, we like to abbreviate things and make them shorter. So this is I-18N. In fact, it's one of the longest words in the English language. So we like to abbreviate that as I-18N. So what is I-18N? These are screenshots from YouTube, this YouTube video. On the left here, I have my locale set to Japanese. On the right, I have it set to Spanish. And we can see a little bit about what changes when you change the language of your web browser. So on the right here, for example, you can see that there's, obviously the translations are in the appropriate language, but you can also see things like on the right, you have a bit more than 1 million upvotes on this video. On the left, I have 191 something. I have 191 wands, actually, which is 10,000s because groupings work differently in Japanese, for example, than in Spanish. Obviously, dates change. Many different things change when you change your locale. So there's a whole lot of things that can change when you go to different languages. This is just a sample of some of the things that you might need an internationalization library to solve. Things like locales, numbers, currencies, units, dates, times, time zones, numbers, date ranges, relative time formats, temporals, eras, collations, plural rules, list formats, language display names, region display names, text segmentation, and the list goes on. And all these things change when you change your language, when you change your region. Somehow, software needs to figure out how you can operate your application correctly in a certain language. So a lot of people sometimes tell me, like, oh, well, that's all great and all, but, like, I-10 is a solved problem, right? Like, this is one of many other jokes you can tell yourself, because this is one of the biggest myths that sometimes I hear. Languages change, regions change, time zones change. And we try to keep up with the latest and greatest things that you can do with languages. So a lot of this comes down to having an internationalization library that can solve these problems for you. So we have goals in developing an internationalization library that you can then plug into your app and have it work in many of these different languages and many of these different regions and locales. One of the things that you want from internationalization library is you want to pay for what you use. You want to be able to have add extra locales on demand. These two things sort of go hand in hand. On the bottom left here, I've got a little graph that shows the common locale data repository. data size. There's hundreds and hundreds of locales supported, and each of those locales has many features in it. And the number of features, when you take number of features, from the previous slide, you saw the list of features. You multiply that by the number of locales, you get like a quadratic explosion of data. So you have a lot of data. You only want to ship what you need. The next thing you want to do by adding extra locales on demand is to be able to maybe download extra locales, load them into your application, but depending on what language the user speaks, it doesn't make a lot of sense to ship 300 languages if the user speaks maybe 5, right? So you want to be able to load extra locales on demand. You want to be able to run in resource-constrained environments. You want to be able to run on anything from a microcontroller to a data center, right? And you want to be able to keep up with the latest and greatest programming languages. We want to be able to write once, and we want to be able to have it work anywhere, in this case, programming languages. Internationalization sits at the border between programming languages and human languages, right? So we want to be able to write once and run anywhere. So this is when Unicode decided to form the ICU4X Technical Committee. The ICU4X Technical Committee is one of the things that I'm a part of. It's a cooperation between several organizations that you may have heard of in order to develop a new library in order to solve all of the problems that I had on the previous slide, problems that the existing libraries written in C and Java didn't really solve for us. So this is when we decided to go ahead and form the ICU4X project. So this is a little timeline of the history of the ICU4X project up to now. In 2019 is when we sort of, formulated these ideas, pitched the ideas, see if we can get a team together and to start solving the ideas. In 2020, we made one of the most pivotal decisions, which is obviously to go with Rust for solving these problems. We implemented some of our early infrastructure. A couple years later, in 2022, we released the 1.0 version of ICU4X, the ICU4X Rust project. In 2023, we started landing on some of our clients. We landed in the Firefox web browser and the Pixel Watch, among others. And then 2025, just last week, we released the ICU4X 2.0 release. We also landed in Android, and we're working on other clients. This also means that it's our 5th birthday, so that's always exciting. From the 0.1 to the 2.0 release, it's our 5th birthday. So that's exciting. So here's some examples of some clients that would use ICU4X, like who use the things that we built. On the left, we've got CanvasKit, which is using us which can use us via WebAssembly. In the previous talk, you heard a little bit about Skia. So this is basically Skia on the left side. All these components fit together when you do like text rendering. It's really mind-boggling how many things you need in your text rendering stack. And internationalization, in this case, text segmentation is one of them. We're on the Pixel Watch. If you happen to have a Pixel Watch in ambient mode, ICU4X is what's rendering your times and dates and heart rates and things like that. On the right side, we run in data centers. We help reduce and make more efficient internationalization in data centers as well. It's kind of mind-boggling the scale that when you have a core library that gets like half as big as the previous one, then you can save a mind-boggling amount of like compute resources. These are more ICU4X clients. If you use Firefox, you're already using us in your text segmentation, as well as in the temporal datetime library that's coming soon. The Rust C compiler uses ICU4X for error messages, for certain parts of error messages. Android, as I just mentioned a little bit earlier, we've got for Unicode properties. And Chrome is a work in progress. We have some changeless open that will hopefully be landing quite soon to do things like transliteration and temporal. A lot of people have put a lot of time into making all these things happen. So this is quite exciting. Okay, so now let's talk a little bit about like what is the library. It is IE10N that is portable, lightweight, and secure. So let's talk about all those words and what they all mean. So on the top left here, I was afraid it would be too small, but this is such a big screen. You can actually see everything on the screen, which is quite cool. On the top left shows the performance. This is just like, this is just a criterion benchmark. This is, how fast can you render the date and time, right? So on the top left, we've got, on the far left, we have the ICU4C, which is the C++ code. And on the right, the far right, we have the ICU4X 2.0 Rust code, which is quite a bit faster. And this is, I'm really happy that we're able to achieve this. The other columns are different configurations for ICU4X depending on on what version you're using, but the one on the far right is the one that you'll probably be using if you just install it from crates.io. On the top right, we show the memory usage. This is also, I think, something I'm really proud of. Like, basically everything that we do with formatting of datetimes and everything that you can do with Internationalization Library, we do without allocating any memory, which means that implies that we have very low memory usage. So that's what you can see on the right here. This is a logarithmic scale because basically I think we have like one allocation or something in like datetime, which is like, allocating like the string to render the output or something like that. And that's what's probably showing up in these benchmarks here. But very low memory usage. It also means that we can run in no-stud environments at places where you don't have an allocator. ICU4X solves that problem for you. On the bottom left, we can show that we already have very good binary size. So this is like if you build your app and you want to reduce the size of your APK, for example. A lot of people care about that. We're improving even upon the benchmarks we've already set for ourselves. We cut in half, even since ICU4X 1.5 to the 2.0 release, the binary size. And this is the code size versus ICU4C and ICU4X. This is a linear scale. This is comparing apples and apples. I tried really hard. I'm also a contributor to ICU4C, and I tried really hard to make sure that I was comparing apples to apples as much as I could. And this is I think the bottom right graph I think is the graph that I really want to emphasize. A lot of people are like, why didn't you just can we get the same results from ICU4C? And we really needed to start with a clean slate in order to achieve these results, and that's what we did. So I'm at Rust Week, right? People are like, that's great. Like, why did you choose Rust to solve your problem? Tell us more. So no other programming language was going to be able to do everything that we needed as well as Rust. So Rust works on all different types of devices. It's good for high performance and low memory environments. It does Unicode string handling by default for us, which helps us, which means that we don't have to ship expensive character encoding pieces of our stack. We have tree shaking, LLVM integration that helps us achieve small code size. It works really well with foreign functional interface, cross-language portability. It supports zero-copy deserialization. And one thing that I really didn't appreciate until after I had used it for a while is that it's really good for tooling and productivity. We have a large network of contributors, and Rust really helps us be able to review the code and land code and know that it's going to be safe and going to be secure. So that's really important. So let's talk a little bit about how ICU4X achieves its small binary size. So we optimize for dead code elimination. I'm going to go through this slide a little bit fast because I'm running a little bit low on time. But we focus on functions with a single purpose. We have data linked into each individual function. We have careful use of generics. Generics can either make your code big or small depending on how you use them effectively. We reduce code bloat. I already talked about allocations. We impl copy when possible. This is something people are interested in sometimes. All of our error types don't have a drop impl, and this actually does a big job of reducing your code size. And another is we avoid linking debug impls when possible. Debug impls often increase your code size. These are just general tips on how to reduce your code size, but these are the things that really have given us the most results for ICU4X. Zero copy deserialization. I'm going to talk about that in the next slide. I'm probably going to go through this slide fairly quickly, but this is a very important slide, so I'll try to spend a little bit of time here. The ICU locale crate, which does locale canonicalization and so forth, has many dependencies. But the reason we have many dependencies is because we really focus on making our code modular and pulling out the pieces that really enable us to achieve these goals. So on the orange boxes are like the ICU4X core crates. These green boxes are things that we've then contributed to the Rust ecosystem, right? So these are all things that you can use in your own apps. The title of this talk is Beyond ICU4X, so I'll talk a little bit more about a couple of these. But TinyString lets you have tiny strings in the stack. Writable is fast string formatting. It's almost twice as fast as the standard library display trait. We've got Databake, which Databake, Zervac, and Yoke I have slides about right after this one. And then we also use some standard library, or not standard, sorry, we use other ecosystem traits that we leverage. So it's a lot of crates. People, when they install ICU4X, are like, oh my God, so many crates. It's such a big library, but it's a big giant library. I just showed you the graphs a few slides ago. It's actually quite small and compact. So all these things are zero-cost abstractions. Again, the thing that we can do with Rust that's very hard to do in other languages, these zero-cost abstractions give us these small binary size even if you see a lot of crates coming in. ZeroVec is one of the util crates that we have. It's a way that we can take a vector of strings or integers or whatever and pack it into a binary format that we can then do zero-copy deserialization for. So this is a little example of how ZeroVec can work. If you're in any situation where you need to do low-cost deserialization, ZeroVec is a really good tool for that. Yoke is a tool that we use to solve self-references, and we solve that by having, for example, if you have a data file that you've loaded and you have a lot of locale data in that data file, maybe you loaded a new language pack, for example. You want to have a lot of things reference your language pack. What we do here with lifetime erasure, basically, is by having your deserialized data borrow from your buffer, and then we have many yokes that can then have reference counts to the same buffer, and you don't have to carry lifetimes around everywhere because oftentimes you want to create your formatter and you don't want to have a lifetime borrowing from some data file somewhere. This is how we can achieve that with Rust. Another exciting one is Databake. This is a thing people are like, how does this work? Like how can you achieve optimal binary size and data size? Well, you can actually serialize your data as Rust code, right? So for example, if I have like a data struct that has like a string and an integer in it, we can generate Rust code. And we've serialized your Rust code, but we serialized your data, but we've serialized it as Rust code. We didn't serialize it as JSON, we serialized it as Rust code, because why not? It's something we can do in Rust. Just a few more slides here. Diplomat is another thing that people are very excited about. It's how we scale to many different programming languages in terms of the number of languages. So the motivation here is that we want to support many programming languages, C++, Dart, JavaScript, etc. We do it via the C ABI, which is the lingua franca. I'll go through this slide fairly quickly. C, BindGen, WASM BindGen are great tools, but they target one language at a time. How can we target many languages all at the same time? By using the Diplomat macro. It takes Rust code and transforms it into something that you can use in many different programming languages. Here's a little example of how that works, the Diplomat macro. So on the left, you've got your Rust code. On the right, we have the corresponding C ABI. The C ABI calls back to the Rust code, and you can then run this in many different programming languages. One thing I want to emphasize here is that it's very easy to add another programming language. We've had contributors from many different places and backgrounds contribute. These are some of the contributors on the bottom here, and the language that they've spent the most time contributing. And this is a great way to contribute, which actually leads me to my last slide. I don't have time for telling you what's new in ICU for X 2.0. You can just read it here. You can also read the email that I sent out last week for more information here. So that was a lot of material. Watch this talk again if I went through it too fast or you want to learn more. There's also other talks you can find about other specific topics. And this is my conclusion slide. So I told you about how you can be a contributor, contributing to Diplomat, contributing another programming language. That's a really great way to get involved. We have a lot of mentorship opportunities. We have a lot of features that need to be implemented still, because internationalization is a very big space. There's a lot of things we could implement. We have a lot of open issues. We have a lot of good first issues. You can get in contact with me or anyone else from the team. And please use our infrastructure. Our infrastructure is here. It works. It's standalone. Even if you're not doing internationalization, maybe you need zero-copy deserialization. Maybe you need Databake. Maybe you need one of these other tools, Diplomat. If you want to take your Rust library and use it in some other programming language, Diplomat's also there for you. So, the point of this talk is really to, drive home these points, show you some of the things that we've done, contributed back to the ecosystem, and we're a very big open project. So that's my last slide. So I think we have time for a couple of questions. Thank you.
Thank you, Shane. We should have given you a longer time slot. There was a lot of talk in there. That was amazing. All right, are there any questions? Here, and there's a catch box over there. Great form.
Does it work? Holy shit. This is amazing. Okay, so in the example ICU for X clients slide, you show the Canvas kit, with some text and that you were resizing the Canvas kit. I'm curious, did that was that actually doing text segmentation or was it not for like the line wrapping? Because
yeah, I'm scrolling back to this slide. Here's the slide you were talking about. Yeah, so it's using ICFrec for the text segmentation is what's going on here. So like it has to figure out when and where to break the words. This is quite, it's in a language that has spaces to separate, it's like, don't you just look for the spaces? But like, I think on one of these slides, maybe the previous one up back here, I have examples of, for example, there's a Japanese text on the bottom right. Like, there are no spaces. You had to figure out like where the word breaks are, right? And this is the thing where we have to have an internationalization library to solve that problem.
Exactly. Nice. Okay. Amazing.
All right.
There's a question there all the way in the back. Yeah. Oh, this is going to be a big throw. This is fun. You're going to do it?
Do it.
Yeah.
All right. It should get a
On to
little
the
bit
next.
of an extra boost.
Yeah.
There we
Oh,
go.
almost.
Hey.
Here we
With
go.
Diplomat, you put the derive macro only on the struct definition, so how do you get the list of methods in the import block?
Diplomat macro, let me go to that slide. This slide here, I believe.
Yes.
The diplomat macro goes on the everything on the left has is actually inside a module that has a annotation called diplomat bridge, which is not actually shown on this slide, and it should be. But all the code on the left is analyzed by the diplomat macro.
Okay, so it's the same thing CXX does.
It analyzes the whole macro and then generates the C bindings from everything that it analyzed. And it produces an HIR representation, which is what the target languages can use to then generate like the code that they use and then call into the C API bindings.
Cool, thanks.
There's a question over here on the right. Yeah, you can throw it back.
In the meantime, I'll say that we are going into lunchtime, so if you really want to have lunch, then you could, but I mean,
I'll be around I'll be around all week. Find me and ask me more questions.
Well, let's do a couple more questions. Go ahead.
Hey, thanks for the talk. It was great. I truly apologize for the following question, which is sort of beside the point of this whole thing. But you did pique my curiosity with the implementing copy trait to reduce the size of the binary. Are you saying that implementing the copy trait sort of forced you into a coding style that is more amenable to small binaries, or is it that having the copy trait implemented on, trivial structs actually changed the way that the code is compiled?
Well, I think the answer to this question is like before we had the policy of implementing the copy trait for all of our error types. It was somewhat common to find things like a box dying error inside of like error types, or to have a string inside of error types, a capital S string, and those things just really increase the size of the code because now you have a drop impl. Whenever you call a function, you have to have like a drop impl for this error type, right? So like enforcing this policy that all like error types or copy has like sort of focused us in the direction of being able to produce this small code size. Like whether or not like if you have the exact same structs or the exact same array enums, whether or not they actually have the copy attribute, the copy derive on them, I haven't actually tested to see if that has an impact on the code size.
All right.
All right.
Just real quick, for the people who are walking out and want to have lunch, if you have any LRGs, make sure that you talk to the people at the bar closest to the entrance.
Yeah, they can hook you up.
They can
with,
direct you to food that is appropriate for you. But
exactly.
please carry on with the
I
questions.
see. Last question.
One philosophical question. What can you do to increase adoption of this? Like one of the first slides you showed, people think that getText or strftime is like the best thing ever. And how can you convince people that there is better ways?
One way is by coming to places like this, to Rust Week, to sort of emphasize like it's really important to have your software support multiple languages as well. Like raise your hand in here if you speak more than one language. Like this is a very easy question in the Netherlands, right? So people here like understand this, even more than sometimes the other audiences that I give this talk to. But like being able to build software that actually works really well across programming languages, it gives your apps a competitive advantage. If people like to use apps that work and make sense to them, like I think a lot of experiences of multilingual users is like, well, I'll just like switch to English because like it's better in English. But like that's not the world we want. We want a world where all 2,000 languages like have really good experiences. And in order to produce that world, like in Unicode, we're producing not only the ICU4X library, we also produce the Unicode standard. We're encoding new scripts. We work a lot with digitally disadvantaged languages in order to acquire data, in order to really build software that works for users in every country around the world, right? So, I think, if evangelization and really, setting a good example is a really big step in order to, produce the world that we're all striving for.
I think that's a fantastic closing answer.
I love the phrase, what was it, digitally disadvantaged?
Yeah.
That's a good phrase, I love it. All right, thank you so much. We're now going to have lunch. It is 1 hour and 15 minutes of lunchtime until 2 p.m.
Yes.
And then, so there's loads of lunch downstairs. Feel free to take what you want.
All right. Thanks a lot.
See
Enjoy.
you in the afternoon.
once more. Huawei, who's a diamond sponsor, made this event possible, along with Z Industries, who's a gold sponsor. Both organizations have a booth downstairs, so go
You should
visit
go
them.
check them out.
Check them
Definitely.
out. Lots of interesting stuff.
Definitely.
Yeah.
All right. There's a little bit of a sort of PSA. There's somebody who lost their brown laptop case somewhere between row 9 and 10, seat 15. So around that area, if you find a brown laptop case, it might contain a passport. So it's quite important. So
Yeah.
if you find it, please let us know.
That's really specific, though.
Yes.
The row and seat number.
Yeah. Yeah, they
This
were
is
very
the
specific about it.
advantage of doing this thing in a cinema.
Exactly. You got really specific numbers. All right. Let's introduce. We actually have 3 speakers lined up for this next segment.
Absolutely.
It's packed, and they're so good.
This is the part where the MC tries to get the pronunciation of names right and then hopelessly fails, because this time it's Polish. It's Michał.
Yeah, Michał.
Kostrowicz.
Kostrubiec.
See, I think I get it right, but I don't.
Close enough.
Yeah, thank you. You're a contributor to Rust C, right?
A tiny bit here and there.
Yeah, okay. And you're famous for your Reddit posts?
Well, could you repeat?
Yeah, you're famous for Reddit posts?
Yeah, I write blog posts like teaching people kind of a tiny bit about my work related to the Rust compiler, about kind of how Rust C works in general. That's like also the goal of this talk, to kind of
super awesome.
intrigue you a tiny bit in how the Rust compiler works, to kind of point you to. I feel it's a very interesting subject, the Rust compilation.
And you're
in
going to
general.
do 2 talks?
Yeah, 2 talks. So.
Well, good luck.
Pressure is on, definitely.
Exactly. Good luck with the first one. Hey,
Yeah.
take it away.
So, thank you very much. In this talk, I will tell you about my work compiling Rust to C. My name is Michał Kostrubiec, and I am a 90-year-old student at the Maritime University of Szczecin, Poland. I have learned Rust in 2020 during the lockdown, and I have been working on this project for about 1.5 years, maybe soon 2. And your very first question may be, why would anyone want to compile Rust to C? Rust is a safe language and C is not, so going sort of the wrong way may seem kind of pointless. However, there is surprisingly a use case for this, so let me explain some of my reasoning. The main goal of the project is better platform support. Currently, there are quite a few systems that are not supported by Rust, and that's not because no one wants to support them, that's because LLVM doesn't support them, and in some cases even GCC doesn't support them. Like in the case of a lot of those systems, the only way to get any code running there at all is to use a proprietary C compiler, which is not ideal if you want to write something in Rust. And at first you may think, okay, we cannot run Rust on some platform that no one has heard of in 30 years. What's the big deal? Surprisingly, a lot of those systems are not nearly as obscure as you may think or wish. To give a more concrete example, recently over on the Git mailing list, there have been some discussions about moving parts of that version manager to Rust. But it was quickly pointed out that doing so would mean dropping support for the no-stop OS system. That's like a fault-tolerant OS used heavily in finance. And the Git, I believe the Git platform support policy is a bit wobbly here, but in general, they don't want to drop support for anything. So they really cannot move anything too critical from C to Rust without either they would have, I don't know, maybe keep 2 implementations in parallel. It would be like very awkward. So for now, I believe they have decided to only write new things in Rust. And it's a real shame because they have some really good points around that mailing list about what benefits Rust could bring to Git. However, if we had some way of turning any Rust code into undefined behavior-free, equivalent C code, this problem would kind of disappear because we could then translate Rust to C, feed that C into that platform's proprietary C compiler, and get Rust running on a lot of systems. Obviously, there are some caveats. There are some systems that are way too obscure for Rust to run on, but in general, we could get a big chunk of new targets at a relatively low cost. It's not a very simple process, but it's doable. And additionally, this has been a learning opportunity. This project actually originally started with, I didn't think I would finish it. I thought, okay, I would just try writing something related to the Rust compiler because I wanted to learn how it works. And it kind of snowballed from here, and I have been working on this more or less daily for about those 1.5 years now. And I have been trying to teach people about the Rust compiler because I am of the opinion that a lot of people overestimate how difficult working on compilers are. They feel kind of impossible to work on because they are very big. But if you focus on a small part of the compiler, if you really put your heart into it and spend the time necessary to learn to get the hang of things, then after some time you will actually be able to contribute to the compiler quite easily, because it's not difficult, it's just very big. So I have been writing a series of blogs, and it's also, as I said, the purpose of this talk is to show you a basic overview of the Rust compiler and maybe kind of encourage you to try contributing yourself. I feel if my work indirectly causes even one more person to contribute to Rust C, then I have done something with my life. Additionally, compilers are just ridiculously fun to work on. I would be lying if I said that this wasn't mainly a passion project. Really, there's no word to describe this unique feeling you get when you see Rust running somewhere where isn't supposed to run on at all. I got Rust running on a Game Boy console, or I even got it for April Fools running on TempleOS. I don't know if you have heard of TempleOS, but Rust is now running there. Yeah. So really, as I said, I want to kind of share this feeling with you, maybe infect you with my passion for compilers, because I feel it's one of the most fun things you can work on. Now that I have kind of said why, I think it's important to say how, because at first you may be kind of skeptical. Rust is not known for being a simple language. It has a lot of features. And writing a whole Rust compiler as one person would be impossible. But there are some things that make it slightly easier for me. So first of all, the Rust compiler is modular, even though it's kind of split into 3 parts. You have the front end, that's what parses your code and does things like macro expansion. You have the compiler middle, which is responsible for things like type and borrow checking, and the compiler backend. That's actually what creates the final executable. And the compiler backends can be actually replaced at runtime. It may come as a shock to you. You can replace entire components of the Rust compiler simply at runtime. You pass it the right flag, tell it, please load me this library and use it as a code gen backend. It will happily do so. And to write a Rust to C compiler, I don't need to write a whole compiler. I only need to write that one specific part of the compiler. This may still seem quite hard, but the way compiler backends are designed makes this a whole lot easier. So a compiler backend doesn't actually work directly on Rust code. It works on something called mir. You can kind of think of mir as a simplified representation of a Rust program. So one big Rust function will be actually split into a whole lot of mir statements and terminators. Those are primitive operations, so array indexing, addition, function calls. And all of those things are simple in isolation. And since mir is fully borrow and type check, I don't need to worry about things like lifetimes, generics, how iterators are implemented. All of that, all of the things above mir are actually an implementation detail to me. I don't need to, worry about them at all. They are irrelevant to my project, and all I need to worry about is mir. That also means that new features, when new features are brought to the Rust compiler, I usually don't have to put in all that much work to add support for them, because they quite often compile down to the exact same mir statements. So since, for example, I believe that enums and closures use some of the same machinery. And because of that, adding support for things like async and for future features is relatively easy. Right now, I believe updating to a new native version, usually I need to change something, like a couple lines of code every month or 2. So it's not too difficult to keep up with the newest Lightning. I don't know if I'm at the newest Lightning right now, but I know that I'm usually at most a week or 2 behind. And translating mir to C is made way easier because each component of mir can actually be handled fully in isolation. They are not really context dependent. So if you have a sequence of mir operations, a given operation will always more or less translate to same C. It doesn't matter where is it in the function. And a given, for example, there's something called a projection, which refers to some place in memory that will also get translated to more or less the same C operations, no matter where it is placed. So I need to write simple code that handles every single one of those components in isolation, and then they get combined down into something much larger. And this is what actually enables a project like this to exist at all. Because if I am able to look at each small part of the compiler in isolation, they become way more manageable. Taking everything that there is into having all of this in the head would, at the same time would be impossible, but focusing on a single part is way more feasible. So that might have been a lot. I have introduced a lot of new concepts. So I think we will kind of look at the journey of one simple Rust function for you to get a hang of how those things look. I will show you first the original Rust code, and then I will show you the mir, talk about some of its properties, and then we will look at this generated C for you to maybe not fully understand the process, but get a gist of how things are working. So here we have a pretty simple Rust function. It consists of just one expression, and it computes the component or field-wise sum of two vectors, which represent a point in 3D space or a direction. We, for example, want to add a direction, so we add its x component and assign it to the x field of the result, or we add the y field and assign it to the y field of the result, and so on. And I feel like I don't need to explain this code all that much more. It's fairly simple Rust, fairly standard syntax. But now we will take a look at the generated mir for it. I hope that you can see everything there is there, because as you can see, the mir is quite a bit longer. Why? Because one complex Rust operation, one expression has been compiled down to a whole lot of steps. And the first interesting thing you may notice is that the return terminator at the very end here, it doesn't take in any value. So you may ask, well, what does it return? It always actually returns the local number 0. Locals in mir are referred to by numbers and not by the names. So like this actually simplifies some of the optimization work, I believe. And you may here notice that the addition of each field has been separated out into a separate statement. So when we add the x components, it is a different statement than adding the y components. And as you can see, those operations are very, very primitive. Like I don't think there's anything simpler than a binary operation. And here later we create an aggregate, and then there's also a separate operation. So really, all of those complex Rust operations get compiled down to a whole bunch of those simple primitive things. And this, as I said, means that things like iterators get compiled down to some branching and function calls. Like there is no concept of a for loop or a while loop or an if statement on mir level. It all gets compiled down to like gotos and something called switchings, which are basically a way of implementing switching on values in mir. And now we will take a look at the C code I have generated from this mir. And you may notice that there is the exact same number of local variables, because at the beginning of the process, I actually try to keep the mir and the generated C as close as possible. I try to keep the local variable numbers as close as possible. This is, once again, something that simply makes my work easier and makes debugging this whole thing easier. If I can take a look at the mir and the C I generated from it, I can kind of more or less eyeball if I'm doing something right or wrong. Another thing you may notice is that sometimes I am actually unable to compile one mir statement to one line of C code. Here we have the initialization of the return struct value. This actually simplifies some stuff because enums require initializing enums using as literal in C would be a bit difficult, I believe, because you need to both initialize the variant and the tag, and it would get all messy if I try to initialize it all at once. And additionally, I believe it improves compatibility with some old C compilers. I have seen compilers which don't actually support the literal. I believe I'm not sure if it's in the first version of the C standard stack literals. I believe they may not be in it. So this actually also improved compatibility besides being a tiny bit simpler. And now we'll get kind of into what I believe to be the meat of the talk, so-called nasal demons or undefined behavior. This is actually something that my project kind of its success hinges on it a lot. Because I don't want to ever translate valid Rust code into invalid C code. But before I talk about undefined behavior more in depth, we kind of need to establish a baseline for what undefined behavior is, because I have talked to quite a few people and I was shocked at how many people don't know what undefined behavior actually means and how many misconceptions about it are out there. Some people believe it simply means that you will get some kind of undeterminate result, that you may get different results between platforms. Some people think you will always crash with undefined behavior. And some people will just kind of do things like read uninitialized memory and say, oh, you will just get a random value out. Spoiler, you will not. Here we have a fairly simple Rust function that we add 1 to a certain value and check if it's the value incremented by 1 is smaller than the original value. This will actually only return true in the case of an overflow, because we have overflow, so the largest possible number becomes the smallest possible number. And at first, your intuition may be to translate it more or less into line by line to C code that looks identical. Here we are only like change a few things. Those are more or less identical, save for a few syntactic differences. And you may ask yourself the question, well, is the result of the operation the same? Will this like test, will the assertion still pass? And the problem is, it sometimes may and it sometimes may not. Because a really undefined behavior happens when, at least I like to think of it as us violating some kind of rules of the language. The language is specified in a certain way that things will work, something will or will not happen, and we violate those rules. For example, if you try to, in Rust, if you try to mutate an immutable variable, it's obviously wrong, because the compiler can use the fact that it's immutable for optimizations. And here, when we turn optimizations on, this function can actually be optimized to always return false. You may wonder why. Well, the only way for this function to ever return true is for an integer overflow to happen. And in C, signed integer overflow is said to be undefined. So if it happens, the compiler can assume it never happens because it's a compiler for C. And in valid C, there may be no signed overflow. It's not a compiler for something that kind of looks like C. It's a compiler for C. And it's not like the compiler is not doing anything wrong. It's actually doing something right, let's say, because we want our compiler to be able to optimize things. Like, as I said, we want the Rust, for example, with the Rust compiler to be able to optimize things based on the aliasing rules. We want for it to be able to see that reading from an immutable reference will return the exact same value. We want without undefined behaviors, optimizations cannot really work because the compiler needs to assume certain things to be always true. Like it cannot assume that our variable will not be mutated by someone else, or it can assume that certain things simply may never happen. And here it assumes that an overflow may never happen. Because if an overflow can never happen, then this function will actually always return false. So this is a fully correct transformation, and it will not break any valid C programs, but it may break invalid ones. And I think the devil in the detail is that it may break. It doesn't have to necessarily break it. You may run this test on all sorts of different compilers, and some of them may optimize this, some of them may not. Different versions of the same compiler, different combination of flags. All of that may affect if the undefined behavior will actually cause trouble or not. And even in theory, the compiler could even check if it's Monday and only break your program in such a case, because it would never break valid C programs, so it would still be fully standard compliant. And so undefined behavior is undeterministic, and it can lead to all sorts of issues. First of all, incorrect behavior. Here we have seen a pretty good example of that. The end result of the program is not what we would expect it to be. And it can lead to memory unsafety, it can lead to crashes, and it can lead to vulnerabilities. Because, as I said, if we break some of those rules and the compiler optimizes based on that, it could, for example, optimize away some kind of security check. If we imagine that we, for some reason, use that function from the last slide for, I don't know, authentication, to check if the ID of a user is equal to int max, the compiler could optimize that away to always return false, and our program would be broken. Some kind of security critical stuff may be broken. And the interesting thing is that safe Rust is undefined behavior free. Like safe for compiler bugs like CVRS. Rust code is considered to be undefined. Safe Rust code is considered to be undefined behavior free. Otherwise, it's not sound. And if you can actually invoke undefined behavior in safe Rust, that would be a compiler bug, and it would get reported and it would get fixed. If you can do the same thing with the library, it should get reported and should get fixed. So really, the translation process must produce undefined behavior free C code. If it does introduce any kind of undefined behavior, then, well, I should just pack up and go home because this project will not go anywhere. Currently, right now, 96% of the core compiler test should pass with undefined behavior checks enabled. So that does not necessarily mean that there is no undefined behavior left, because undefined behavior is insidious, and as I say, the more I learn about C, the less I know about C. Because there are quite a few things that are undefined behavior but are not exploited by most compilers or by our compilers I have access to. So is it undefined behavior if compilers don't exploit it right now? Well, it still is, but it's not really a problem. or the undefined behavior checks, they only kind of check for the most common kind of undefined behavior. They don't check for all possible undefined behavior. There are some like things that may slip through them. Yeah, I have also seen like with some compilers, they detect undefined behavior only when you, for example, enable some optimization. So really, squashing all the possible undefined behavior may be like verifying that I for sure produce undefined behavior free C code is quite a task. I don't know if I will be able to ever say with confidence that there is no undefined behavior there, but I can say that I have put a lot of effort to minimize that risk at least. And yeah, so that's, as I said, undefined behavior will screw us over. If there is any undefined behavior in your program, there will be issues at some point in time. Oh, we can see here a little bug. Oh well. So let's kind of look at some ways we can avoid undefined behavior, because some of it is quite ugly, but for a lot of problems, actually the solution is relatively simple. It's like you will be able to understand why those solutions work. They may not be pretty. They may have some overhead. Okay, thank you. They may have some additional overhead. They may be quite ugly. So let's start first of all with signed and over and underflow. So the funny thing is that in Rust, the signed and unsigned variants of operations are actually identical if you look only at the bits of the value. That means that if you ignore the type and you only look at the bits that compose the value, they will be identical. And if you look at the instruction that in most cases the compiler will use, they will be identical. So we can, instead of performing a signed addition here, we can simply replace it with unsigned addition. And this is actually fully sound, and from what I have checked, most C compilers will simply translate it to the correct instructions. There will be actually very little to no overhead to this. So this is a nice example of a case where we can avoid undefined behavior with relative ease, and where we don't need to pay any additional costs to prevent it. Another thing that can cause undefined behavior are bit shifts. So in C, if you shift something by an amount larger than the size of an integer, the result will be undefined. But in Rust, you will either get a panic or you will get a shift by the modulo of the amount. So here we have to actually add something to the C code, but it's actually a cost that the Rust compiler pays to in a lot of cases. So this is an example of where undefined behavior makes the generated C code slightly more complex, and I think some C compilers may not be able to eliminate it in all of the cases, this additional modulo, but it's, as I said, if it is a cost that's also paid by the Rust compiler, it's not really a cost we pay. Like in the end, the performance between the C code that got compiled to native code and the native code created by Rust C is more or less the same. And one thing I have actually seen that a very few people know that casting a floating point value outside of the valid range is actually undefined behavior. And this actually has led to some interesting bugs in the real world. I don't know if you have heard of the game Mario for the Nintendo 64, the first 3D Mario game. You can actually crush it in quite a few ways by because that particular system, I believe, traps when you try to cast a float value out of range. So if you try to cast a too large of a value, you will actually get a crash on those systems. And on other systems, you may get a wraparound. On some, it may saturate. So there are as many systems there are that many completely different behaviors in regards to this. And as I said, it's undefined behavior. So if you, for example, do this kind of cast, the compiler may later assume that the floating point value is actually in the range, and since it sees that if it was out of range, you would have undefined behavior, can actually remove some checks later on. So this is once again the case where undefined behavior may be viral. That's like one thing that's, I think, very important to understand here, that undefined behavior can actually affect pieces of code that seem completely unrelated. So my solution for this is fairly stupid. We simply check if the value is outside of that range and return int max or int min. It isn't the cleanest thing ever, but it works. We actually also use here a simple none check, because since none is not equal to itself, we can simply check for all values that are not equal to itself, and this way we'll actually quite cheaply detect none. This actually can still cause problems if you turn on some optimizations in, I believe, FastMath, for example, in GCC, because in those cases the C compiler can actually assume that nuns don't exist. So that would be even more of a trouble. But like you actually have to ask for this trouble. So I don't, and there really isn't any way for me to avoid that, save for, I don't know, emulating floating point values or something crazy like that. Yeah. Intrinsic, and this is like one of the funniest cases of undefined behavior for me, because the count leading zeros intrinsic is actually quite simple. All it does, it counts the number of zeros at the beginning of a number. So here, for example, it will return 0 because there are no zeros in that number, or it will return 31 because the first 31 like digits of that binary digits of that number are actually zeros. But if we call it with a 0, that's undefined behavior. And you actually, the C compiler in a lot of cases catch that and even warn you about that. And the reason, you might wonder, like, why on earth would this be undefined behavior? Why, like, this seems like, what would be the benefit to making this undefined behavior? Actually, the problem is that on architecture level, the bits scan forward instruction, I believe, is set to produce not undefined, but an unknown result if you pass 0 to it. So on the CPU level, the instruction itself is set to, it can produce something else than you may expect. And this is actually, from what I've heard, like through the grapevine, that's one of the reasons why this intrinsic is actually undefined behavior for 0. So yeah, CPUs can have kind of their own version of undefined behavior too. Yeah, so now I will kind of wrap things up, start kind of summing things up. Like I have gone over like the simpler cases of undefined behavior. I have actually kind of considered going over some more complex ones, but I feel like I wouldn't have the time to give them justice. I will like quickly mention some of them later on. So the only reason a project like this can exist is because the Rust compiler is highly modular. Like if it was designed in a different way, if there was no way to replace a backend, something like this couldn't exist. I think for sure with only one person, like I would need probably at least as many people as are currently working on the Rust compiler to kind of recreate it. So the only reason I can do something like that at all is because the Rust compiler is modular. And despite being called unstable, from my experience, the compiler internal APIs that are exposed are actually fairly stable. That's one good thing about them. Like they are, even though they may not be always perfectly documented, the one good thing about them is they tend to be stable. They don't tend to change all that much. And because Mir is so much simpler than Rust, I don't need to worry about a lot of high-level detail. I can simply ignore that. I can only worry about, as I said, a small part of the compilation process, and I can ignore quite a bit of the complexity. Here, really, I think the biggest lesson for me for the project is to kind of work on focusing on a certain scope and to not kind of exceed that. The biggest challenge for the project is, as I said, undefined behavior, and it makes sense because Rust is not C and C is not Rust. They have different semantics, different things. There are actually cases where something is not undefined behavior in C but is undefined behavior in Rust. Those are quite weird, but they do happen, and there are cases where something is undefined behavior only in C. So really, the translation must preserve those semantics of Rust as well as possible. I have actually also fused my backend with a tool called Rustlantis. It actually generates a whole bunch of compiler ER, and I use that to kind of more ensure correctness. Additionally, like it's not perfect, but since it was used actually to detect bugs in the upstream Rust compiler, it has actually detected, I believe, 20 or so of them. So I believe that I did a much smaller fuzzing campaign, and I haven't found anything yet. Maybe that's the case of someday I need to throw more compute at that to like find those cases. But in a lot of cases of an undefined behavior, we actually have simple zero-cause workarounds. So for example, with overflows, as I said, they compile down to the same instructions. So really, there is no need to worry about that. In other cases, we have some overhead. Like with shift, like it's an overhead that's actually also paid by the Rust compiler, but there is overhead. There are some other cases like with intrinsics. Oh, like to quickly mention about the count leading zeros intrinsic. Actually, the Rust compiler has two variants of this intrinsic, one for non-zero values and one for zero values. That's because it actually needs to insert a check just like that. So the check I have inserted for non-zero values, that's something the Rust compiler will actually insert too, because of the bitscan for one instruction. On more modern CPUs, it will actually use an instruction that implements the intrinsic for all values in a fully defined manner, but okay, I digress. Certain kinds of undefined behavior are way more complex to work around. For example, I know that some people who are more in the know will be very curious about strict aliasing, because that's kind of a big elephant in the room. Strict aliasing basically allows C compilers to assume that certain kinds of pointer will not alias. The general simplified idea is that if you have pointers to different types, they will not overlap. So if you read a pointer from an integer, the pointer from a float will point to a different allocation at the same time. Okay. And in this case, the workaround is kind of ugly. I just need to use memcopy for all memory loads and memory writes. As I said, it's not pretty, but it works out. Yeah. And like this will be, I'm kind of wrapping out now, but I see that I have slightly more time. So to mention another thing, because this is something like people ask me about, like precede some questions, I actually preserve debug information in the generated C code. I use something called the line directive to preserve source file information. So if you use a debugger, it will actually point at the Rust code. And like, as I said, the main goal of my project is to create C that's undefined behavior free, and if possible, that looks also similar to original Rust code to allow you to quite easily verify that. So yeah, if you have any more questions, you can actually find me anywhere in the conference. And like, feel free to just go up to me. I will, since I'm one of the GoSim people who got the GoSim Spotlight, I also have a table at which I will be sitting during most of the breaks. So you can just come up to me, ask any question you may have about anything, and I will try to explain that. And I believe, do we have like time for questions now? Okay, so like, if you have like.
Nice.
Thank you, Michał. Well, great talk. Should we do some questions? Is Arya going to throw the catch box?
Arya, you got it?
Where are the compiler nerds at?
I think I can probably guess the answer, but do you do anything about the max symbol name limit in C versus mangled symbols?
Yeah, actually, like in such a case, I was have something to like. I don't truncate them, but because that leads to collisions, I have to first I hash the symbol and then I use the symbol hash. If like it's very very long, in such a case, I replace it with like an encoded hash of the symbol, and that tends to work out. Like I haven't seen like a collision with that yet, but you would have to have a lot of symbols for there to be a collision in such a case. But yeah, it's kind of sad that I have to do something like that, but I have a limit. That's like configurable. I can kind of, I believe right now it's a constant, but I can raise it or lower it depending on C compilers, because I have actually seen some C compilers. There's actually, with symbol names, there's actually a lot of work between different C compilers, because some of them allow some symbols like the $sign. So some C compilers accept that, but some of them only accept ASCII characters. So I have actually an option to like lower our symbols to only use ASCII. Yeah.
Okay. Want to do a question here?
You already know about a lot of potential theoretical problems when going from Rust to C, but there are probably some blind spots you may not be aware of. So when you get your C output, how do you test that what you have obtained is reliable? How do you find new blind spots to work on and to patch further?
That's actually a pretty good question. As I have kind of alluded, I run the Rust compiler test suite, and I kind of cross my fingers and hope that by running that much code, like a lot of those are actually written to test different pathological cases. There are some really, really weird things out in the compiler test suite. If you like look at the passing test, there's a test called Zombie Jesus or like something like that. So there's like a lot of really weird tests that test really weird edge cases you wouldn't think of, like comparing the addresses of function pointers and things like that. So they, because I believe back in the early days of Rust, things like There were actually some issues with aliasing. I believe the Rust compiler didn't emit the no alias attribute because there were some LLVM bugs that caused miscombination in such cases. So there are a lot of tests that test this kind of thing. So the hope is that I will catch most of them by running those tests with undefined behavior checks on. I also, as I said, I fast the compiler a tiny bit. I have my own tests written for some things that I know that tend to. I have my own regression tests that I run on every commit to ensure that I don't break anything, because I have in the past broken things in some ways that I didn't expect to break. Yeah, there are definitely a lot of really weird edge cases that I have to kind of go over it. And hope is, as I said, there's no. If I find something weird, then I just add it to my test suite, and it kind of is growing over time. I have 400 or 500 of tests of my own. Yeah.
Okay. How are we doing on time?
I think we can do 2 more questions.
Okay, cool.
There's one
Up
over there.
here, hello. You've nearly found me. That's okay. I am curious about how big your project is, and also how big it was when you had the first successful compilation.
Depends on what you mean by successful compilation.
Just the very smallest piece of Rust that generated valid C code.
It was I think the 300 or 400 lines of code that were needed to start the backend. That was at the very beginning when I compiled a simple function that just added 2 numbers together. Right now, I'm kind of in an awkward spot because I'm doing a very big refactor right now. I have made, as I said, it's a learning project, and I have made some very stupid mistakes in the past that I'm kind of trying to dig myself out of the holes I dug. So I think it's 40,000 lines of code, but a lot of it is duplicated because I am moving from one representation of C to another that's way more optimized. I started with kind of a stupid representation that doesn't do any interning, and I'm adding things like interning right now. That basically means that it allows me to save on memory. Yeah, so I think at least 10,000 lines of code is duplicated between the old and new implementation, and I'm kind of slowly ripping that out as I kind of work around some issues. But another interesting thing is that actually most of the code is shared between my work compiling Rust to C and work compiling Rust to .NET. I believe the difference between the code compiling Rust to .NET and Rust to C is only a couple thousand lines of code in the very end of compilation. Most of the process is actually shared, and that makes some things easier.
And the compiling to .NET is what your other talk will be about.
Yeah.
So the ecosystem track, if people are excited about that.
So if you are not bored of my voice already, I recommend you go there.
Do we have one more question somewhere? I don't know where the box is. I can't see anything.
Yeah. So I got a question here. Maybe is that okay?
Yeah. If the box is not in somebody's hands.
Hi. Thanks for the talk. Do you plan on supporting unwinding at any point?
I support unwinding for the .NET part of the project, but I haven't looking into how to do that in C, and it looks like there's some compilers have their own extension. Right now, I basically compile unwinding to the equivalent of .NET mechanism for try-catch, and if a compiler supports something like try-catch, I can support unwinding. In such a case, I have actually my own implementation of libunwind, a mock implementation that implements all the functions necessary for Rust to work. But adding full unwinding support requires C compiler to support that, and then I don't feel I think MSVC has something like that with structured and exception handling, but that's only one compiler, and there are some restrictions, so I haven't actually looked into that quite yet. I have kind of once such, as I said, it needs the C compiler to support some things, and not a lot of them do. So for now, I just kind of, you have to abort on panic. With .NET, you can actually recover from a panic, but with, but with the C side of stuff, sadly, there's just no good way. Maybe someone will tell me that maybe there exists a way, maybe I'm just blind and I didn't notice something, but right now I don't think there's simply a good way to do that.
Sounds like you need to compile to C++ or something.
Yeah.
All right. Thank you so much for your talk. Give it up for Michal.
Yeah, we'll now set everything up for the next speaker and give a tiny opportunity for all the people there to either take a seat, see the people moving around.
Time for a room change.
Thank you.
All right, last people, please take your seats. We're going to get started with the next talk. So, the next talk is by Caroline Morton. She is a medical doctor and epidemiologist, which is a hard word for me to say, but she's also the co-author of the Async Rust book by O'Reilly, and she's created the Women in Rust group. And at the end of your talk, there will be a way that you can contact her about that if you want to get involved. And her talk is about how we can use Rust, like sort of from a different perspective, how we can use memory-safe and performant programming languages to improve scientific outcomes. Take it away, Caroline.
Well, thank you very much for having me here. So I can't actually stray too far from my laptop because I've got one of those annoying MacBooks that's only got 2 ports, so I can't plug in the clicker. So I'm going to be here. It means I can't see you. So my name is Caroline Morton. So who am I? So I've already been introduced, but I work now as a software developer. In Rust, I do consulting, and I also run this company called Clinical Metrics, which is a simulation company we make. It's like an emergency room simulation. I previously worked as an epidemiologist and as a doctor. I've done lots of epi papers, epidemiology papers, and kind of got into programming through that way. So from like a statistical programming perspective into programming. And then I was lucky enough to co-author this Async Rust book. And as mentioned, I've set up with someone else, Women in Rust, and there'll be a way to contact me at the end if you want to get involved. Okay, so this talk is going to require a little bit of explanation about what the problem is I'm trying to solve. So bear with me, there's a lengthy introduction, and that is very much on purpose because it is something which is kind of complicated. So we'll go through the problem, we'll talk about the tool, what my plans are for the future, and please implore you to get involved, and then some of the key lessons that I learned for this specific journey, trying to implement something for kind of scientists, basically. Okay, so we're going to start with this question, which is, what is a coded event? Okay, so the way that I always explain what a coded event is to think about you as a patient. Okay, you're a patient, you've got a cough, you feel rubbish, you go to your doctor, and they examine you, they do your temperature, they think you've got a chest infection, you've got a pneumonia, give you some antibiotics, and away you go. Okay, so you may see your doctor writing notes furiously on the computer while you're doing that. At least that's what patients always complain about, is that their doctor is writing on the computer. And you might assume that that is just free text that is going into the computer. But actually what happens is, as they type, things are being popped out and said, you've started typing pneumonia, do you mean pneumonia? And so it's like a pop-out. And that, from a doctor's perspective, is really useful because it's like, oh, I don't have to type the whole word. Brilliant. But what it actually is doing on the back end is it is assigning these numerical codes to things that you've written. Okay, and that is a coded event. So you can see on the left-hand side, there is a number, that's a SNOMED code, and in the middle you've got the term, and sometimes there's a measurement associated with it if it's like a blood pressure. And so we're going to come back to what SNOMED codes are, but that is how your appointment would be essentially coded in the computer. It's slightly confusing because I'm using the word code and coded quite a lot, but if that, I can always clarify that at the end if there's any questions, or actually shout out. So we've got your GP appointment, and we've got your coded events. Now all of that information then gets put into a table. Imagine a massive table, and we're talking about millions and millions of lines of data, because you can imagine you have your whole life, or you have a family doctor. It gets put into a secure data environment. it goes to a data provider, and then people like me or people who are doing research can request to use that data under very specific circumstances that I'm not going to go. It's sort of out of the view of this talk, but we don't have willy-nilly access to your data. It is under specific circumstances. Okay, so what are these codes? So we briefly mentioned SNOMED. So SNOMED represents the world. Okay, there is a astonishing amount of SNOMED options. There's including everything from different ways that you might get hit by debris falling from an aeroplane to different dog breeds are encapsulated within SNOMED. And yeah, I mean, if you're an epidemiologist, you have such fun games trying to find the most hilarious ones. For example, injury caused by debris from a cargo plane. Very common. The important thing about SNOMED is that it is a tree. Okay, so the numbers actually don't correspond to anything understandable. They're not grouped together, but they are arranged in a tree in terms of there's a SNOMED kind of reference guide. So this is a simple example. We would have diabetes, and underneath it you'd have type 1 and type 2 diabetes. Okay, but I lie, because actually there are tens of thousands of different codes. And so this presents a real problem for epidemiologists and researchers who are trying to find all of the people who've got pneumonia, okay? Because there are many different ways that you can represent pneumonia in the data, essentially. So for example, cough, cough is pretty, you've got a cough, right? There are 43 different ways that you can code a cough, including, helpfully, absence of cough. And this is a terrible website, sorry, NHS Digital, where you can look up different codes. It's very slow, and yeah, there's lots of repeated data in it. But you can see, if I type in pneumonia, it's not obvious, but it comes up, it matches 2,274 matches. Okay, so what is a code list? So a code list is a way of representing a disease state. So if I'm doing a research study, I want to find all of the people who've got acute confusional state. I need to create a code list which essentially allows me to find all of the ways that that could have been coded on someone's medical record. And because we're dealing with such huge data, we can't just go and look for it. We have to do it in some, we have to go and find those codes and then run it through the data. Okay, so this brings me on to sort of the fundamental crux of why I've done this project, which is, how is this done? So pretty much any way that you can imagine this has been done. There is no set way of generating, saving, sharing these code lists. When I first rocked up in epidemiology and did my first research study, it was very much like, well, just talk to Sharon up the corridor. She probably has a code list, and maybe she'll send it to you, but you have to put her name on the paper, that sort of stuff. So they're sometimes they're text files, sometimes they're CSV files, sometimes they are printed at the end of a paper, really helpful, or on a PDF, okay? Or sometimes they're just absent and you have no idea. And this is really important because we want our data, the data that we produce, to produce good science that's reproducible. And if we don't know what they've used to generate that data, it's a real problem. Now, there are a couple of notable mentions. So sometimes people do put them on GitHub, and I've been, along with lots of other people, really making a push for people to put it on GitHub. And then there's also this other project, Open Code Lists, which, full disclosure, I was involved with when I was at Oxford, where it's that website where you can see them. But it is kind of slow, and it doesn't have everything. So this is a problem that I've been trying to sort of solve in some way for quite a while. And I've come to the conclusion that what we need is a standard way of doing this, that you can output something, a CSV file, preferably, with a comma, not any other variation of what you might want to put, like a tab, again, I look at you, NHS England. And we want it to essentially have like a consistent way that you can generate this data, you can share it. And what I ideally want is that the pipeline for producing that code list is essentially encoded within the code list itself. So it's part of the metadata. Because sometimes you get something like, imagine someone's emailed you a code list and you're like, well, it's great, but do I believe it? Why have they done it in this particular way? And often in those cases, you don't necessarily believe that they've got every code that you might need, and so you end up doing it again. So there's just a huge amount of repetition, whereas if we had a pipeline, that would just be removed because you could work out what people have done. The other thing I really wanted was a plug and play. So I really want a way that people can generate code lists in their scripts for their research study. So that's within their research study. But also they can use them in tools like a web API or a website where you could like look at them and share them even. Okay, so I'm starting out doing this project called Code List Tools. That looks like this. It's under it's an open source project, and it is essentially in this organization EHR Tools, which I just started because I was like, while I'm at it, hopefully we'll create some more tools. But Code List Tools, I'm just being optimistic. And so Code List Tools is the first one. Okay, and as I said, this is building on previous experience that I've had, and in particular, this project Open Code Lists, and this other, my first iteration of trying to solve this, which was a project called TRE Tools when I was at Queen Mary University, which I think I made a bit too complicated because I also tried to do some of the data cleaning aspects of it as well. Okay, so the structure. The structure is this. Well, this is the plan anyway. We have a Rust base layer, which is basically small testable packages that do one thing well. Okay, for example, managing the metadata around code lists, or validating that the code list actually contains codes that are real, or a way of editing it or mapping codes. But I don't expect everyone to learn Rust. In fact, most epidemiologists and researchers, they write code every day, all day, but they would never consider themselves software developers. They are statisticians. They would say, no, I just play around with Python or R, but I'm not someone who writes code. And so we need to make the sort of how they interact with this tool useful for them, and for that it has to be in a language that they use as part of their normal everyday life. And that is for health research is going to be Python, or it's going to be my nemesis R. See, other people have interacted with R. And so the idea is that we have these bindings that allow you to call under the hood. It is calling the Rust implementation of it, but the person using it doesn't need to know about that. Okay, so the first package that we have is just imaginatively called code lists. And this is a central data structure which represents the medical code list. Essentially, it contains the metadata, the codes, the type of code list. Because I've talked about SNOMED. There are several other coding systems as well. ICD-10 is the other sort of really popular one. And this allows you to, I've written some Rust code here, but it allows you to create a code list and then add codes to it, and it does a lot more than that, but my space was limited. Although I didn't realize I was going to have such a big screen. Okay, there you go, a bit bigger. And so this is allowing us to create the contributors. We can work out, we can put in this is where I got the original bit of information for this code list, I manually created it, or I got it from Sharon up the corridor, or whoever. And then really importantly, the purpose and context behind it. So there's been this research paper that has come out, or I guess it isn't really a research paper, more as an opinion piece, where it's saying what information do we want to actually collect about our code lists. And so the middle section, which is dealing with metadata, specifically references the things which have been highlighted in this consensus paper. That's the word I was searching for, consensus paper. And then you can save it. Okay, and then hopefully this has come out. So this is a machine printable version of a code list, which I hope is much more readable, and you can imagine that you could input this in and send it, or like this would also allow you to put it onto a website because it's just JSON, and you can add to it. Okay, so let's come on to the Python bindings. So here we have the Python implementation of this. I opted to use PY03 and for Python specifically, and this is a Python wrapper that essentially is pretty basic. It's like a meta big object essentially, and it allows you to create a code list. Essentially, you're creating it in Rust under the hood, but you don't need to know anything about the Rust implementation. And this is the first time I used PY03, and it was a pretty good experience. It has its own like particular ways of doing things, but once you get the hang of it, it's relatively simple. And the bit on the right is some simple Python code, and this allows us to just import the code list and then add the sort of information that we want to add, like adding a contributor, adding a use, adding some codes, and then we can just use it like any other Python code. Okay. So the second library that we've added is a codeless validator. So when I worked at Oxford, we were doing a lot of the COVID data processing, and you know, when you're dealing with like millions and millions of data, like rows of data, it takes like 8 hours for the analysis to run. So we really need to make sure that any code that represents a disease state, a code list, is valid before it even hits the data, because otherwise it's just a waste of everybody's time. And so this was something that I really was like, oh, we should have this. And unfortunately, we never did, but I think it's something that we should definitely have. And this is quite easy in a sense, because all of the codes have a particular set of rules. So for example, ICD-10 it has to be 7 characters or less. The first character has to be a letter. The next 2 characters are always numbers. Then it might be a dot. If it's a dot, there's always a number after it. If it's a cross, it stops, etc., etc. Okay, and so we can just allow for that by using a regular expression. Okay, so in progress. How much time do I have left? Oh, you can just say it. It's 13. 18. Oh, 18. Okay. All right. So what I'm working on at the moment is kind of a big project, which is a codeless builder. Again, this is something I've been wanting to do for a while. It's not there yet. I would love some help with it. I have this theory that the amount of time that we're spending writing these code lists basically could be not quite automated, but massively sped up by just doing some sort of keyword search. So I want to build a builder where we can search for a term, like diabetes, type 2 diabetes, and it will find all of the codes. It finds similar codes, and it also finds, you can specifically search by a particular code. And the builder is kind of an interesting problem to solve, because it's not as simple as just creating a binary where you've just encapsulated, like essentially put SNOMED and like plonked it into your project, because SNOMED is under license. And so you have to sign the licensing agreement to be able to use it. And so what this project needs is it needs a way that you can use this library and then download SNOMED yourself and say, like, okay, here's where it is in my computer, build me the codeless builder. Okay, and this is what the data files look like. Well, it's actually considerably more than this, but this is the useful part of SNOMED, where there's concepts, there's descriptions. You need both. And usefully, the description is not with the code. for some reason. And then there's also a relationships. One of the files is a relationships file, which tells you how do things associate with each other. So that is coding in that parent-child relationship for like type 2 diabetes and type 2 diabetes with complications, for example. They're massive files, and well, they're not actually massive files, but they're very long in terms of the data that is contained within that. And it's something that needs to go in correctly, but there's also a lot of useless data that we just can chuck out. Okay. So why did I do this? What did I want to achieve from this? I wanted to have a data structure that would allow us to essentially query the builder, as you would a SQL table, and also allow some graphing and querying of that graph. And so I've opted for SurrealDB as a backend. And this allows us lots of interesting and fun possibilities because we can also use some of the vector search capabilities that they have for finding words which are similar to other words. So yeah, we can talk about that at the end perhaps. So this is how you can load some of the data into Surreal. So I'm creating the concepts from those text files. That's just via struts. And then I essentially then create a relationship between those different concepts within Surreal. And once we've done that, this is a very small example. I've only put in 10 codes, otherwise it would be massive. We can then look at all of the different relationships, and you can see that there is a graph, and at the top of the tree there'll be, maybe endocrine disorder, and then underneath that there'll be lots of different types of diabetes or whatever. Okay. Here I've got a function which I've written into the database so that you can get child codes. What's really nice about using Surreal is because it is in Rust, it's highly optimized. So it's so quick to get the child codes of, say, diabetes. Okay, upcoming projects. So that's what I'm working on at the moment. So my next thing is a wish list. So I would really love there to be a way that we could interactively adapt and edit the code list. That would be obviously amazing, more so than just editing the metadata. I also would like one day, and hopefully someone in the audience can help me with this, a way of creating an app that allows you as a research organization to point at a particular place on the shared drive and say this is where we keep our code lists, and an app to open up. That, in an ideal situation, this would just be a website. But what I've learned from working in this space for a long time is people don't want that. They don't want to share their code lists openly, certainly not during development. So they might release them at the end when the paper is done, but they don't want it to be open access all the time. Obviously, some people do. And that was one of the big problems that we had when we had open code lists, is it was just open to anyone. And so we need a local solution. Adding in the R API is a next big project. It's kind of tricky because you have to go through C, but now I'm feeling inspired from the previous talk, so maybe I'll be able to do it that way. And then also some documentation website. Cool. So yes, please get involved. It would be great if you have any range of experience, thank you. So expertise in Rust, I think you probably all are experts in Rust. And then particularly if you have expertise in R, that's my nemesis, but we need to do it because that is what people are using. And Python, even if you've never really written any Rust, come and talk to me, and we can get you involved, even if that's just doing some documentation while you get used to the code base. And it's an open source project. So it's a nice way of being able to show off some skills. Okay. So lessons learned. So I think one of the key things that I learned was like I needed to really start from the API first. And I think initially I had a fixed idea of what the Python implementation should be like. So I was thinking, oh, we would basically use classes in Python, and that will be easy because everyone knows what a class is in Python. That's very much not the case. And so I needed to really simplify it. And so I'm very lucky because I still have a foot in the epidemiology space, so I'm able to just talk to people who I know and engage with users. There's sort of like 3 universities that already said that they'll trial this for us, so we're going to get like a very quick iteration with feedback. Understanding your users is so key. I know that everyone says that, but I think it is really, there's nothing as discouraging as writing a tool which no one uses. And so, I would love to cut R out completely, but we need to do it because people are using, like a lot of epidemiology research is now using R. In the past, people, like when I trained, we used Stata. And I sort of didn't really know very much R, but that's very much changed, which is a good thing because people have moved on to more of an open language rather than one you have to buy a license for. But it is something which is not maybe the easiest language if you come from more of like an object-oriented programming language. It's very functional. And I could have used the C interface to do this. But the code also needs to be really understandable to users because people will be interrogating it, the code base, and being like, oh, is this doing what I think it's doing? And you can have tests, but people like to eyeball the code. And having a decorator saying this is a method is much easier than having to look at C code. So that was the reason for that. So yeah, as I said, it's been great to engage with some early stage developers within the Women in Rust community, but it is open to everyone. And using the sort of graph and SQL capabilities in one place is really cool. I've previously worked on a project, well actually the company that I run, we have a project, like our main product, we have all different types of databases for different capabilities. So it's really nice to just work in one place. And kind of a bit of inspiration I hope to give to you. A lot of Rust developers do come from science backgrounds. As a show of hands, who did like a science undergraduate degree, master's degree? Yeah, a lot of people. Okay. And I think that what we can do is we can help bridge the software and science. And what I've observed is lots of people are working in the science space and they're doing their own thing and they're doing it really well, but it's a very competitive field. They've got to get funding. They've got to produce papers. They're not necessarily rewarded for implementing a package that everyone else can use. And so people are doing kind of their own thing. And so what I really want to do, because I've got the time and space, this is very much a side quest. I can help build this new way of doing codeless tools. I can also help people who are trying to get started in Rust. And hopefully we can create kind of a better set of tools for epidemiologists and researchers to use. Yeah. And that's it. Thank you.
Very, very nice. Thank you, Caroline.
Thank
you. Very inspiring.
Yeah, go find some questions, I guess. Who's got questions? I see one all the way at the top. There's a challenge.
Hi. My question is, are these things like SNOMED, are they, you said you need a license for them? Does that mean it's a restrictive license?
No. Oh, sorry.
Sorry, go on.
It is a license that you have to sign up for to say that you're not going to do anything bad with them, basically. I don't know what you could do bad with them. But yeah, so you can, it's used in commercial solutions as well. So obviously the people who hold the electronic health record data, so the data of your GP records and stuff, they are for-profit companies. So they they have access to all of these tools. So yeah, but you yourself personally have to sign a license saying, I agree that I will download this.
So it's like Pantone, but for symptoms.
Maybe.
Pantone colours, but for symptoms.
Oh yes, but like imagine, I don't know, are there more SNOMED codes than colours? Possibly. Who knows? Maybe all of the colours are within SNOMED. Yeah, I mean, there's so many.
All right. There was a question all the way up there. Where's the
yes,
just throw the box up?
Can I ask?
Sure.
So these codes, I don't know anything about the medical codes. Are they, how universal are they? Are these only like UK? I mean, yeah, are these only UK codes? And in other places there are other standards, or how is it? Are they universal?
Yes, so they're relatively universal. Actually, that's not true. They're not 100% universal. So SNOMED is a international standard, and then each country has their own edition of SNOMED. So the UK version has like some specific things that they don't include that are in international SNOMED, and I think you can also add stuff into your own local edition of it. ICD-10, which is what hospitals in the UK use, is a WHO standard, so that's very much used across the world. But yeah, SNOMED is used in many, many countries. And the code, the names of the codes don't necessarily change between countries, and they shouldn't, in theory, replace any of the names of it, although there was a bit of a whoops about one of the COVID codes, but never mind, a story for another day.
All right, I think the box is almost
Yeah.
Yes,
all the way in the
there it
back
is.
there.
Oh, wow.
Yeah.
Very nice. Yeah, so I was curious about the codes. You mentioned the code list builder was something that you were interested in. You'd mentioned that these codes are a tree, so can you imagine it that if for pneumonia you have 12 codes, you'll have one parent code for pneumonia and all 11 others are subcodes, so you can just traverse the graph? Or is it a bit more fuzzy? Because something you hadn't mentioned was using some sort of statistical methods to do the searching. So maybe you have like semantic embeddings, and then you know that maybe the cough code isn't related to pneumonia. It's not a subcode, but there's like semantic similarities, and you can like train a model. So yeah, is it all just through these graphs or that you're going? Can you be certain that there's a tree, or do you have to be able to expand your search to things that are maybe not in the tree?
That's a great question. And so it's not as simple. So the first part, it is fuzzy because some of the codes aren't. So like, for example, absence of something is often nested under the thing that it's an absence of. So like absence of cough might be nested under cough. So it's not necessarily enough to just say, oh, we want all of the child codes of this. There are also, it's not just like cough would have one layer of children codes underneath it. It would have like grandchildren and potentially great-grandchildren. And so you need to be able to get them all if they're relevant. And then there's a lot of effort manually put in at the moment to deciding what is relevant for a particular research paper. So, for example, if I'm doing a study where I'm looking at cough, and I'm actually, let's make it kind of more, say I'm looking at like pneumonia, or and I want to see like how quickly does it take from the first time you have a cough until you get diagnosed with pneumonia. Then it's not enough. I need to find everyone who's got a cough. But what I don't want is all of the people who are like allergic to their dog, or they have some other reason that they're coughing. And so that would definitely be under the header of cough, but it wouldn't be relevant to my study. And so there's it's not as easy as that. To your semantic search thing, that's really what I'm trying to achieve with the next iteration, which will be the vector search side of trying to find these things by name. So what I'm imagining the builder is going to end up being is that you can say, like, pneumonia, find me all of the codes which are relevant to pneumonia, and then you overlay on top of that, removing absence, and then also find me similar codes. And so that is something, again, which is manually done, which even if it's not perfect with the automatic solution, it will be a lot quicker than having someone sit down. I mean, I've spent hours and hours writing code lists, so I don't want to do that anymore.
Fair enough.
Oh, and they also usually have to be signed off by 2 people at least, so it's a lot of person hours.
So also just having this as sort of a script that you can evaluate is much easier than looking at the full list. And
Exactly.
auditing it.
Exactly. So what happens at pneumonia? At the moment, I've got pneumonia on the brain now, but I am going to use the example of pneumonia. Say I wanted to do a study and I wanted to find all of the people who've got pneumonia. I might put in pneumonia, right? But I know that lots of doctors think that, and I think lots of patients actually, think that the word pneumonia is scary. So they'll say things like, you've got a chest infection, or you've got, whatever. And so you then need to also have that knowledge to be able to say, okay, I also need to find all of those codes which are lower respiratory tract infection. And so I have to have that knowledge, whereas I would suggest that if you did a vector search, pneumonia and lower respiratory tract infection will be pretty close together. Right. And so we can kind of use that. That's the plan.
You need to really be in touch with your user base and understand how people are describing things for you to be able to catch up on that.
Yeah.
Should we do a final question? I don't know where the box is.
For 1 second. You say vector search. Is this like a word embedding is what you mean? Something similar to that?
So I missed what the first part of the question was.
Sorry, you said vector search.
Yeah.
I assume you mean like, you're embedding words into some and then similar. Okay.
Yeah. That was the plan. Do we have any other questions? That was such short and sweet, so.
It was good. I would just like to say that I love that you're sort of bringing that open source mentality to science, like sort of a more open sciencey kind of thing, especially with the open code lists and publishing every part of the research is so important for making it replicable and that just so good.
Thanks so much.
Nice.
Shall I put this up so you
One last
can...
question. Yeah.
It's gone.
Where's the question?
So you mentioned that you're looking for some open source developers to help with this tool.
Mm-hmm.
More generally, are there any other places you recommend for either researchers who are looking for some developers who have some time to help, or people that want to do some useful development in their spare time to find tooling that's missing?
Oh, that's such a good question. We should invent that. I don't know specifically off the top of my head. I think if you did a search for open science tools, you could probably find something. But I would also encourage you to look at your colleagues or your personal background. A lot of us have come from science, so what were the specific problems that you were trying to solve back when you were a scientist that you could maybe bring some of your current knowledge? And it's really nice, actually, because you get to essentially kind of keep your hand in and have conversations with people that you really love working with, and hopefully you're doing something useful for them. And because it's open source, it doesn't have the pressure of my former academic life, where it's I've got to get this out before this paper is due. I would encourage you to sort of just look around. And can we put the thing back on so I could just share the QR code for... I don't know how to do it, sorry. It looks really massive from here. Oh yeah, so if you scan this, it should have a bunch of links so you can learn about GitHub and then Women in Rust and some websites. Pardon? Really? Interesting. Okay, I will sort that out and maybe send it somehow.
Anyway, where they can find you?
You can find me through, I have a website, so carolinemorton.co.uk. You can find me on LinkedIn, and I can give you all of this information. We're always looking for speakers for women in Rust. You do not need to be a woman. You can come and give a really good talk. And there's lots of people who are in the community who are really keen to help. And yeah, come and get involved.
All right, thank you so much.
Thank you.
All right, we'll have a little bit of a room change.
Yeah, people can move in and out of the room, and then we just need a couple of minutes in order to set up the next laptop for the next presentation, which includes audio. So it'll be a bit finicky.
You can drop it.
We can make this work.
It doesn't yell at you.
I
think I'm like throwing it a little bit too much. I'm scared of throwing it. I have the opposite problem. Oh, right. Oh. Right, someone's handling it. Yay. See? That was the correct answer. Yeah.
I'll take it out of my framework again.
Things are good.
Grit and persistence.
And lifetime errors.
Okay, let's give it. Oh, I'm off.
How many
Yeah, that should be off. Okay. Yeah, I want to say one more minute. You know, that's not happening now. Can I have the mic back? 1, 2, 1, 2. No. Yeah? Okay, there we go. Yes.
Hello.
We're still listening to jazz. Or, well.
All right,
it's
we're
very soft,
gonna
right?
continue.
For the last presentation in this section, and then we're going to have another break. I saw lots and lots of soft drinks downstairs. So apparently that's what's happening. Maybe even
It
a
is.
snack or something like that. I don't know. Next up is Stephen Buchanan. He lives in Haarlem and he works in Amsterdam at the Random Studio, right? Not a random studio, but the one. Talking to us about creative coding. Because you are a motion graphic designer. And
video editor. Yes, I used to be. I used to be.
Okay.
A while back.
Take it away.
Taking
Thanks
that
a lot.
experience with you.
Okay,
Go
thank
ahead.
you very much.
Give it up for Stephen.
Thanks. So yeah, I have the pleasure of showing you a lot of pretty pictures because that's kind of what I do. I'm going to try and answer two questions. I hope I succeed. The one is, what on earth is a creative technologist? The answer is, I don't actually know myself, but I'm going to try. And what has Rust got to offer this niche little industry? So I say I don't know what a creative technologist is. The first time, apparently I was doing it for years. Back when I was in South Africa and I was working as a video editor and I was doing a lot of motion graphics, always had an interest in computer science and programming, and I ended up doing a whole bunch of, I moved from that kind of media to online things and all kinds of gimmicks and experiences at events and so on, and that became my job. The first time I heard about the term creative technologist was a few years later when I applied to a position for a creative technologist at the place where I have been working for about just over 8 years now, which is Random Studio. It's based in Amsterdam and also in Paris. And it's an experience design studio, so very much coming from the design, media, marketing, branding, all of those things. So the way that I understand creative technologists now and what they do, what I do, is being that bridge between the creative industries. So that can be media, it can be AV, it can be branding, all those things. And then also the technology side of things. So the other way of looking at it is that I've got to take the really wild, crazy ideas of the creative people, and I've got to be the one to actually make it happen, make these things actually work. So just to give you a few examples of the kind of what actual projects I actually do on a daily basis, it's quite a wide range, and sort of what sort of technologies it tends to touch. So these things can be online, they can be websites, they can be something that lives in a specific space. It could be an exhibition, almost like a museum type of experience. They can be digitally augmented architecture. So in this beautiful image, pretty much everything you see is real, but the view through the window is a rendered scene, a live rendered scene. Sometimes it can be making an actual game, although not the kind of game that you're necessarily going to release to the public, but it might be living in a store. It could sometimes be performance art. Sometimes it's all about light purely, and sometimes it's all about sound. And sometimes it's about music. It can be about generative music. It can be about video, live video, playing with video effects. And it can often be, it can touch on electronics as well. So it can be motors and sensors, and it can be microcontrollers, and it can be Raspberry Pis and all those kinds of things. So from that little brief overview, you kind of get the idea that, wow, this is really exciting. It is a fun job. You get to play with something new every single day. And you're going to come up with something new every single day, you know. So there are a couple of challenges of doing this job. It is very fun, but it's also the kind of thing that tends to be. It's easy to underestimate how difficult it can be to produce all this kind of work a lot. And clients are paying a lot of money for this stuff. So some of the challenges that are unique to my role, and I'm going to try and relate these to how Rust has, at least for me, addressed some of these unique challenges. So it's very much a project-based thing. You're not working on a product that lives for years and years. You are doing a new thing every time a client or a creative comes up with a new idea. Which is great, but it means that it's very difficult to evolve things, and you're always reinventing the wheel all the time. Everything has to be unique, everything has to be custom, everything has to be something that nobody's ever seen before or done before. So it's very hard to find the tried and tested way of doing something, because often there isn't exactly that. There are bits and pieces and you've got to kind of combine them together. There are some insane deadlines. Unfortunately, that's kind of coming from the rest of the creative industries. So you might only have a few days to make a prototype of a key part of what you're supposed to do. Hopefully you have a few weeks to finish a final project. If you're lucky, in some cases it can go a few months, but that's about it. There's not a very good distinction between what is the prototype that you build in the beginning and what actually ends up becoming the final product. That's the problem. And you've got a very wide range of like how long these things actually live. So sometimes they can be a day or two if it's for a product launch or an event, but it can range all the way through to things that are semi-permanent, that actually live in a store somewhere for years and years and have to run 24 hours a day for weeks on end remotely, and you need to be unattended. So there's quite a difference in how long they can actually last. And then don't be fooled thinking that, okay, that's, you've got all this rapid turnaround, so everything is just frivolous and fun and it's all great. The other side of it is that you have big screens, you have big speakers, you've got lights, you've got sound, you've got the thing that is open to the public from day one, open to the client from day one, has to work flawlessly the moment the doors are open until it's finished. Often you have the media showing up on day one as well, so there's very little room for error, actually, and things need to actually be quite reliable. So yeah, well, the last thing you want is a 10-story high blue screen of death. Yeah, so I am going to have a look at how maybe Rust, at least for me, has tried to address some of these challenges to my little niche industry that touches on all kinds of industries out there. So what sort of tools are people like me currently using? A very famous one is called processing. It used to be Java-based. It's now a version of it is very popular, P5.js, which is a JavaScript version. And it is built around the concept of these, it calls this program sketches. That gives you a sense of like, yeah, it's something you can just try out an idea. It's very visual, it's very interactive. It allows you to get something on screen to play with really easily, and that's great. It's also extremely slow, and it's very hard to take this, which is great for making a hobby project, and turn this into something that you can present to a client and it's going to work for years on end without any problems. Then if you want to get more serious about it and you want it, and it needs to be faster and etc., then you have things like Open Frameworks, which is a C++ based library specifically for creative coding. This is not fun. For me, doing a lot of C++ work with Open Frameworks specifically was a major motivation for looking elsewhere to see if there was some other way to do this. C++ always makes me feel extremely stupid. If you're a genius, then I think this is going to be great for you, but it never made me feel comfortable. I always felt that there's something I'm not thinking about here, but it is fast. So the other thing is that it's like Open Frameworks, for example, has its own way of doing things and its own kind of little bits of packaging systems and things like that. So, but as soon as you move outside of that ecosystem of things that are made to work with Open Frameworks, then it's very, very hard, and that's partly because of C++ and all the different build systems and the whole thing around it and how big and complicated it is. It's very hard to just grab something, to make a new piece of hardware work or whatever. So that's very frustrating. And then, yeah, you also have a lot of, for those who, obviously, a lot of people like me are sort of stronger on maybe they come from a design background, or they come from, they're more of an artist rather than a software engineer. So there are a lot of tools out there that are not necessarily low code or even no code. So visual programming environments, a very famous one is Touch Designer, it's a big software application, and you can connect things together, boxes together, and everything's visual. There's also VVVV, and an online version or browser-based version is CablesGL, which is actually really good. And then finally, a lot of creative technologists are using game engines to not necessarily make games. Okay, so why would I not settle for something a bit easier? And I think I've touched on it a little bit, but this idea of having these tools that are easy for artists and designers, there the focus is, make it very accessible, make it easy to get going, make it easy to put things on screen. Provide ways to prototype things so that you can get feedback early, so you can have some happy accidents, so you can have fun building things. It's very difficult to get it from that to something a lot more reliable. The other thing is that using something that's already out there, that's been built by somebody else, you have to live with all the poor design decisions. You've got to live with all the legacy issues that it may have. Sometimes you will find that certain things are very easy to do, and suddenly something that you assumed would be easy is extremely difficult to do, and it's not your fault. It's just because it's just something that the designer didn't think of. So with Rust, I kind of, I gotten into this area of making things because I enjoy building stuff. So I really wanted to. I get a little frustrated if I'm only having to rely on other people's tools and other people's designs. So with Rust, it meant that I could kind of go back down to the basics in some ways and really enjoy actually building small programs that could do one thing really well and cobble them all together, but they could be really fast. And I also didn't have to reinvent the wheel all the time because there were such great crates out there that I could just easily install. I didn't have to deal with C++ dependency issues and things like that. So that was made a big change for me. Then I'm going to show you just one example from a very recent project, and I'm going to sort of try and point out like where Rust fitted into this particular one. It's not the only use of Rust that I have, but it'll just give you an idea. I'm going to play a very short video. It just gives you an idea of roughly what this was about. So this is for a beauty products brand, Glossier, and they were launching a new perfume in Paris. So this is the video.
In Glossier's pop-up, the large language model is instructed to be a poet, making loose associations between the visitors and the new fragrance of Glossier.
You stand, bathed in soft light, fleur glints in your hand, your stance quietly confident.
Random's Living Lab is looking at the future of living spaces.
Okay, so it looks very pretty. You see all kinds of stuff happening there. There's sound, there's lights, there's a sensor when you pick up the perfume bottle, when you put it down. We use a large language model to take an image of the people, whether it's one person or many, try and notice something about their clothing or their style, and then incorporate that into a custom, like a personalized poem. That then gets projected onto a piece of fabric, which is very nice experience, very pretty. So I get to be the person that's going to explain what on earth is going on here, how does all of this actually work, how does it all fit together. Behind all the things I'm going to show you, because there are lots of pieces to this, and a lot of them are written in different programming languages, and they're using different pieces of software. So we developed in Random Studio just like our own in-house. It's basically like a messaging protocol. It uses MQTT, which is used for IoT devices and things like that. And we developed a lot of, it's just a way for programs to talk to each other, whether they're on the same machine or whether they're on different machines in the network. And that allows us to have this really nice way of being able to send messages around between different pieces of hardware and software. And we built, so a lot of the stuff that I'm going to show you, although they may not be written in Rust, a lot of the tooling for this system Tether, which includes being able to record data, play it back, simulate things, being able to troubleshoot stuff, see what messages are going on in the system. All of that all of those command line tools and graphical tools are actually written in Rust. So you'll have a thing like this. I called this like the most over-engineered kitchen scale ever made. It's just a lifting sensor. It's a weight sensor. This is C++ code running on a little Arduino microcontroller. It connects to a custom piece of software. Now, this is written in Rust. It's got a GUI, but it doesn't need the GUI. It can run without it. It can just run from the command line as a process. But building little tools like giving it a graphical user interface is really great when I'm working with a designer or a creative that is not doesn't want to look at code at all, but it allows us to have conversations about, so what this brain is doing is it's taking in the sensor data, figuring out when you've picked up or put down the bottle, and then it's giving instructions to the rest of the system about when do I need to change the sound to do something. When do I need to change the lights? When do I need to take an image to generate the poem? When do I need to render the poem up on the screen? When do I need to clear away the poem, etc.? So all of those timings and those kinds of state things are managed really nicely through Rust. And because this thing is sitting at the core of the entire system, it means that having a strict language like Rust means that I don't have to worry that I'm going to get lost in some weird state, because that sounds like it's not a problem. But when you have a client that has spent a huge amount of money on this experience that's open to the public, you just can't afford for the thing to be stuck in some weird state somewhere, because you're not always there to go and push the button and restart it again. There are some web parts of this. So there's one route that is doing the actual generation stuff and passing things off to OpenAI to generate the poem. We have our own special prompts and so on. And then there's another part of the web application that's just doing the rendering of the text and doing the nice animations and playing back the audio of when the narrator it does a text-to-speech thing and then reads it out. Then we've got another part that's written in Rust. This is just a small application, and this has been reused in a couple of projects. It's a sound sequencer, but it has a very simple job. It's just to loop sounds, to fade them in, to fade them out. But it can be given, because of our Tether system, it can be given very simple messages. Here's a group of sounds. They're named this. It's a scene. Play these now, or transition to this group of sounds now, or fade this one out over 5 seconds, etc. And this is all remote controllable. And again, it's got a GUI, but it can run without the GUI as well. But it's useful to have the GUI so that when you are discussing this with the sound designer, you can figure out, okay, so you mean the sound must play like this now, and you push the button and try it out. There's also lighting control. So you saw that you might have seen that there were quite a few kind of moving DMX like stage lights kind of fixtures. I think there were about 5 in this particular project. But again, I've written a piece of software that handles all of this DMX control, because every light fixture has its own list of usually 500 different DMX channels, and they all do different things: zooming and blurring and panning and tilting and changing colors and all this kinds of stuff. So this allows me to group those, what it's supposed to do, into scenes and then animate between them and so on. So this is also a reusable piece of software. Yeah, so I mean, basically what happened is that this is increasingly the way that that we build these types of installations, is that we break them down into small pieces. We make a kind of a distributed system of all these little things that need to talk to each other, that all get orchestrated together. Some of it is custom built now for that specific project, but there are a lot of pieces, like you've seen, that are actually reusable. And this is amazing for a creative technologist, because usually you just don't do that. You end up reinventing the wheel every time. So finally, I have these little applications that I can make better over time. because they're written in Rust, I've got this really fussy compiler that if I have my half-baked ideas, I've got to make sure that I really think it through properly, consider some things, and be really clear about what I'm actually doing, and then I can reuse those things. And yeah, that means that I have a toolkit now of applications that I can trust I can leave it running for weeks at a time. In a store that might be in Tokyo, and I don't have to worry that something is going to crash or do something undefined, because Rust has got my back with some of these things. So that is my experience with Rust, and I hope you found it interesting. If you want to see more pretty pictures and videos, have a look at my website, and obviously you can also look at the website of Random Studio. But thank you for your time. I hope you found it interesting.
Thank you so much, Stephen. Thank you so much. All right, let's do a couple of quick questions. I think we also want to go to the break, but let's do like 2 questions maybe.
Hey, I noticed C++ open frameworks. There's also a Rust framework called Nanu, I think. I was wondering if you had experience with that, and maybe you could shed a few words.
Yeah, so I have used a project called Nanu, which is also very much sort of inspired by processing and open frameworks. I have used it on one project successfully, and it was great. I think that 2 things happened. One was that it lost a bit of momentum at some point, and that was not that helpful. But on the other hand, I also found that because of the way Rust programs can be built, you don't necessarily always need a whole creative coding framework ready to give you all those tools. There's lots of little bits and pieces that you can draw from to just get enough to do the job that you wanted to do anyway. So yeah, I found that I could do a lot of the things where I needed visual output. I could use something like eGUI, like an immediate mode GUI, and otherwise So I'm aware of Nanu. It is very nice and it is very useful. It's not always the right tool for the job for me.
All right, next question over there.
How could Rust change the language to be better suited for these creative technology tasks? Or you have choice of question.
Yeah.
Or what one single crate that doesn't exist now that you'd really love to see to support this kind of work?
I guess what would probably be useful is maybe for those that do need to prototype things quickly and are less concerned at that point about the final product, I suppose it would be useful to be able to, like processing did quite well, was they packaged like their own little sandbox IDE almost that allowed you to very rapidly, with very little code, kind of do the useful stuff, in their case mostly sort of interactive and on-screen sort of things, really quickly. And it might be useful to have that kind of thing, I guess, for creative coders. I think the nice thing about it is that then maybe you could take that sort of sketchy kind of code and then make it better if necessary later on. But that would probably be quite useful, I think.
All right, I think we should thank you very much.
Thank you.
And slowly move on to the break. I have a few things to say before we go to the break. There is if you want to experience a mixed reality Rust programming thing, or just play a round of Mortal Kombat, you can go to the MakePad area, which is right over there.
Yeah, I think it's right out the door here.
Yeah, right out the
You
door
walk straight
here
into it.
on the second floor. I think it's marked Event Zone, and Rick Arends of MakePad will be there doing lots of crazy stuff. And then also there's been a last-minute addition to the schedule for this last segment that we're going to go into. In the room that's for the industry track, so Cinema 9, there will be a second recording of a podcast. So there'll be 2 recordings of podcasts happening, one with Matthias Endler and Nico Matsakis, and then now also one with Luc van der Duim and Matt Campbell about accessibility. So do check that out if you want to. And with that, we have some well, we have break until 16:20.
Yeah.
So enjoy.
See you soon.
Thank you so much.
Thank you.
No, it's really nice. I
Check, check. Check. Ah, thank you. All right, we're almost starting with the last block of this day. Give everybody an opportunity to take their seats.
Yes.
Stefan, you're all set up, like technically, right? Ah, perfect.
This will be the last block.
Yeah.
Our last two speakers of the day. That's that's so cool. You already made it through the day. That went quite fast, actually.
That went like a blast. Unbelievable. So the first thing I want to do is do another round of thank yous to the sponsors. First of all, ARM, who's a silver sponsor. Thanks a lot for making this day possible. Along with Infineon, they also have a booth, so you can visit them downstairs. Thanks. They're also a silver sponsor.
Yeah. And they make all of this possible.
Yeah.
All right, I'd like to introduce our next speaker. Our next speaker is Stefan Baumgartner. He is a moderator at Eurorust, organizer of Rust Linz, so very active in the community. And he's also kind enough to be an MC tomorrow.
Yes.
Here on this.
Yes.
in this
Taking
track.
over your job.
Exactly. So he's coming for us. He also wrote some books on programming, mostly TypeScript. And I did have a question when I was reading through all his socials. He's using the nickname Dead Parrot.
Yeah.
And I was wondering, where does that come from?
So a couple of years ago, I was registering for two things in one April's night, which was I was registering for Twitter and for the last Monty Python shows ever to happen. So it comes from Monty Python, and I thought,
it's just resting.
It is based on a Monty Python sketch, and I thought, yeah, it's kind of fitting because the Twitter logo was a bird, so maybe use the same handle. Little did I know that this was the perfect foreshadowing, because we all know what happened to Twitter. So yeah, nothing more than a dead parrot right now. But, yeah.
All right.
Super nice.
That's a good story. Thank you so much, and
cool.
Please take it away.
All right, thank you very much. Okay. So, hello everyone. Thank you for coming to my talk. Thank you for this lovely introduction, which means that I don't need to introduce myself anymore. We can get directly to the meat. We are going to refactor some software together today. The basis is a simple key value store. It's a web application. You send some data via POST request and store it in some sort of database. And with a GET request to the same URL, you retrieve the data again. It uses Axiom under the hood, but don't worry, you need to understand any Axiom intricacies. You don't even need to understand web applications. We are focusing just on the Rust part here. The important thing is that in this scenario that we are having, we want to prepare our code base for future development. So product management is onto something like they always are, and we want our software to support their ideas. And this is why we want to refactor the existing code into something much, much more sustainable, because believe me, the code as it is right now is a mess, very intentional, because it was just hastily written over the course of a weekend. And as always, all the examples in this session are fictional, but rooted in reality to save the innocent, which is, I guess, me. All right. So before we start, we need to look at the code base at hand. And you need to be strong now, because this is not for the faint of heart. This is our database, ish. So, or actually, database isn't, I don't know. It's a simple hash map that stores a tuple of string and bytes based on a string key. And since it's a web application, the string in the value represents the content type we want to store. We are going to save that. And the bytes are the raw data. What's nice about this particular slide, and there's not a lot of nice things on it, is that we use a type alias to not always write arg, rwlog, whatever. We just have a name, a proper name for the things we care about. And this is the clicker. Okay, cool. And this is the main app. Those are two handlers that are mapped to the respective URL endpoints. In one handler, we handle the POST request that stores data along with its content type, based on a specific key. In the other function, getKiwi, we process a GET request to the same URL, returning the stored data if available. If no data is available, we send a 404 status code along with the error message. There are a couple of highlights. First of all, we apparently don't care about error handling. We have a couple of expects and unwraps in our code, which is funny because we are returning a result already, so why not just, bubble everything up? The nice thing about those results is that if Exum, the framework that we are using, gets one of those results, it will just convert it to either a success response or to an error response. And Exum needs something in there that can be converted into an HTTP response. For that, they provide us with the into response trait. This into response trait is already implemented for a multitude of basic types and also tuples of basic types, like we see here in the getKiwi function, where we cobble together some basic data to, get it done. But yeah, this would be it. If it weren't for the idea of product management to find a new product direction, they want to pivot our app, which is a very basic key value store, into an image processing app. Okay, this is not right, I'm sorry. This is much, much better. Now we are professionals. Now we can continue with our work. All right. Sorry, the clicker is acting up, don't worry. Anyhow, we already do have a feature implemented that we want to expand upon. So this is another endpoint where we create a grayscale version of every image that is stored in our database. So you give it a specific key, it takes the key. If it's an image, it creates a grayscale version. For that, we read from the database. Again, notice the unwrap. If we get some content, we want to continue. Otherwise, we return with a not found error message in status code. If the content is an image, we create a dynamic image. This is a type provided by the image crate, which is an excellent library if you want to do something with images in Rust. It basically does all the heavy lifting for us. It has a really, really nice API, and you have a multitude of things that you can do with it. And if you're not dealing with an image, we are returning a forbidden status code because we can't make a grayscale version of data that isn't an image. Once the image is received, we create a new buffer vector where we store the modified values and use the dynamic images as API to produce a grayscale PNG, which will be stored into that byte vector and converted into a response. So a lot of stuff is happening in those couple of lines. So this is everything that is actually the meat of this function. But yeah, a lot of stuff is happening, but eventually, I think it's fine. The code does its job. It has been hastily written. It lacks proper error guidance, yeah. But if we don't need to touch it and we're still, in the prototyping phase, then we are good. However, we aren't, because this should be a product in the future. We need to revisit our code base continuously and add new features or fix bugs or whatever. So let's make our lives easier. And the first thing that bugs me is the atrocious error handling, or actually the lack thereof. We basically don't handle errors at all, except when we produce a few specific status codes. We ignore a lot of the errors that could really happen and panic using unwrap and expect. And we need to do lots of manual response building with custom error messages. And this is something that we want to streamline. We want to streamline this error handling, and we want to make good use of the built-in error capabilities of Rust. And we do so by implementing a custom error type. So you've probably done this in the past, most likely with a library like this error. But here I want to implement error handling by hand and step by step, because I guess we're onto something here. Our type is called KeyVerror, and I suck at naming things. So, except with my children, they have great names. But here I really, really suck at the naming things, so bear with me. It holds a status code, which is a type from Exum. Like not found, forbidden, every HTTP status code that you can think of, and a string which represents the error message. And we implement a few functions on it. A constructor function that by convention creates a new structure. Note that I use impl into string, which allows me to add anything that can be converted to a string as a function parameter. I'm using into because the into prefix gives no indication of the conversion costs, whereas if I would use something like toString, for example, with toString, there's always a conversion cost attached to it. It's always an expensive operation. I'm also creating a few shortcuts, so I don't need to write every message over and over again. And this is everything our type has to offer. To make it an actual error, I need to implement the debug trait, which I can simply derive. I also need to implement the display trait, which I need to write by hand, but I just put out the error message. So now I can print the error on standard out and ignore it in the log file. And with those two traits, we finally get, and we can implement the error trait. They are a prerequisite for implementing the error trait. And with that, it's now a proper Rust error like it should be. Next, we want to make it compatible with the errors that could actually happen. And for that, we implement the from trait for every error type that can occur. It's possible, for example, that the database is corrupted and we get the poison error. And we want to convert that into a Kiwi error. Same for the case if the image can't be loaded or modified or anything related to the image crate, actually. This should also be converted to a Kiwi error. And last but not least, we implement the trait from Exum to convert this Kiwi error into a response, making every error case we have in our application compatible with the framework. All right, magic pixie dust time. Let's see where our refactoring has led us. So this was the main app, the get post handlers before our changes, and cool. And this is it afterwards. Not too big of a change, but we finally got rid of all the unwraps and expects and have proper error handling and error propagation. If something goes wrong, we just bubble it up with the question mark operator, and the error that we have will convert easily into an Exum response without us needing to do anything. And in the get case, we also make use of the shortcut methods if we want to say that we haven't found something under that key, returning an error here. The grayscale method itself looked like this, and it also becomes a little cleaner. We bubble up the error case in case the database crashes or the image can't be loaded or modified. And the most important thing here is that we don't expose any details, but rather hide the complexity of the error message creation and status codes in our shortcut functions. So now we have a name, now we have something that is tangible, something that you can take to your colleague and they know what you are getting, or they know what they are getting. Ultimately, we created a type that can be used universally in case something goes wrong. And I did do that by hand because I think there's a little pattern hidden there. So the interesting thing about creating this custom error type is that we unknowingly follow the pattern that is so common in Rust that I struggle to find a proper name for it. Maybe the name is just software engineering, but I think it's a core pattern. We need to apply to make Rust code easier and make it more maintainable for future changes. First, we create a type, and this is the most important one because suddenly we have a thing instead of a process. We don't talk about what we do, but rather about what is involved. And then we implement standard traits to make it compatible with the built-in language features. Then we implement library traits to make our type compatible with the crates we use from the vast Rust ecosystem. It's type, trait, trait, over and over again. Clicker. And let's see that in action with the next example. All right, this is the grayscale function as it looks right now, and I want to focus on this process where we create the grayscale image from our original image. And I said it already, a lot of stuff is going on there, lots of details happening. The problem is that in just a few lines of code, we expose much complexity that we even can't correctly name. We need to deal with vector buffers, cursors, content types. We load, we convert, we send a response, everything in those couple of lines. But you only know that because I told you. We see what's being done instead of what is involved. And if you wouldn't have written this on your own, or if I wouldn't have told you, I think it might be really, really hard to understand what's going on without any context at all. Let's change that again with type, trait. Let's apply this pattern and see where we get. I want to focus on the last line, on the sending of the response. I want to focus on how we create an HTTP response, and for that I create a new type called image response. And this image response stores the data I want to send. A tuple type is ideal for this purpose. It enables me to add my application's domain in form of this particular name on top of existing types. The constructor function takes an into bytes parameter, allowing me to convert any data that can be converted into bytes into an image response. Now I want to implement the standard traits. So I can convert the dynamic image I have from the image creation part earlier to an image response. I use the try from trait to indicate that this operation may be potentially problematic. Hello again, Kiwi error. Great that we did that. And in the conversion, I add all the details that are just there to create bytes out of a dynamic image. The vector buffer, the cursor, the conversion to a PNG, and since I use Kiwi error, I can propagate the error in the writing process. I do this for a reference to dynamic image and also for the own type, allowing me to convert it for many situations. So implementing standard traits, done. And the nice thing about it is that while it's still the same code as in the function before, we now know from its surroundings what it's all about. We want to create the response from an image, and that's the steps we have to do. It becomes clear by just looking at the function signature instead of going into the nitty-gritty details. So, and then we want to convert the image response into an actual exome response. So we implement into response for image response, setting the content type and the response body, and then call into response again. So this is exome framework code, but it's very, very handy. And again, we hide lots of the complexity in there. We don't need to focus on having what's effectively an array of header information, an array of tuples of header information, and then the bytes, and then calling into response. The only thing that we care about here is that we want to create or want to convert an image response, our own type, to something that Axum can understand. Implementing library traits, done. Again, pixie dust time. Let's see the magic happen. This has been our original. And no, it's just 5-6 lines of code, but there's lots of details in there, lots of implicit knowledge. And instead of writing this, we can just simply do this. We have the image, we call the grayscale method on it, and then we create an image response out of it. And since the interface from image response try from is the same as in our grayscale function, it returns a result of either bytes or a Kiwi error. We don't need to wrap anything in an OK or error or anything. We just can return image try from, image response try from image. And even better, since image.grayscale also returns a dynamic image, I can put it in one line. A simple single line that almost reads like English, you know. Try to create an image response from an image that is converted to grayscale. I think this is very, very elegant if you compare it to what we had before. But not only is it elegant, I think we have achieved something very important. And this was my aha moment. So when I did that originally, this is where I figured out, wait a second, it's important for us that we talk about what is involved rather about what is happening. This makes it clear why we do certain things to begin with. And Rust types of system supports you really, really well. You start thinking about what is connected and how it is connected. And I think personally, so this is now a little bit philosophical, but I think this was always the true promise of object-oriented programming. You have stuff that can talk to each other, and by the interfaces or by the contracts, you define how they should talk to each other. And yeah, and it's also nice to collapse everything into just one line and be done with it. Okay. Next one, the last one. I'm still not too happy with how we deal the type that we store in our database. So this is this part. We want to look at how we retrieve the data that we work with. And this piece primarily involves wrangling with different data. We perform all the necessary steps to ensure that in the end we are working with an image that we can convert into a dynamic image so that we can do the actual work at hand. And the problem here is that we handle the kind of data too late. So we want to pivot to an image processing software. So images should be the main focus of our app. Instead, we still work on tuples to figure out which part defines what. And we have lots of if-else branches that take up a lot of space for something very, very simple, like, well, is the key here and is it an image? So let's try it again, almost like a mantra. Let's try the same process again. Type, trade. We want to be explicit about what we store. We care about images first and foremost, so having an enum with two different variants is actually what we're looking for. An image that stores the type dynamic image and everything else, so this is perfect. This will do the trick. And if you want to be explicit about more things in the future, adding another enum variant is actually quite easy. When we create a stored item, based on the content type, we can already create the dynamic image that we want to store. Yes, this changes the semantics of the data that we store a little bit, but again, this is in purpose of the app that we want to support. At creation, we decide how we want to handle the data. We define the purpose of the data, and it's not an afterthought every time we want to work with the data. And we also get a central place to modify and change things. After the type, we implement traits. And this time, we don't need any standard traits, at least for now. But we can implement the library trait to make the stored type work with Axum. So here, we want to be able to return any stored type via an Axum handler. If it's an image where we don't do any modification, just create another image response. Otherwise, do the same thing that we did earlier, where we cobble together the content type, add the data, and call into response. So, how has our code changed now? It's actually a small change, but it has a big impact. This has been our original database, which is now working on a stored type. And this is, in my opinion, a huge improvement, because instead of having a tuple of things that can be anything, we know now what we want to store. If we look into it, we get more information on the variants. So we have a term, a noun, something to hold on and to communicate. This is the original storing and retrieving. Again, we also changed to a stored type, which, thanks to the into-response trait and proper error handling with Kiwi error, great that we did that, also becomes a lot simpler and clearer. So I like now that in the post-Kiwi, that we actually create a new data type and take care about where we want to store it later on. And again, error propagation through the question mark operator. It's happy path programming in Rust is fantastic. If doing it right, you don't need to handle any error ever at all. You just need to bubble it up. And even nicer is that in the getKiwi part, we just extract the element and send it back. Fantastic. Otherwise, we send an error not found. But the biggest change happens in the grayscale function, which is now in this state after the last refactor. So instead of this, we just reduce it to its most minimal version. We read from the database, we get the data, and if it's an image, let's do stuff. So we went from a large piece of code with numerous details to something readable and understandable. It utilizes terminology that aligns with our applications domain. If I give this piece of code to you, you are going to figure it out. You're going to figure out what's happening there, even if you don't have any context. All right, on to the finale. So I guess I'm very much within the time limit. All right. Again, why did we do that? We want to pivot. We want to have a code base that is maintainable, that has a certain longevity, where we can easily add new features. And if we find bugs, we know exactly where we want to handle them. So we had some smaller changes, we had some big changes, and it's time for our new product to shine. We want to go forward and implement new features. This was the original Grayscale function from the beginning. This is how it looks right now. So this is a huge, huge difference. It's much easier to understand, it's much clearer. The hard parts are somewhere else. The right abstractions can be modified and changed without needing too much, needing to touch every piece of our handler functions. This makes it great for adding new features. So let's implement a thumbnail function. Boom. There you go. Now we want to get brighter versions of an image. Boom. Here again. Look at that. So I'm basically just changing one meta call. That's all I do. It's the same piece over and over again. We just changed a single line. And basically everything that the image crate has to offer now can become a feature. And we are fast because we move the details into the right abstractions. We don't accidentally introduce copy and paste errors because everything that is process and ceremony is someplace else. Everything that happens in these functions is clear and unambiguous. There's some message in there. First of all, one thing that I really, really like is that we see all previous refactorings fall nicely into place. It was really, really good that we started with the error handling because errors can happen and Rust is a great language to avoid errors. So if you know which errors can happen in your software and you have the right types for it, this makes a lot of things for future refactorings much, much easier. With proper error propagation, we actually don't need to do a lot of error handling. We just call the question mark operator. It's also great that we started to store the dynamic image to begin with, and not just some bytes that we get, but we do the conversion before we actually work on the data. With that, the dynamic image being such an important piece of our code, all the other conversions align nicely because they already work on dynamic image. Some more sensible refactorings, like preserving content type for images, etc., happen on a type level and not on a handler level. And we introduced vocabulary that we can easily grasp, and we know what's going on. And this makes adding new features really, really easy. But, I want to stress the fact that we didn't do that to just create the most elegant code base of all time. There are so many people out there who can be really, really dogmatic about, polishing every little bits and piece of the code. This is a side effect. Having an elegant code base is a side effect of a much, much more important fact, namely that we do that to increase efficiency. Efficiency either by developing new features, but not alone, but also debugging existing features. Because understanding where problems happen. Because suddenly what belongs together is together. And with that, we can easily figure out if something goes wrong, where it is. And we notice one place where we need to touch it. And with that, to me, Rust type system supports or even fulfills the original promise of object-oriented programming. With different parts of your application that hold data can be glued together by defining the right contracts. And don't forget that code is communication. You want to write something that is understandable not for you, but for others as well. You rarely work alone. You rarely work on your own. And if you do, you always work with future you. So future you needs to pick up the stuff that you've written before. Be nice to future you. So make pragmatic decisions over dogma. Do the right refactorings because it helps you in the future and you communicate with others. A single refactoring technique, introducing a type, implementing standard traits, implementing library traits, type, trait, trait, is all you need to do to get the best out of your Rust code. Thank you very much.
Thank you so much. Thank you so much. Lots of good advice in there.
Yeah. Do I have one more minute?
Yeah.
Cool. Because we are in a cinema, I do some Avengers-style post-credit scene. All right. So, do you remember how I was annoyed about the database, that it isn't actually a database? Well, I make it a database by writing a database trait and implementing it on my shared state. Now it is a database by name, and I'm really good at naming things. So, and with that, putting all that stuff of getting an image or not getting an image into this trait with this getImage function, the grayscale function just becomes a one-liner. Image response derived from the image that I want to get from my current state. So now I'm having a database. It's database and something like that. But more importantly, if I now convert to an actual database, the code base doesn't change that much. I just implement the same trait for a different type. There you go. Thank you very much. Sorry, this was very important to me.
That's perfect.
No, that was great. That was great.
Questions?
I think you're the first one I've seen today who's used like slide transitions to great effect, or at all actually.
Still waiting for a 3D presentation.
Yeah. All right, let's see where the first question is. Is the catch box already on its way?
Yeah. Ario's completely ready.
I see all the way up there is one.
Yes, this is going to be the throw of the year.
Just it can go in multiple hops. It's fine. It doesn't need to go in one way.
Ooh. See? And this is how BGP works. Sorry. DNS and BGP is my life.
Yeah, when you hear hops, you just immediately go, oh, BGP, yeah. All right, what's your question?
Yeah, so I've only been doing Rust for a little bit, so my question is probably pretty newbie, but when I first started doing errors, I was doing a struct, and then I started reading blog posts that recommended doing enums. So now in your presentation, the error is a struct. So now I'm left wondering, are there different situations where I'm supposed to be using structs versus enums for errors?
So I guess the most honest answer to that is, use whatever you think is right. The great thing about using an enum is that usually you have lots of different errors from different parts of your application, like libraries, third-party libraries, or your own, that produce a certain type of error. And you want to convert that into your own error. So an enum is really, really great because you want to distinguish between those variants. And this is what an enum is for. So having the variant A from this crate, the variant B from this crate, whatever. In my case, this was rather special because in the end, I'm going to have an HTTP response. So I actually didn't care too much about what the actual error was, but rather about which status code to send. So every conversion that I did was not trying to figure out which variant it was, but sending the right message, which is in the conversion from poison error to whatever. I did an internal server error with a proper error message. And this was the data that I'm concerned about. So from that point onwards, Exum takes care, and Exum doesn't care if I have an enum with variants, because all it does is creating an HTTP response. So yeah, so the reality is it depends. Cool. Oh, I wanted to say that the entire time. It depends, that's like software engineering is, but it's true. Whatever works best in that case. I also used a struct with a tuple struct, and this is just because I like it more. But you can use a struct with property names and whatnot. So totally up to you.
Nice. Any other questions?
Let's see one over there. And the catch box is on its way.
Where do you go to see that?
Packets dropped.
Tomorrow I'm going to bring my sunglasses. Right?
We need to put a line on it.
Yeah.
Thanks for great talk. Yeah. I'm wondering about the tight coupling side.
About what?
I'm here.
Yeah.
I saw you wrap the key value error with HTTP status code.
Yeah.
Imagine we are not using REST API, but we want to separate our storage layer or whatever business logic from the API layer. In the future, I want to use a message broker to integrate with my components. So it looks like tightly coupled with logical things, with HTTP things.
Yeah,
what do you think about it?
This is an absolutely valid point, but this is the beautiful thing about refactorings. You don't stop there. If in the future you want to talk to a message broker or whatever, I guess it makes sense to do it like the other person said, to have an enum that is agnostic to his response format, and then decide on the status code by implementing the inter-response trait for this particular enum and looking at the variance and do the decision there. This is totally fine, because then you have a type that you can use everywhere for all message protocols that you want to use. But the interesting thing about this is, I'm not doing any premature optimization here or anything that makes it the most elegant version that it can be, so it works in the most scenarios that it can be. I'm doing it for what's coming up next. And I'm very well prepared for what's coming up next. If we decide to support more protocols, more outputs, whatever, then this would be the next step. So absolutely.
All right. Where's the box? Where are the hands? Excellent.
So you mentioned already during your talk that naming things is hard.
Yeah.
And combined with that, I sometimes come across projects where they implement their own logger trait for type, for example.
Logger, yeah.
Yeah, which is one of those things that everybody uses, logging and tracing.
Yeah.
So you shouldn't create your own type for that, right? Because otherwise you're just implementing all of these interfaces all the time. So how do you make the decision between doing that first step, introducing a type,
you are hitting a nerve here.
To a library?
You are hitting a total nerve here. I mean, I'm biased here because I work at Dynatrace, which is a monitoring and observability company. And when we do Rust, we do a lot of Rust in our company, and we use the OpenTelemetry crate and just be done with it. And we are very, very happy with it because it totally lines up with the software that we use. And for us, it was an easy decision. We want not only to log something and browse for logs and ignore it, but we want to send it to our monitoring software, and there's an ecosystem for that, and it's actually pretty good. So our decision was, let's take what the ecosystem offers for us, because we don't want to do their work, We want to move along with them. And if we don't want to do the work, Dynatrace is contributing to those crates, but you know what I mean. So this is something that should evolve separately from us. And it's good that it can evolve separately from us. So this is a dependency that we willingly take to have our software monitored. And yeah. So the decision is rather, I guess you need to evaluate it based on your context. If you work in an environment where every piece of your software needs to be certified and run through a certain piece of process, maybe having a third-party dependency that has lots of subcrates is not the right thing. Maybe you want to do it on your own so you know what's happening there. But in our case, it was easy. It was, hey, we want to have it in Dynatrace. This is the way to do it in Dynatrace.
Thank you.
Yeah.
Cheers.
Cool company.
Yeah, we can do one more question.
Yeah, if you want, we can do more. We've got some time.
I'm here all day.
Yeah, and I see a raised hand, so we could make this work. All the way in the middle, of course, so we could just lots of throwing really far.
Let's hop this again.
No, it's going to be a personal delivery.
As long as it goes up. This is a good team building exercise.
Thanks. Hi, thanks for a great talk. I really enjoyed it.
Thank you.
I noticed that you used a bunch of good things from Rust, so traits, structs, enums. I noticed also a very glaring lack of things like generics.
Yeah.
Now, was that on purpose?
Yes, this was on purpose for this kind of talk and for. It came along actually with the framework that I was using, which builds heavily on generics, so it does the heavy generic lifting for us, but there would be an extension. So this talk is based on a workshop that I did, and one of the steps after that was introducing a trait and working with generics to swap out the databases from, my hash map key value store to actually talking to a Postgres database or to an object store or whatever. And this is where we would have to introduce generics, but it's, 30-minute time slot. But really good question. So generics would be the next step, and they align very, very well with traits. So actually the last slide that you saw was kind of a, next time on refactoring in Rust. Because there we are not introducing a type, but we're introducing a trait. So we turn it around. We're introducing a trait and implement it for existing types. And this is where the generic stuff starts and where we basically create our own library for that. Yeah.
Come back for Rust Week 2026.
Oh, please. Oh, I'd love to. It's a fantastic conference.
We'll talk about generics.
Yeah, exactly.
Yeah, that's it, right?
Yeah, let's have another room change. Thank you so much to Stefan.
Thank you for having me.
Yeah, this is great. Thanks. So we just need to do like a little technical swap. People can move in and out of the room. We're going to set up another laptop real quick. And then in about 5 minutes, we're going to have the last speaker.
Last speaker.
Wow.
Wow.
Zo'n klein detail wat we...
Ja, nee, dat je dat glas.
Nee, precies. Get you some new water?
Oh, the music stopped, so that probably means that.
Is that our cue?
Yeah, that's our cue.
Oh, that's our
Absolutely.
cue.
Last speaker of the day.
Right, I lost my card, so it's all up to you.
Oh, yeah, but I got my card. And Pietro, we know him from lots of things.
Yes.
Crazy.io, DocsOS, Fair Systems, core team. And currently, I need to read this, the infrastructure release security and response team. Right? So
That's
proud to introduce Pietro Albini. Yeah. Thanks a lot. Take it away.
Hi, everyone. We all deserve helpful tools. We deserve tools that when something goes wrong, tell us something went wrong. We deserve tools that when something goes wrong, tells us why it went wrong, and what are the causes, what are the context around it that helps us understand what is wrong. And we also deserve tools that when something goes wrong, try to help us, try to point out possible suggestions, possible fixes, and guide us during debugging. And I'm sure we are all familiar with tools like this, because Rust is such a tool. The Rust compiler is so good at designing error messages and emitting correct and useful suggestions that I often like to call it your pair programmer that sits next to you and just helps you when something goes wrong. But this is not by chance. This is possible because Rust puts a lot of focus on error messages. It's one of the core principles of Rust. We had Alex early this morning that actually mentioned error messages as one of the major things. And that is not by chance. Rust's motto is empowering everyone to write reliable and efficient software. And I want to put focus on empowering. Because we are coming from a world where systems programming was only C and C++, only programming languages with a very steep learning curve. And Rust has one steep learning curve too. But the compiler, its error messages, help people let beginner understand their mistake and fix their mistake. And we're not alone in this. Rust is not the only tool that does it. It was not a tool that invented those, that pioneered error messages. A lot of the inspiration for what Rust does came from the Elm programming language, which is a functional programming language for the web frontend. But now that Rust got into the mainstream, now that Rust made it, its error messages are influencing all of the tools around us. Every year there is a new GCC release, and there's always this really nice blog post from Red Hat mentioning the new changes they made to error messages. And with giving something that, even though it's still not perfect, could still use a lot of work, is still miles better from where we were 5 years ago. This example in particular is from the latest GCC 15, where C++ template have kind of a tree-shaped structure when they're evaluated, and now they actually show those messages in this tree-like structure instead of trying to condense it into a linear message and creating a mess and a very confusing situation. GCC is not alone. Before working on Rust, Python was my main programming language. And there, in the last few years, there has been still improvements. It, again, might need some help. I would love some colors to just point out where things are. But in the last few releases, we now have Python that tells what part of the line caused the error, that gives you suggestion if maybe you just misspelled a variable name. And I cannot list all of the tools, either existing tools that has started to put focus on error messages, or new tools that are providing that are bringing fresh air, and along with the fresh air, better messages. But this is for tools written by others. What about you? How can you improve error messages in your project if you're developing a tool, a library, something other people use, or even just a side project for yourself? And this is what I want to cover today. How can we make error messages better? How can we make helpful tools? And I want to start doing it by looking at what Rust does. How does Rust do it? How are Rust error messages so good? And this is not a given, because having good error messages is actually really hard. Sure, sprinkling some color is a very quick win, but once you get into actually providing helpful suggestions, once you get into trying to put yourself in the shoes of your user and try to think, okay, if I were a beginner, where would I stumble and what would be the most helpful suggestion there? That is where it's really hard. But for Rust, errors are a core focus, are one of the pillars where of how everything is done. When designing new features, we often think, how can error messages explain when this new feature goes wrong? And everyone on the compiler team cares about error messages. It's not just a few individuals that go around and fix the bad error messages everyone else on the compiler team made. It's a systemic concern to have good diagnostics. And everyone I know on the compiler team puts effort into that. And it's such a core focus that bad error messages are actually considered bugs. In the Rust issue tracker, there are now around like 10,000 open issues. Around a fifth of those, 2,000, are diagnostic error messages, diagnostic bugs about an error message that could be more helpful, that maybe gives an incorrect suggestion, or that with a small change will just elevate the experience for all of the users. And 2,000 is a lot, but the other number is that around 4.7K of those are actually already closed and fixed. And there is so much effort into that. So one of the ways Rust does it is just having it prioritized, having error messages be at the same level as, like, if a change is made, a change needs to have good error messages, the same way it needs to have tests, the same way it needs to be documented, the same way its code needs to be maintainable. It's a first-class concern. And going back to testing, Rust tests all of the error messages. And this is actually really important because if you put a lot of focus on error messages and then an unrelated change makes them worse again, you wasted your time. If error messages are a first-class part of your software, they need to be tested like one. Rust's main test suite is called the UI test suite. And it currently has more than 19,000 tests. And those tests, that suite is called the UI test suite because it tests the UI of the compiler. It's made of 19,000 Rust programs, small Rust programs that are all compiled. And then we check whether the output of the compiler is what you expect. And if the test is supposed to pass, like if the program is supposed to compile, then the output, of course, is the banner that is executed. But if the test fails, then if the compilation is supposed to fail, then the output of the compiler is the error messages it gives. And that's what the UI test suite does, is it takes the output of each of those 19,000 tests and compares it with a known good copy of the error message. This is a technique that Rust did not invent. It's called snapshot testing, and it's useful not only when testing error messages, but in general whenever you do end-to-end tests and you need to assert on what the end result looks like. And if we just look at an example of how Rust does it, this is one of those test cases that in this case checks how casting between numbers and characters work. And we can see that it has three actual constant definitions. And the first two are supposed to error out. And there is a comment below them that in Stock Data Suite, please expect an error from this line. But this is not enough because, sure, this error tests that the message contains only U8 can be cast into char. But what about the rest? Along with this test file, there is another file with an .stdr extension that contains exactly the output that the compiler is supposed to give to you. And if any of those bytes is emitted differently by the compiler, the test will fail. Having a bad error message is a test suite failure. Of course, in some cases, this is expected, and then there are some tools that the compiler team uses to update the non-good copy. But often it happens that your change accidentally makes error messages worse, and this lets you notice that, this lets you fix that. So if you want to put focus on your errors, and I think you should make sure the error messages are tested. Same way you test everything. But Rust, it doesn't end here, because Rust has actually a disadvantage, is that it cannot control the quality of all its error messages, because when you misuse a library, the compiler cannot provide good error message information on how to best use that library. And we wanted to fix that, because since fairly recently, the Rust compiler allows us library authors to customize the error messages emitted by their library. And the same way that the Rust compiler team helps users of Rust have a good debugging experience, this lets library authors give their users a good debugging experience. This is done through the diagnostic tool namespace, which was an effort that, of course, as with everyone, every Rust feature was not developed by a lot of people, but was spearheaded by the maintainer of Diesel, Rust ORM that had a lot of complex error messages, and they wanted to improve those. The diagnostic tool namespace are a set of attributes that you can just put in your code, and if you're a library author and you're not aware of those, and your code uses a lot of traits, you should really look into, because let's just look at a few examples of what you can do with those. This is one of the error messages from the Diesel crate. And here, they are trying to query an integer and with a string. And that doesn't work because it is a type error. But the suggestion the compiler gives in the lower half is confusing and useless, because the compiler here actually tries to be too clever. And it finds that there is a less used implementation that might solve the problem, but is not actually what you want. So a thing we stabilized fairly recently is the diagnostic : do not recommend attribute that you can place on top of a trait implementation, and that will tell the compiler to never suggest that. This can be used in what is often called the pyramid of tuples, when a trait is implemented for tuples of variable length. With this attribute, you can avoid showing those. Or in this case, this is actually amazing, like removing that single trait implementation gave a useful error message, because it now said that the trait is implemented as expression integer is not implemented for a string, which is actually what you want. Another example is from the Bevy game engine, where they were trying to register a type. And here their message is actually good. Like there is not it's not misleading. It says that the trait type registration is not implemented for the type, which is what's happening. But with diagnostic on implemented, library authors can customize every part of the error message that they display to the user. And so not only they can change the message of the error, so in this case, my component does not provide type registration information. They can also add custom notes. Below, you can see, consider annotating my component with derive reflect, which is something specific to Bevy. The compiler cannot figure that out. But since Bevy knows that is correct, having that line provides an invaluable help for new users of the library. And so if you're a library author, please consider looking into this to help your users. And if you are working on any other project that accepts third-party inputs like dependencies, libraries, or something, make sure those users can cooperate with you to give better error messages. And so far, I talked good about Rust, good about its errors. But it's not always true. So what I want to do is take a bad error message, cause a bad error message with you, and see how we can improve it together. See what the thought process that goes into providing good error message. So let's just bind to SQLite. SQLite is a C library to have databases, to have embedded databases. And given that it's a C library, if you want to bind to it, we need to create an FFI declaration. So this is how you do it in Rust. You import the required types, and you declare what the function should look like. Then we add the link attribute to tell the compiler to link to SQLite version 3, so that in the end it will be included in your program, even though it's not written in Rust. Then we just call the function. It has to be unsafe because Rust cannot verify the safety of a C library. And then we just do some error handling. And this looks like a normal Rust program. And if we try to compile it, we're going to get this error message, which is a linker error message that if you're familiar with C or C++, you're probably scared about them. And linkers are like a small part of the toolchain that is executed at the end and pieces together all of the parts, all of the compilation parts to create your final executable. And those tools have not really improved in their error messages since the 80s. So, which is a problem. So here C actually shows you the direct error message that the linker says, and then tries to be helpful, like, no, some external function couldn't be found. But the suggested case is actually wrong, because Rust doesn't have the information the linker has. So let's actually try to make this error message better, and let's focus on the error message the linker gives you. This is not a great error message, but let's go through it bit by bit. The first thing on the error message is the path to the linker itself. This is not really useful if you're trying to debug why a symbol is missing. So let's just ignore it. The next part is the object file that causes the failure. And this is something that, except for linker errors, you're never exposed to object files, because they're an implementation details of how the build works, of how your build system works, of how programs on Linux work under the hood. But this doesn't point to anything in your program. This doesn't give you any context on what caused the failure. So this also should be ignored. Then we get the first useful bit of information, which is the name of the function that caused the error. But again, this is not the most useful way to do it, because if you have a very large project, just having a type name doesn't let you easily go to where the error is, because it might be more complex. Like, it might be complex to find the file. But let's keep it its useful information for once. Then it repeats the object name, because if you missed it before, you need to see it again, of course. And then we have where the error happened. And this is actually the exact location of the error, but it is possibly the worst possible way you could express it. Because it points to the section of the executable that contains the error, and then the plus 0x28 is the offset of the assembly instruction that caused the error. I don't know about you, but my editor cannot open that. But it's information, let's keep it. Then we actually get to the actual error message, which is undefined reference to SQLite open, so something is wrong with it. And this is the error message, let's keep it. And finally, we have a line, which is an implementation detail of how linkers are invoked on Linux. And it doesn't serve any purpose whatsoever if you don't work on build systems. So this is also useless. And if you look at it, half of the error message doesn't help you. And actually, I would argue it's not only noise, it's actually actively harmful, because if you're a beginner, it's the first time you see a linker error, then what is .rcgu.o? What is collect to? What is this huge string of text? It just leads you to, it might lead you to go into the wrong rabbit hole and waste a lot of time in things that are not useful. So let's just remove all of those. This is already way better. So please make sure to remove all noise from the error message. Actually, it wasn't fully noise, because if you were working on a build system, some of that information might be useful, but very few people work actually on a build system. So if there is that kind of information, it might be useful to display, but hide it behind a verbose flag. Hide it behind something that, think of the audiences that will see your error, and think of what they would like to see. So these are better, but let's continue to improve it. We can see that we have two ways of providing the location of the file. The function name that, as I said before, is not the best way to navigate through your source, and then the location in the object file, which is not great. Can we improve this? And the answer is yes, because that string of text, that huge string of text, is that because binaries, like your executables, contain information to turn that string of text into a line, into a file, and a line. This is the same thing that happens to display backtraces. So the linker knows it. The linker can use that information and provide this, which is slightly better than what we started with. So make sure that all of the information in error messages is actionable. That you can just take it and use it. You don't need to look how to convert that string into a file and a line. So we have this, which is better. Let's just sprinkle some color to it and maybe make it look more like Rust. And this is not just like a stylistic tweak. This actually helps because it puts more emphasis with the colors, with the bold, on what the important part of the error message is. It allows you to scan it quicker. So colors let users focus on parts of the error message and have intrinsic meaning. If something is red, in most cultures, that means it's something problematic. So take care of using colors when the user interface supports it. It's not just a gimmick. And so we got that error message from where we were before. Can we do better? This is just we just reformatted what linkers emit now. Can we do something more? And turns out, yes. Because linkers are linking together your whole program with all of the libraries. They know all of the symbols, all of the functions that are present. Why can't linker just say, help, did you mean SQLite free open? Because that was actually the error that caused the program to fail. I forgot that in this SQLite free library, functions are prefixed with SQLite free instead of SQLite. If the linker said that, and that is something that it could take an hour to implement. It's not something that requires a major architecture of the linker. Would save how many hours of people that just had a typo there and went into the wrong rabbit hole or had to open the documentation for the library and search for the function. This is way better. Can we do more? Turns out we can. Because on Linux, the way libraries are installed is standardized. And there is a file called package.config that tells you where each library is located. And this is shared across all Linux distributions. So what if the linker so let's say that the error was not caused by a typo, that I just forgot to link to the library. What if the linker just searches your system for libraries that contain that symbol? And tells you, hey, there's a library that actually provides the symbol you want, and here's the information on how to link to it. You should help your user. You should give them pointers on how to solve the problem, because that saves them time, because they don't have to look for the solution. But also, it helps users figure out which are not the most probable causes, where to go in their debugging experience, and save them a lot of time. And actually, the two suggestions I showed fix 2 of the 3 possible causes of linker errors caused by undefined symbol errors from Rust programs. And having good suggestions for 2 of them, the third, of course, unfortunately requires a lot of cooperation between multiple parties, so it's harder. this saves you so much time. And the good thing is, all of this is actually possible. What I showed to you today are not just ideas in my head, are not just mock-ups I made. I actually implemented all of them. A while ago, I started working on Plinky, which is a very side project of mine to try to implement a new Linux linker from scratch. And to be clear, this is very much not a project announcement. Plinky is not ready, is not designed to be actually used, and I don't think it ever will. It's just a way for me to learn how linkers worked. At work, a year or two ago, I got to a point where I got a very confusing error message from a linker. And I spent days working on it. And after that, I realized I don't actually know about linkers. And so I just wanted to try to make one. So the code quality is not really good. I didn't know anything about linkers before. It's just a playground for me to experiment, to learn. But while doing that, I realized that linkers have access to so much information. Linkers have so many details about your program, about what they're doing, and they could put all of that in their messages, but they don't. It was so frustrating that I decided, okay, Plinky is not just a way for me to learn. It's just like a way for me to learn, to experiment on how to push the boundaries. If you actually want to contribute to a linker or want to use a linker written in Rust, don't use Plinky, to be clear. David Latimore made a talk earlier today about his Wild the Linker, which is an actual project that actually works. And so if you want to contribute to one, go talk to him. He's in the GoSim Spotlight area. Don't use Plinky, please. But this is not just about linkers. This applies to all tools. I focused today a lot about tool chains for programming languages because that's what I like to work on. That's what I'm familiar with. But I made these slides in types. Types is a new alternative to LaTeX. And its error messages, its compiler suggestions are miles ahead from what LaTeX does. And this is in a lot of new programs that are starting to be written now. And originally I wanted to say, and here are some libraries on how to write better error messages or all of that. But that is not actually a good suggestion because good error messages are not a technical problem. They are a prioritization problem. They are a social problem. There is no reason why linkers back then could not have error messages as good as we have them now. It was never a priority. The reason why Rust has such good error messages is because we put focus into that. We care about those. And you should put care into your errors. You should make sure that if you're developing a tool, if you're developing a project, either as a side project or from your company, put care into error messages, prioritize their work, treat them as a first-class citizen. We all learned Rust, or are currently learning Rust. And I am right now fairly experienced in Rust. I know what is the cause of a lot of the error messages, so I don't care too much about how an error looks for Rust. But when I was learning Rust, they were invaluable. And all of the work the people did before me helped me learn Rust. And if you're currently learning Rust, I'm sure that is the same for you. So everyone before us helped us make good error messages. And I strongly believe that we owe it to the next generation of programmers to make tools even more helpful, to give them more suggestions, to give them good resources to debug, because we all deserve helpful tools. Thank you.
Amazing, Pietro.
Yeah, that's
amazing.
fantastic. Yeah.
We wholeheartedly agree. We were like nodding along.
Yes.
I am blinded by the lights. I cannot see anyone.
No. We've been doing this all day. No, but the first thing I thought was that in the olden days, sort of the fact that you get this error message and you don't understand, that means that you're obviously not smart enough to be programming in this language. This is sort of, I don't know what the word is, arrogance maybe. And I love that Rust is so much more helpful. I think it also says a lot about sort of the community and how it works together.
Yeah. Right. Should we move on to some questions from the audience? Where are the hands? Put them up high. Yeah. I see some over there.
Lots.
Amazing, amazing.
Almost.
2 hops.
This
All right.
one. Okay. So, with your suggestion about testing error messages in the test suite, I am worried about that becoming a scalability nightmare. So, can you say something about the tooling you mentioned in Rust compiler for updating those tests when you want to change the error messages?
Yes, absolutely. So like that is a tooling problem, and Rust solves this by Rust uses its own custom test infrastructure because a lot of the complexities of testing a compiler. Basically, the way it works is that there is a command line flag you can pass to the test suite called --bless to put your blessing on the new outputs of the tool or the new outputs of the errors, and then the test suite will automatically update the files. So if you make a change that changes 200 errors, you just do x test bless, and it will automatically update all of those. Outside of the Rust test suite, what I really recommend is using one of the snapshot testing libraries that exist in Rust, because all of the snapshot testing tools have a way to automatically update the blessed version of the output. So there are, for example, in Plinky I use Insta, which is one of those libraries. And there after I change the error messages, I just do cargo insta accept, and it's going to update all of the saved examples. So here, the only solution is to use one of the libraries that provide this.
All right.
And for the bad example you gave from the linker, all of that stuff probably wouldn't be noise to the developers of the tool, because they might care about those details like the name of the object file and so on. So what are some good practices for maybe hiding unnecessary detail from the release version, but still maybe outputting it to help you debug issues for you as a developer of the tool?
So for the developers themselves, I would argue error messages are not, user-facing error messages are not the way. Their logging might be more helpful because it not only includes context about the error, but what led to the error. And that is what the standard in the Rust ecosystem does with the Rust log environment variable when you can toggle on and off error messages. Another thing, because you need to think about the audiences of your errors, who is going to see them? In the linker example, an audience is all users compiling Rust programs. But another audience is authors of a build system, where the name of the object file is actually really important, or the name of the symbol is really important. And there is no good solution, because it needs what is the audience of your tool. For something that most people don't care and only a few people care, maybe putting a verbose flag might be helpful, so that, or say, if you want more information, pass -- verbose. It all depends on on who your users are and what do you expect most of the users to care about.
Right. Very good. Where's the catch box at? Has it moved?
Yeah.
Can't see it all. I just wanted
you
to
throw
say,
it over there?
I've been implementing a programming language, and I've been looking at Rust error messages a lot, and it surprised me based on just sort of the feeling how terse they were sometimes, which is so the part of eliminating the noise really resonated with me. It's a good error message doesn't show you what you can't use. I thought it was lovely.
And those are really hard. I cannot put enough emphasis of how much work and how much code goes into implementing the Rust error messages. Like, there are people whose only contributions to Rust, or most of their contributions to Rust, are just improving error messages. It's like, not trivial, but I think it's worth it.
Yeah, fantastic.
Did the Couchbox end up at the correct location?
Yes. Well, it ended at the correct location, then it was the same question, so it was passed on to me. I love the error messages in Rust, especially someone who's more of a learner. But as I understand it, a reason why Rust error messages can be so good is because the type system is so good. So maybe from the design of Rust, it's easier to know what's gone wrong. So prioritizing error messages, to what degree does that influence the implementation itself? Because maybe some information now has to be kept track of that didn't have to before, or maybe that places limitations on how good the error message can be. So how does wanting good error messages implicate itself in the development process itself?
Everywhere.
Okay.
Like, I mean, it's goes to what I said before. Like, there should be one core priority for you, because then you don't add error messages the last minute, 10 hours before the release. You think about error messages while you implement the feature. And some features in Rust had their design changed because of how do we teach this feature. And how do we teach this feature includes how can we explain when things go wrong, how can we design the error messages. Because it is a teaching problem in the end.
Yeah. Should we do one more?
One more.
One more.
One more.
Where's the box at?
If there is one.
Oh, I see box being held up high. Is there a question?
Yes. There. Excellent location.
I don't know how you can see anything.
I can't.
Yeah, it's more like edge of the shade.
Oh,
yeah,
okay,
Now I'm blinded again, and now this is what I'm doing all day long.
Sorry. I think for me, to make a remark rather than a question is, I think, for example, for linker, it's important that if you compile for a C file, the object file name is very important, so you probably want to keep that. I think the important thing is actually, ideally, you will keep your error message structural so that it can be understood by another tool. For example, rustc can generate error messages in JSON, which Cargo and Rust Analyzer can then parse and then emit it in their own format. So for example, the linker can include the object file in a field, and which, if the rustc understands the linker, a structural error message from the linker, then can just present this in a better way to the user.
Yes, absolutely. That is, I guess, an implementation detail, because from the point of the user, you still, in Rust, you don't care about the object file. And also, it's something that is hard for interoperability, because right now there is GNU-LD, there is LLD, there is Mold, we are creating Wild. We will need to have all of those projects agree on something, or have every downstream tool implement support for 5 different linkers. It starts to become problematic. But that's an option, and that's an option I would like to see. More structured errors is one of the options now to do that.
Great closing words.
Very good.
Yeah.
Thank you very much, Pietro.
Yes. Also, if you are attending the 10 years of Rust celebration, I will be doing a release live. At the release of the next Rust version, which is 187. So come see us, come see it.
Yeah, there's still tickets available, I think.
Yeah.
So you should all come and see a live release of Rust 187, right? 187. All right. That leaves us to close the day.
Yeah, absolutely. You are holding your phone. Does that mean you're going to read out something, or
no? That's just because I lost my card.
Okay, yeah. But anyway, so there's going to be drinks until 7, but all of these cinema rooms they need to be cleared out by 6. So that's about in about 20 minutes. Also on Friday there's a hackathon which is free for all of you to attend. Lunch will be provided during the hackathon, so please attend it if you have the chance. That'd be great. And is there anything else on my card that I want to mention?
I think it's just that we all want to see you back here tomorrow
At 8:30.
And the venue opens at 8:30. We'll start, I think, an hour later.
Yeah, absolutely.
So, see you all tomorrow.
Thank you very much.